Yeah.
So such expansion waves are found here, or
they are quite weak.
quite weak. So
It's
you're
there.
not able to.
We can, if we see the pressure contours, we can see that there is an expansion,
So
but we can't
can-
really.
Yeah, we can just note the pressure in the negative x direction, so that we can see that an expansion wave or not. Because that is called the Gooderly theory, the fourth wave theory.
Yeah, that's what is the thing. The expansion fan, the formation of the expansion fan. It's there. I haven't shown this. But because it's very weak, it's not showing up in the contours.
You need to plot the pressure.
We have to
see that.
Yeah, I'm more interested in the supersonic.
And I'm sorry, I'm very happy that with the viscous effect, the patches are increasing.
Yeah.
Because then it's easy to visualize that using Schlieren now.
Yes, that's true. Yeah, that's the thing that kind of confuses. Yeah, conflicting.
Right. I think we have run out of time.
Fifth order. Yeah. Miss it.
Yeah. So we'll thank the speaker once more. The work was co-authored by Professor M. Ramakrishna, and 1 second. So the next paper in the session is on the development and assessment of open source hypersonic equilibrium flow solver by Anurag Aditya Narayanan and Ashok Dey from IIT Kanpur. The presenter is Mr. Anurag. Yeah. Welcome you on the dais.
Okay, good morning, everyone. I am Anurag Ray, working under Professor Ashok Dey at IIT Kanpur. Today, I will briefly give you a glimpse on the aspects of the solver development that we are carrying out in our lab. So before that, I would like you to briefly give you the glimpse of what hypersonic flow really is, although we know it, but that will be much more helpful for me to make you understand the development aspects of the hypersonic flows. Then previously, what are the computational efforts carried out various research groups? I'll be briefly talking about that as well. And finally, after understanding those aspects, I'll be trying to give you certain voids that needs to be filled. And I'll be talking about some of the aspects of governing equations as well, which is the backbone of the solver. And finally, I'll talk about the validation studies based on the increasing order of complexities. So the hypersonic flows, what are they? Generally, it is said that if Mach number is quite high, or let's say if Mach number is greater than 5, that flow field can be termed as an hypersonic flows. But according to J.D. Anderson, that is not only the sufficient criteria. For hypersonic flow, there needs to be some additional flow features to be visible as well, which demarcates it from the supersonic flow. And one of which is a thin shock layer, because the shock wave is lying very closer to the surface of the body. The shock layer, that is the fluid region between the shock wave and the surface of the body, is squeezed in between, and which creates the high density region. Second is the viscous interaction. Because of the leading edge shock wave and the thick boundary layer developing on the surface of the body, it may interact to create high peak pressures as well as high heat loads. And the high temperature effects are quite evident in hypersonic flows as well, wherein the post-shock temperature reaches to a quite high value, and it is sufficient enough to trigger vibrational relaxation as well as chemical dissociation reactions taking behind the shock. And also the heat transfer due to radiation cannot be neglected further. And moreover, to mitigate these high temperature effects, there has been a lot of studies to modify the geometry and include the bluntness wherever possible. And because of the bluntness, there is the formation of a detached bow shock. And the streamlines crossing the different portions of that detached bow shock will experience different entropy changes. And because of which there will be a formation of an entropy gradient perpendicular to the surface of the body. And it may again further interact with the fluid, with the hydrodynamic boundary layer to complicate the flow physics further. And more importantly, the low density effects is not an inherent part of the hypersonic flow, but most of the vehicles are flying at a very high altitude, as well as the re-entry vehicles is entering from outer space to the planetary atmosphere. So there we generally see the hypersonic flows. So it is not a direct consequence of hypersonic flow, the low density effects, but it is generally seen in those regimes. So previously, a lot of experimental and numerical studies were carried out to understand what hypersonic flows really are. And if we talk about the computational efforts, it was dated way back in 1994, where NASA first came up with a DPLR line algorithm, which is data parallel line relaxation algorithm. And at that time, that solver was quite popular to solve the supersonic flow problems. And they were able to solve the flow problems with a short period of time because of this novel algorithm. However, they tried to include the effects of hypersonics, such as vibrational excitation and chemical dissociation. And they found out that it was quite computationally expensive with the inclusion of those kind of sophisticated effects. And because of which they said that the cost of computation varied with the number of species considered in the medium. Later in 1996, an effort was made at Langley Research Center, which was an upgraded derivative of DPLR code. And although they were able to reduce the cost of computation and as well as optimize the resources used, they wrote a simple code which was valid only for simple geometry such as flow over ellipsoid or paraboloids, which are basically the building blocks of the re-entry vehicles. Later, 30 decades later, almost, a commercial code was later developed at US3D, named as US3D, which is unstructured 3D, which is a derivative of DPLR algorithm. But they suggested a new time integration strategy or a new algorithm, improved algorithm that reduces the cost of computation as well as it is able to solve the flow problems within a short period of time. So what they suggested is they decoupled the sophisticated effects of hypersonic flow, such as the chemical dissociation reaction and chemical vibrational excitation, and they solved the Navier-Stokes equations independently with that, and they applied DPLR algorithm for the Navier-Stokes equations only. So because of which they gave a severe drawback that this kind of solver is mostly will give a correct result for steady state calculations, but they were not sure of the unsteady state calculations. They gave a word of caution for that. And to overcome this also, they were still sticking with the one temperature model itself. And after that, an interesting research group was trying to develop a solver named as Hy2Foam in open source based platform. Although all the reaction effects and every models were included in that, but it used first order time integration, which can be quite diffusive, as well as it had an implicit algorithm to march forward in time, which can be quite unstable if the Mach numbers or the speed of the free stream speed can be, if it is high enough. So we see that most of the solvers were not available in public domain till date, such as the code which is developed at the Langley Research Center. Most of the codes was very old and it uses the resources in a non-optimized manner. It solves the flow physics with very simple geometry, such as the code which was developed at LoRa itself. And it uses simple one temperature model only. And even if the code is open source based, including all the sophisticated effects of hypersonic flows, used implicit scheme of lower order, which can increase the numerical diffusion, as well as it can cause stability issues at high Mach numbers. So I'll briefly walk you through the governing equations that is needed to be understood in order to couple the sophisticated effects of vibrational excitation and chemical dissociation. So first of all, I have solved the conservation of mass for each of the species. This is a basic convection diffusion equation with a source term. The source term is calculated using the law of mass action for each of the elementary reactions that can be considered to be happening behind the shock. I've solved the conservation of momentum in its original form itself, and we have tuned bit the total energy equation, wherein the total energy is decomposed into the internal energy and the kinetic energy of the flow. This internal energy is then composed of various internal energies of individual species multiplied by its mass fraction and then summed over to find out the total internal energy. Internal energy of each of the species is further decomposed into an equilibrium part representing the translational rotational energy as well as the vibrational part, which needs to be found out to include the effects of vibrational relaxation. The equilibrium form of the energy can be found out in this manner, and then the heat flux vector is composed of multiple modes of heat transfer due to Fourier by vibrational as well as the transrotational temperature. And because of diffusion of species also, there is some kind of energy transfer as well, but in our study we have neglected that. And to find out the non-equilibrium part of the internal energy, we are using again a convection diffusion equation for with a source term. This diffusion term is also modeled using the Fourier mode of heat transfer as well. And again, there will be energy transfer due to diffusion of the species as well. And again, we have neglected over here, which doesn't contribute much into the solver. The source term is further classified or decomposed into two parts, one representing the vibrational translation and energy exchange that might be taking place, as well as the vibrational chemistry energy exchange because of the formation or destruction of the species. And finally, the vibrational translational energy exchange has been modeled using classical Landau-Taylor theory, which has been quite popular recently for simulating the vibrational excitation. The equilibrium portion has then been calculated using that formula that I've highlighted, and all the relaxation time for each of the species has been calculated using Millikan-Schweitz expression. And finally, the pressure that I'm finding is using the Dalton's law of partial pressure, and each of the species is assumed to follow the ideal gas law. And to calculate, and all the elementary reactions are either taken from Park's 1993 reaction rates and Dunn and Kang's reaction rate and recently developed quantum kinetic reaction. So I will briefly walk you through the validation cases that I've taken up to validate my solver. The first one is the zero-dimensional heat bath case, which is simply a small cubical volume composed of nitrogen atom as well as nitrogen molecule. We are just interested in looking at the interaction of the source term for the reaction and for the vibrational excitation, and study the evolution of all the flow properties within that control volume. So these are the initial conditions that I have used. You can see that vibrational temperature is quite much lower as compared to the transrotational temperature in my study, and rest of the other initial conditions is shown in this table. So we have plotted the temperatures, that is vibrational temperature and transrotational temperature with time, and also the evolution of the species with respect to time. The figure on the left shows the translational and vibrational temperature evolution with respect to time. We see a pretty good match has been obtained with the high-to-foam solver, which has been shown over with the square symbols. However, we see a quite amount of discrepancy with the particle-based approach of DSMC foam results, and this has been attributed in literature because of the modeling difference between the particle-based approach and the continuum-based approach. Similarly, we see a quite good amount of match with the high-to-foam solver for species evolution as well. Now, instead of considering non-equilibrium, I have considered equilibrium between the vibrational temperature and the transrotational temperature itself, and rest of the initial conditions are given in this table, which is similar to what we have just seen. So again, this temperatures profile are quite accurately matching well with the high-to-foam solver, although we see a certain amount of discrepancy almost before 10⁻⁻⁶ seconds, that is 1 microseconds. That I think is attributed due to the non-inclusion of the vibrational energy exchange that might have taken place. And I have neglected that in my study, which in some literature has been stated that it doesn't contribute much to the solution. But however, we are seeing a good match with the species evolution with time as well. Now, I solved a little bit complicated case further than the previous one, which is a one-dimensional reacting shock tube. We see there is a diaphragm over which the flow states are separated, and all the initial conditions for this driver section and reverse section is given in this following table. So we have obtained the profile along the center line of the shock tube, and we see quite good amount of match has been obtained by us as compared to the previous computational studies. Also, we have plotted the density profiles and the mole fraction of atomic nitrogen as well as mole fraction of nitric oxide. However, we see a certain amount of discrepancy just behind the shock for the density. I think this is because of the non-correct amount or the incorrect amount of the species that might have formed behind the bow shock. But to ascertain that, I really need all the data for different species as well, so that I can find out the total amount of density just behind the bow shock, and then we can check whether that is creating the problem or not. Fortunately, we have been finding a good amount of match for the mole fraction of nitrogen atom and nitric oxide. Now moving on to even a further bit complicated flow field, which is two-dimensional hypersonic flow over cylinder. We see I've used this computational domain with the relevant boundary condition. This is acting as a free stream inlet. These are acting as the outlet, which is wave transmissive. That is, all the quantities are being transported outside the domain. And also, we have used a slip adiabatic wall for the cylinder. And free stream conditions has been given in this following table. We have obtained the variation of properties along the cylinder in the azimuthal direction. And we see properties such as pressure, temperature, mass fraction of nitric oxide, and mass fraction of O is quite pretty much matching well with the previously established computational results. So with this, we get a confidence that our source terms and all the implicit parameters are working quite well. And we further wish to develop to include the viscous effects as well. So with this, I conclude my talk over here. These are the references that I've used. Thank you.
Time for a few questions.
The present case, your scenario is a single species gases on either side.
For the zero-dimensional case, yes, it is single species.
So can you suggest how we can try to model the wave transmissive conditions for a gas mixture if we have it?
We can definitely, we are using the transport equation for individual species. So each of this transport equation can be convected simply out of the domain just by writing 1D convection equation.
Same is for even the acoustic waves also.
Yeah, it is same exactly. That was meant basically for acoustic waves, but it basically works fine with the Euler equations as well. So that's why we have used.
Could you tell us a bit more about what numerical schemes you used?
Okay, sorry, I forgot to tell about that. I have used for convection flux splitting, I have used Kurganov-Noel and Petrova scheme. And for time integration, we have used the third order accurate RK4 time integration scheme with an explicit time integration instead of implicit one.
I have one question. So generally source terms when you have reactive flows are treated implicitly, right? But here you are treating everything using an explicit time integration. So
Yes,
what
sir.
impact does it have on the, number of time steps, the time steps that you choose, and the number of time steps you require for getting a solution?
Uh, Actually, if we exclude the implementation of the reaction portion, earlier it was seen that with the implicit time integration, which is based on operator splitting approach, for very high Mach numbers, it has caused spurious oscillations behind the shock waves.
I'm just talking about the source term, the reaction term.
As such, it has not caused any trouble for us, but it needs to be included just because that source terms values are quite high. And in order to match that source term, we have to pull down the time steps much lower to this.
Yeah, because I think the time scale for the reaction is typically much smaller.
Yes, sir. It generally in literature it has been quoted that the relaxation time that I was talking about using Millikan's White expression, the time step should be 1.1 times of that relaxation time. So that would be sufficient enough to capture the vibrational excitation. Similarly, we have Damkohler number for species production as well. So based on that also, we need to check the time, what time is required to capture the reactions that is happening.
So as of now, everything is explicitly integrated in.
Yes, sir. But for now, we are using the fixed time steps. So for now, I have not included those aspects.
Okay, so if there are no other questions, let us thank the speaker once more.
Thank you.
We will move on now to the next talk, which is effect of polynomial degree on discontinuous Galerkin simulations of compressible flows. The authors are Vachan D. Potluri, Balachandra P. Puranik, Kaushik V.R. Bodhi. And the presenter is Mr. Potluri.
Good morning, everyone. So we have conducted a study where we have studied the effect of polynomial degree on DG simulation of Euler equation. So as Shiva already described, DG method is a finite element inspired discretization, mainly being used for convection dominated PDEs, where in every element we use a high order basis to essentially get a high order accurate solution. So if we use nth degree polynomial basis, we theoretically can get n+1th order accurate solution. So that means that for a quadratic or higher basis, we get greater than third order accuracy. That's generally considered high in the CFT context. The problem in going to arbitrarily high order accuracy is how do we handle shocks? Since the PDE becomes invalid at the shocks, there needs to be additional stabilization done so that the computation is stable. In the DG context, this is called limiting. That's generally done by adding additional dissipation or by filtering out the high order modes. And these techniques are generally inspired from second order finite volume theory, which are considered robust for handling shocks. So then we got the question, which is natural, that given that the limiter does something extra inspired from the finite volume theory, how accurate will these methods be when we apply them for discontinuous flows? So we are trying to answer this in this specific context, where we study the Euler equations with an in-house implementation of a subcell limiter that was recently proposed. Let me briefly describe the algorithm in one dimension. So let's take the 1D Euler equations on a single element, which is omega e here. They are mapped to the reference element, to the reference space, and then we approximate u and f to lie in a linear polynomial space. So u and f are approximated using a linear combination of these basis functions Li. These Li are defined such that they take value 1 at the ith node and 0 at every other node. The nodes themselves are just Gauss-Lobato points. Now, of course, this approximation will introduce an error, and that error is minimized by minimizing its projection on the basis space. And we thus get the nodal DG discretization, where this matrix vector operation now represents the flux derivative. Now it turns out that if we use collocated quadrature to calculate the elements of this matrix, then this particular term can be written as a flux difference of some auxiliary set of fluxes defined on a new set of points, which are called flux points. So how does this help? Suppose we consider the region between two flux points as a subcell. So this is an element, this is a subcell within an element. And if we assume that the value inside the subcell is equal to the nodal value, then we can simply calculate this auxiliary flux as a numerical flux between two subcells. So that gives a low order scheme, abbreviated LO here. So that can be expected to be stable at shocks. However, we have lost nothing in doing this. We can still define this auxiliary flux in a certain way to get a high order accurate scheme. What the limiter does is it blends both these formulations using a weight alpha, and the value of alpha is set high near discontinuities so that we get a stable discretization. And then these are integrated in time. We are using a low storage 5-stage RK4 algorithm. So let's come back to the question of how the basis polynomial degree affects the solution. So suppose we take a grid and use two different values of n on the same grid, then we see that the one with the lower value of n has lesser number of nodes. So in this example, n equals 1 has 4 nodes per cell or 4 nodes per element. N equals 2 has 9 nodes per element. So this will consume lesser disk space. So we are sort of handicapping this one while performing the simulations. So a better way we thought would be to increase the number of cells for the lower n case so that we now have the same total number of nodes in the domain. So we have unintentionally stumbled upon this question of how are we going to assess the performance. And the first one, as we saw, is the memory requirement. And that is mostly the volumetric data is what consumes the most memory, which is directly proportional to the total number of nodes in the domain. So NE is the number of elements, and n plus 1 power d is the number of nodes per element. D is the space dimension here. So that means that if you want to guarantee constant memory usage, then if you change n, you have to change the grid also. The second metric, of course, is the accuracy. If we have an exact solution, we can use the norm of the error as a measure. But in many cases, we don't have an exact solution. And many times, a single value is also not representative of the solution. So we also do a visual comparison, which is not quantifiable but useful. So we first consider the Schuh-Osher test case, which has an interaction between shock and an entropy wave. And we are mainly focused on how the capture of the shock and the high frequency waves behind the shock change as n is increased. So these 4 simulations use 4 different grids so that they have the same total degrees of freedom. And we see that as n is increasing, that's from left to right, we'll see the insets. The shock thickness is getting better as we move from left to right, and so does the resolution of these high frequency waves. At medium resolution, we see similar trends in the shock resolution. The high frequency waves do not improve after this point. And at the highest resolution, the shock thickness is almost the same. But again, the high frequency waves, they improve up to this point and then not much after that. And then we consider the 2D double mark reflection case. So again, the same 4 values of n. The grids used are set up such that all cases have nominally these many number of degrees of freedom. So the figures here show the density contours with surface plots of the vertical momentum. So we immediately see some wiggles in the density contours for n equals 2 and 3. That's because the ranges for density in all these cases were different, but the contour values used were the same. Other than that, we also see a staircase-like pattern in the incident shock and the reflected mark stem. for n equals 2 and 3. The thickness is mostly the same. The mark stem thickness is also almost the same in all cases. However, this triangle of waves, which is the reflected shock, secondary reflected shock, and the slip line, their resolution is getting slightly better up to this point and not much beyond that. And so does the resolution of this slip line bending. That's getting better up to this point and not much beyond that. So there are no significant differences between these three cases in this particular problem. So finally, we consider the 1D short shock tube problem. So here we are interested in the resolution of the shock and the contact. So at the lowest resolution, we consider the shock thickness. That's getting better as we move from top left to bottom right. The contact thickness is getting better up to this point, not much beyond that. At a medium resolution, both the thicknesses of the shock and contact wave, they are getting better up to this point and not much difference beyond this. And at the highest resolution, the shock is almost equally well resolved in all cases. And the contact resolution is getting better up to this point and not much beyond that. Since we have an exact solution here, we can calculate the error. And it turns out that if we fix the number of degrees of freedom, then the error actually drops as we increase the value of n significantly up to n equals 3, but not much beyond that. So what we saw was that if we fix the memory, which is the number of degrees of freedom, and if we increase n, the error was dropping. Now we like to add one more dimension to this analysis. So that is the cost incurred in performing the simulation. So in that case, we would be doing an error versus cost analysis while keeping the memory fixed. So one estimate which we all really care about is the CPU time, but problem in using that, it's implementation specific. It depends on who writes the code rather than what the algorithm is. And I am by no means an efficient optimizer. The second thing we have to keep in mind is about the time step. So the stable time step in a DG method that scales as the cell size divided by the spectral radius of the discretization, the differentiation operator. And if we keep the number of degrees of freedom fixed, then the cell size scales as n plus 1. But the spectral radius for small values of n, it can be assumed to scale as n power 1.5. So the stable time step drops relative to when we use a linear basis as we keep the degrees of freedom fixed. So that means we require more time steps to reach the same end time. So keeping these in mind, we already saw this one, how the error changes with n as we keep the degrees of freedom fixed. So we now add this plot. This is the comparison of the relative CPU time. So the CPU time when we use a high order basis relative to when we use a linear basis, keeping the degrees of freedom fixed. So we can see this increases. It's more meaningful if we club these two plots. So here we have the scaled L square error on the y-axis and the scaled cost, which is the CPU time on the x-axis. And the dotted line here is a sort of the break-even curve. It's y equals 1 by x. That means that as we move on this curve, the factor by which error drops is equal to the factor by which the cost increases. And in this case, all the data points are above this curve. So we could conclude that there is no real improvement if we add cost into the picture, except maybe for this point. So in summary, we have seen that as we keep the degrees of freedom fixed and increase the polynomial basis, in smooth problems, the accuracy improvement was persistent up to n equals 5. But as the discontinuities get stronger, it sort of plateaus at lower and lower values of n. And in visual comparisons, we see that the accuracy improvement was more prominent at low resolutions. So these observations, they suggest a particular kind of HP adaptation. So the P adaptation is regular. We use high N or high P in the smooth regions and low value near discontinuities. And we can simultaneously change H, the grid size, to keep the degrees of freedom approximately the same. What this will guarantee is that we can get a more accurate solution without increasing the disk space, that is the memory usage. And what happens when we add cost to the picture? Well, for our specific case, for the solid shock tube case, we saw that the all points we consider were above this break-even curve, except for this one case. But let me conclude by saying that by reminding again that is specific to the implementation, and it's more an attribute of our implementation rather than the scheme itself. Thank you.
Next presentation, Mr. Patturi. We can take a couple of questions. And we'll start with one question. If you can go back to your shock tube simulation.
Yes.
Yeah. So in this picture, I see that there is a kink for the n equals to 1
This one.
weight
Yes, sir.
polynomial, where it's not there for the higher order polynomials.
It's there, but it's
Yeah, so
damped,
it's getting
sir.
reduced weight. Why is that? That seems counterintuitive, no?
We have not investigated this much, sir. But so I think in an element, when we use a high order basis, the nodes are more closer to the edges of the element, and they are more coarsely spaced in the middle of the element. And since this is a discontinuity, the numerical flux has a significant effect on how the solution behaves. So I suppose that having more number of nodes closer to the element boundary is making it is damping the kink in high order cases.
Not very clear, but where are you plotting this? At what locations are you plotting
So
this?
all these are taken on 1600 equally spaced sampling points,
Okay.
and the solutions are obtained by evaluating the solution. Meaning, so we have a polynomial variation within every element.
Mhm.
So we evaluate the solution on these 1600 sampling points to obtain these plots.
That can have a bearing on the plot.
It will, sir, because suppose we just plot the nodal values directly, then those will have different values, but not by much. So since we wanted to maintain consistency, we have used equally spaced 1600 sampling points in all cases.
I'm just wondering if that has an effect on, I mean, is that responsible for this non-intuitive behavior of the solution?
It might be, sir, but as far as I am, according to me, the solution within an element is a polynomial, which the scheme gives. And I think whatever sampling points we evaluate at, we are supposed to get a reasonably good description of the solution. That's what I think. So if it is a dependency, if there is a dependency on the points we take, then I suppose that's how the solution is, because it's
You
really
can have discontinuity inside an element or only at the element?
no, sir, only at the boundary.
element boundary. Then, yeah, then it may not be the case, but yeah, again, that for n equals to 1, why you are getting a higher discontinuity that you might investigate.
We'll investigate that.
Any
Thank you.
other questions?
Okay.
200 points.
Okay.
You sample at 3200 points, I think you'll see a change between n equals 3 and n equals 5.
Okay. We'll have a look at that. We'll investigate. Thank you. Yeah, definitely. So
It's done using a single particular limiter.
correct.
So-
So all these results are very specific to the limiter picture, because these are for discontinuous flows. The
Yeah.
limiter is what dictates the accuracy rather than the original scheme itself.
Even the kink might be because of that.
Yeah, definitely.
Yeah.
Definitely. The limiter is what has a significant say in these cases. So that was our aim. We wanted to see, since a limiter is inevitably used when there are shocks,
Yeah.
how the solutions behave when we increase n with the limiter imposed. So rather than just doing simple smooth flows.
Let's thank the speaker once more.
Thank you.
We'll now move on to the fourth presentation in the session. That's on dynamics of unsteady shockwave reflections using overset mesh approach. The authors are Nikhil Jacob, Manoj P.J., Sumesh Babu CV, Leo A.G. and V. Lijo. The presenter is Mr. Nikhil Jacob.
Good morning, all of you. Myself, Nikhil, and I'm going to present a topic, dynamics of unsteady shockwave reflections using overset mesh approach, co-authored with my professor, Dr. Lijo. And these are the contents of my presentation, and we will go to each one of them one by one. Actually, what we are discussing here is the shock reflection phenomena, which is often studied numerically or experimentally by the interaction of a wedge which is placed in a supersonic flow. And we investigate two types of reflections that most of us will know. That is the regular reflection, and the second type of reflection, that is Mach reflection. So we have classified our domain into three categories. So that is the first domain where only regular reflection is theoretically possible, and the second domain where Mach reflection is possible, and a domain where both regular reflection as well as Mach reflection is possible. So that has been investigated by people before. And what I have shown is a regular reflection and a Mach reflection pattern, as you can see in this slide. So we will be concentrating on the dual solution domain region, where we have the presence of both regular reflection as well as Mach reflection. And this plot is actually the shock angle versus the Mach number configuration. And in the dual solution domain, we can see two boundaries. That is actually the von Neumann criteria and the detachment criteria, which defines a shock angle for a particular Mach number. And my case in this work is actually Mach 4. And by theoretical von Neumann criteria, we define the shock angle to be 33.26 degrees. And for the detachment criteria, it is theoretically 39.2 degrees. And we are numerically investigating an unsteady problem here. And the rotational speed of the leading edge of the wedge is given a certain rotational speed, and we are numerically investigating the case. So since studies has been scarce on higher rotational speeds, the case becomes significant numerically to investigate the problem at certain higher rotational speeds. And regarding the literature review, Bendor and Ernest Mark has investigated certain phenomena regarding Mach reflection in the previous studies. And von Neumann was the first to propose these two conditions as a possible RRMR transition criteria. And as I have said, both of these boundaries together represent a dual solution domain case. And our region of investigation is actually this case, where we observe a certain transition from a regular reflection case to a Mach reflection case. And for a perfect gas, the critical Mach number is actually 2.202, and ours is Mach 4. That is what we have used in this case. And also, Skews in his previous studies has investigated the dynamics of a rapidly rotating wedge. It was at a Mach speed of 3, and he has done it for various rotational speeds experimentally. And regarding the research gap that I have seen, In experiments, when I have conducted the review, literature review, I have seen that rapid wedge rotation reported in experiments was almost about 11,000 degrees per second. And numerical simulations, we can permit high rotational speeds. And this is practically impossible in experiments due to the inertia of the wedge, and we require a certain amount of infinite acceleration. So what we have employed here is an overset mesh, because deforming meshes usually have a poor quality when we do a work like this. So we have numerically simulated speeds up to 75,000 degrees per second for the dynamic investigation, and it was actually not reported in much of the works earlier. So I think it is significant to conduct some numerical experiments up to that much speed of consideration. So we have employed an overset mesh formulation, and this is about to ensure good mesh quality during our formulation. So I have done numerical investigations on these particular cases where we have investigated the dynamic effect of wedge rotation on shock transitions from a low to high speed range. And these 5 cases of rotational speeds numerically were investigated. And this is the domain that I have used. So I have employed, as I have told, I have employed an overset mesh. And the size of the wedge or the length of the wedge was 80 mm. And there was a symmetric boundary condition as well as a far field boundary condition. Mach number of 4 was used. And there was a background mesh as well as a foreground mesh, and the overset interface is shown. So we have done the grid independent study, and it is actually not shown here. A minimum number of element size was used when we created a second order polynomial fit for the maximum height plot. And this is the mesh. We incorporated the overset mesh for the work here. And as I already told, it is an unsteady simulation. So we have used a time step of 4 × 10⁻⁷ seconds and employed an overset mesh. And these are actually overlapping cells, and they are connected by an interface. And what we have seen is that it actually maintained a good quality, grid quality during the mesh motion. It enables us to give higher rate of rotation than possible dynamic or deforming meshes. Boundary conditions, and the mesh motion was actually rotational speeds of 50 degrees per second, 200 degrees per second, and 475,000 degrees per second. The wedge angle was actually 15 degrees that I have shown. From there, we have started unsteady simulations till we get a transition from regular reflection to the Mach reflection region. The Mach number used was 4. This was a validation part, and we validated the fluent solution with object shock theory, 1D. And the difference was actually minimal, and we have validated for Mach number, static pressure, static temperature density, and the shock angle. And the difference was the results of both of them were almost in good agreement, and the difference is actually plotted here. And now this is the experimental Schlieren as well as the numerical Schlieren. The experiment was Ivanov's paper in 2001, where he investigated short reflection from a rotating wedge. And our numerical grid simulation almost shows an agreement with his work, where we have compared it for 50 degrees of rotation of the wedge for the same flow conditions. So the overset grid formulation was actually sufficient enough for predicting the complex shock system here. And coming to the results part, this is actually compared for a fixed wedge angle. And we have started it from a 15-degree wedge angle. And after simulations for 3 rotations per second, what I have compared, or what I have shown here is 50 degrees per second, 200 degrees per second, and 400 degrees per second, where we have compared it for a constant wedge angle. And of course, the time will be different. So it is seen that with increasing rotational speeds, the maximum height is actually getting reduced for a given wedge angle. And also, for higher rotational speeds, the shock transition to Mach reflection goes at a larger wedge angle. And if one wedge angle is fixed, it was seen that for slower rotational speeds, you have greater maximum height. And as the rotational speed increases, the maximum height was actually found to decrease, as I have plotted here. And now regarding the strength of the reflected shock. So what I have taken here is actually two cases of 75,000 degrees per second and 400 degrees per second. And the first condor is for 400 degrees per second, and the second condor is for 75,000 degrees per second. So for lower speed of 400 degrees per second, we can see a wedge pressure which is higher than that of a higher speed of 75,000 degrees per second. So there was actually a sudden jump in the static pressure, which shows that the wedge surface is having a reflected shock that is striking on it. The reflected shock is impinging on the wedge surface in both of the cases. That actually led to the rise in static pressure for these two cases. So when it strikes, the static pressure is found to have an increase. The first condor is for 400 degrees per second, and the second is for 75,000 degrees per second. And for the 75,000 degrees case, we can see that the rotation is happening more quickly. And this reflected shock striking the wedge was actually the cause for this increase in wedge pressure. And now when I thought about curving of the incident shock, when we have done it for 50 degrees per second, 200 degrees per second, 400 degrees per second, and for the highest case of 75,000 degrees per second, we can see that there was a curving of the incident shock that has happened for this high rotation speed. It might be actually attributed to the highest speed of the work. So I would like to define it as a king point that is actually transmitting downwards, or curving is actually transmitting downwards when a high speed of this 75,000 Ks was performed. So we are actually investigating on this, how the curvature of the incident shock is actually changing and the king point is getting transmitted downwards when we have a higher degree of rotation. So the incident shock is actually getting curved on the transition from the regular reflection to the Mach reflection. So these three cases are for the highest speed of 75,000 degrees per second. And this is actually 4 different cases for our 400 degrees per second case, where we have observed a regular reflection case first, then a Mach reflection, which is about to strike the wedge. Then the reflection point was found to be moving upstream. And finally, a Boshoff system has occurred, or a disgorged system has occurred. These cases were actually observed for all the cases, and it was more quick for the highest rotation speed case. So curvature effect, actually, we are actually studying more, and was actually not really observed for these speed ranges. And we would be taking more considerations on that further. And this is a plot that shows the maximum height versus time. And it is seen that the wedge rotational speed is found to greatly influence the maximum height. And for a slow rotation speed of 5 degrees per second, the growth of maximum height is actually gradual. And higher rotation speeds that I have shown, 550 degrees per second to the 200 case, and the 400 case is actually having a greater maximum height. So also for the slow rotation speed, the establishment of a Mach reflection is actually delayed. So it is actually observed that the height of maximum is greatly influenced by the rate of rotation of wedge. And how we predicted the maximum height is that we have drawn the sonic line and took the maximum of the y coordinate. That is how I have plotted the maximum height. And as already mentioned, it is seen that for slow rotation speeds, the Mach reflection was delayed. And for higher rotation speeds, the maximum growth is getting more rapid. And I have told that there was a von Neumann criteria for prediction of shock angle. And I have compared it for the 2D Euler CFD condition and the analytical von Neumann condition. So for the von Neumann condition of regular reflection to Mach reflection domain, the shock angle was about 33.44 degree. And for the present computational work that I have shown, I have calculated it to be what I've got is 31.65 degrees. This is done for the 400 degrees per second case. So there was actually a very little difference, and the difference between the analytic and the dynamic case was actually found to be 1.79 degrees for the 400 degrees per second case. So we expect a delayed transition. I mean, there is some difference of almost 1.79 degrees between the analytical as well as our work that we have done. Taken for a Mach number of 4 for the rotational speed of 400 degrees per second. And coming to the conclusions part, so we have dynamically investigated the transition of shock waves incident on a present reflecting plane. So as the wedge angle was changing, we got a change in the incident shock angle that brought about a regular reflection to Mach reflection transition. So we didn't want to contaminate the shock reflection point by viscous boundary layer. So the boundary condition used is inviscid, and we have not used the boundary layer concept. So offset mesh was employed, and the regular reflection to Mach reflection transition is actually influenced by the rate of rotation of wedge. So almost similar speeds of 200 degrees per second as well as 400 degrees per second has shown a similar trend. And for the slower rotational speed of 50 degrees per second, the establishment of MR is actually delayed. That is what I have shown. And high degrees of rotation of 75,000 degrees per second was not actually attempted before. So we have done that simulations. And currently we are doing an SHM on this case, where a periodic excitation to the leading edge of the wedge is actually given, and currently we are under investigation on that, and also how the curving of the curvature of the incident shock is happening for different rates of rotation. Currently it is under investigation for our case. These are the contents of my presentation, and these are the references that I have taken for my work.
Yeah, we have time for maybe 1 or 2 questions, quick ones.
Okay. What are the relevant scales in this problem? For low rotation speeds, the linear velocity of the tip of the wedge is usually one of the scales. In your results, you have made no attempt to non-dimensionalize any of the results. So how do we compare?
Yes, sir, we have not dimensionalized here. We have just shown the maximum height as actual. We have not done it.
Okay, so the low rotation speed results, is it going to be qualitatively similar to the high rotation speeds?
Yes, sir, I understand. We will do it. But this is actually just a plot that we have shown, randomly taken the values and presented here.
Okay, so
Normalization we are doing only.
you also have not simulated with a shorter wedge.
No, we will be doing that, sir. We will be doing it for a shorter reflecting surface. Yes,
Hi.
yes, sir.
Good work. We are actually attempting to do this experimentally.
Yes.
Anyways, did you look at the pressure downstream of the normal part of the shock?
No, we have not included the contours for pressure here.
Yeah, that's why I'm asking.
Yes, we have just maintained some basic results only.
Yeah, but if you look at the pressures, that will give more insights. I think like the pressures will not be equal, even though you are saying it's normal shock.
Okay.
The
I've
pressures
just
are not
shown
equal.
only that outfiles only, like pressure history plots on the wedge surface only.
Yeah, you will have the data. So
Yes, I
I'll be
have.
interested in looking at your data separately some other time, probably. Maybe online also. It's fine.
Okay, sir.
Okay.
One more quick question.
Good presentation.
Thank you.
Can you tell me about which axis is it rotating? The wedge.
There was a
Since-
center of rotation in that figure. The center of rotation was the bottom portion actually.
Is it an axisymmetric plot?
Asymmetric.
Axisymmetric.
Yes.
You are using an axisymmetric.
Symmetry boundary condition here.
Yeah.
Symmetry boundary condition here. This is the center of rotation.
And how did you calculate the von Neumann condition for particular rotational speed? Analytical value.
Yes.
Not aware of it. I mean, how did you calculate that?
There was a theoretical value. Then for the analytical value, I have plotted for two different lengths.
No,
Say
you have
x1.
given the von Neumann condition for 400 degrees per second.
Yes, yes.
Some 33 point something value. So
Yes.
how did you get it analytically?
I have taken for the 400 degrees per second, two different lengths, x1 and x2. Then by simple mathematical trigonometric calculations, saying when we get a triangle, we have shown the tangent, tan of that angle I have taken.
Steady value. No, that's not a steady value. I mean, 400 degrees per second. That's the
Yes.
value.
What he's asking is analytical value of Z. How did you calculate?
Yes,
that?
I have drawn a line, say 2 mm above the symmetry plane. And for those two lines, I have calculated the position locations of wet pressure, static pressure, say x1 and x2.
Okay. Maybe I'll talk
That
to
is
you
a-
later.
Okay, that is
There's
actually a
might be some
mathematical
point.
calculation. We will get a triangle, and I've just taken the tangent of that angle where I have calculated the.
Thank you.
Maybe just one comment. In that 75,000 RPM, no,
Yes.
you should not go to an angle where your incident shock, the reflected shock hits the wedge. That is a different problem.
The Bosch case.
No, that is a typical problem called unstart of the tunnel. So if your reflected wedge hits on the surface of the wedge, that's a different problem altogether. Because if you are trying to investigate the maximum height or the transition, then you should not go to that limit where the reflected shock hits the wedge.
Okay, sir.
You can stop before that.
Okay.
That is a different problem, and you will need a lot of other factors to be considering.
Okay, I will do that.
Yeah.
Just thank the speaker once more.
Thank you.
Okay, we'll move on to the last presentation for this session. It's on shock granular bed interaction and effects of compaction models. The authors are Annie Rose Elizabeth and Professor T. Jayachandran from IIT Madras. The speaker is Ms. Annie Rose Elizabeth.
Good morning, all. So today I will be talking about the shock granular bed interaction and effects of compaction models. So this work is done under the guidance of Professor T. Jayachandran. Okay, so coming to the outline of the work that I'll be presenting today. So basically, I'll give a basic introduction, the physics of the problem, objective, mathematical and numerical model, some preliminary results, and then conclusion. I'll be concluding the work. So the shock granular bed interaction, it has various applications wherein I would like to focus on where shock is transiting through energetic granular bed, where we can find some applications like in artillery systems, actuators, pyrotechnic igniters, pin pullers, etc. And if you see in any of these applications, the operation time is very short and there is a production of very high thrust values in a very short interval of time. So to model this numerically, the physics that we use is called granular propellant combustion. So moving on to the physics of the granular propellant combustion. So basically into the granular propellant bed, there will be hot ignition gases that is penetrating. And then through convective heating, the propellant reaches its ignition, and then in due process, there is compaction of the granular bed and rapid pressurization within the combustion chamber. At the same time, while this process is happening, the peak pressure, it propagates downwards the end of the combustion chamber, and there is flame spread within the granular propellant bed. And eventually what happens is there is a rapid depressurization of the chamber happening, mainly because of the rupture of the shear disc. For example, in case of pin pullers or actuators, or say due to the motion of the projectile in the case of artillery systems. So now to model this physics, it is if you look numerically, it is a very involved process and numerically cumbersome. So coming to the objective of the work, so basically first is to develop a 2D axisymmetric unsteady two-phase 6-equation code, and to carry out an end-to-end simulation for to predict the ignition transients in a pyrotechnic igniter. And for today's presentation, I would be presenting on the validation of the code that is developed and an initial study on shock granular bed and its effects with particle compaction. Now, to mathematically model granular propellant combustion, the model that we use is compressible multi-fluid formulation. So basically, if you look into granular propellant combustion, basically there are two phases that is involved. That is, there is a gaseous phase and there is a particle phase. And we assume that both phases are compressible, basically because at very high pressures, the particle phase, that is a solid phase, also becomes compressible. And wherein the model, it evolves with its own pressure, temperature, and velocity. So we have the Gowning equation in conservative form. Now, for easy explanation of the Gowning equation, I will be explaining in one dimension. Whereas if you get back to my full paper, the full 2D axisymmetric formulation is there. So if you look into the control volume, there is both gas phase and particle phase that is existing in the same control volume separately. And if you look now to mathematically solve this problem, we need to solve the density, velocity, temperature, and pressure for both gas phase and particle phase. And depending on the volume fraction that is occupied by each phase, the corresponding volume fractions. Then the bounding equations will be the total volume fraction of each phase is sum is 1. And since both the phases are compressible, ideal gas equation of state for gas and stiffened gas equation of state for a particle phase. So basically, if you see, there are 10 variables to be solved, and we have already 3 equations, and then we need 7 more equations to solve this problem. Now, coming to the various models that we have with us for compressible multi-fluid formulations, one is a 7-equation model. To that, if we assume that the pressures of each phases are equal, then we get a 6-equation model. To that, if we assume that if the velocity of each phases are equal, we get the 5-equation models. And to that, if we assume that the temperatures of each phases are equal, we get the 4-equation model. And for the present work, we will be using 6-equation model. Now coming to the Gowning equations in short. So that is basically we have the continuity, momentum, and energy equation for both gas phase and particle phase. And between the gas and particle, there is the drag terms and the interfacial pressure and velocity terms also coming. Now, basically, if you look 6-equation model, the both phases, the pressures are same. Now, when we have to account for compressibility also, first we find the equivalent pressure, and then for the which will be same as the gas phase pressure, and for the particle pressure, the beta, which is the compaction pressure, also comes into account. Then these are the interfacial velocity, pressure and velocities along with the speed of sound for each phase. Now, in the 7-equation model is hyperbolic in nature, whereas the 6-equation model is not hyperbolic in nature. So if the sigma term here, if it is greater than 1, or greater than or equal to 1, then only the equations becomes hyperbolic. And we as per from literature, the sigma value which we will be using is 2. Coming to the compaction models, there are various compaction models, the correlations given by various authors in literature. After comparing the various models, we have come to a conclusion of come down to three models and done a comparative study, wherein the first model is by Lopez et al., second Zen et al., and Sorrell et al. And then various analysis were carried out, wherein it was found that the model given by Sorrell et al. Is more predicting to the physics of the shock granular interaction. Now coming to the numerical model, that is for spatial discretization, unstructured finite volume method is used, whereas the flux is computed using second order HLLC scheme. And for temporal discretization, explicit scheme where classical 4-stage Runge-Kutta method is used. Now a small insight into the HLLC scheme for two-phase flows for compressible multifluid formulation. So here what we are using is where the three ways for average flow parameters are used, where we have the slowest velocity speed SL, and fastest running one SR, and the contact velocity contact speed as SM. And if you see now what happens is the contact velocity is taken as for the two phases, the mixture flow variables are used, and then the contact speed and corresponding SL and SR are also computed. Wherein if you see the first one, SL greater than 0, this section, wherein that is the flow is supersonic from left to right, and the last one, SR less than 0, whereas flow is supersonic from right to left. But the more for flux computation, if you look, it is more involved where we have to compute in the subsonic region. So where if you look, if you apply the Rankine-Huguenot condition here, if you see here, that is finally we need to compute the conserved variables in the subsonic region. Okay. Now coming here, this after all the derivations with the interactions between the two phases, the final contact speed with average flow properties are this with subsonic pressure, and this is how the SL and SR are computed. And after the for both the phases, after all the derivations and final form of the equations where the conserved variables in subsonic region for gas phase and particle phase is computed in this form. Now coming to the validation problem. So basically today we are talking about the shock interaction with a dense particle bed. Okay, so which is a similar process that we find in internal ballistics of the motor, except the burning part and ignition part if you look. So for the validation which we take is the rogue test case, wherein we have a shock tube of 3.6 meter long, 13 centimeter diameter. And we have a driven section of 800 mm, and then the rest is the driver section here and driven section here. Whereas from diaphragm at 1.15 meter, we have a 2 centimeter thick particle bed, which has a volume fraction of 0.65. So basically, once the shock is propagating, once the diaphragm is done, whether the test is whether the code that is developed could capture the wave travel. Okay, so now with the code that is developed for the study of shock granular bed interaction, for various Mach numbers and their corresponding pressure ratios to generate the shock, and for various particle volume fraction, particle diameters, and various compaction models, this is compared. And here there is it's 29.09. There is a typing mistake. Sorry for that. And with that, if we look, once the simulation is done, here we have a pressure time comparison, 11 centimeters ahead of the particle bed, if you look. So this is done where it is validated with the experimental data given by Rogue et al. And here, if you see, the first jump is where the incident shock is passing through the pressure measuring location. And the second jump is where the reflected shock from the granular bed, the shock is passing back. And if you look that with respect to the experimental data, almost a good match is observed. And for a higher MAC number, the same sets of studies were carried out. And it was observed that the effect of compaction comes into play with more when the MAC number is much higher. If the MAC number is lesser, the effect of compaction is comparatively lesser. And then again, with the values, the model 3 was selected. Yeah. And then if you see for various conditions for MAC 1.3, 1.6, and 1.95, the same pressures were computed and then simulated, and then these are the pressure histories for various cases for with and without compaction model, where there is a better prediction of the physics where the compaction model is also accounted for. Now, to look into more of the effect of compaction models, so we have to analyze the volume fraction within the particle bed region. So as these are at various times as the shock is passing, through the whole process, what is happening to the granular bed. So if you see for 1.3 MAC case, the effect on the case where without compaction, the bed is almost remaining as such. Whereas if you see with compaction model, the bed is actually getting compacted. Delta X overall, if you see, there is a compaction within the. Now, because this is a lower MAC, much effects are not seen for the compaction model. Now, when we come to a higher MAC, say 1.6, then what happens is this is not as per the physics actually. It should not go, the volume fraction should not go to this region. Whereas the one with the compaction model, where it sees there is a compaction of the bed and the volume fraction also is within the limits of, say, how in given space, how much a particle can compact or can be packed basically. And these are some of the preliminary some of the results. There are lots more, but because of the time, it is the results which I'm showing is restricting. The rest of the results are there in the paper. Coming to the conclusion, that is the unsteady two-phase 6-equation compressible multi-fluid formulation code is developed in 2D axisymmetric, and then it is being validated for the rogue test case, and it is observed that the code that is developed can capture the information of the wave travel, and various initial studies on the shock granular bed interaction with the with various comparison on the compaction model and effects were carried out. And the future scope of this work is to introduce burning to the particles and to carry out the end-to-end simulation of igniters or initiators or any of the applications which I have mentioned in the beginning. Thank you.
Thanks, Annie, for the nice presentation. We have time for a couple of questions.
Can you show me the validation with the rogue test case? Here, the third model. Okay, third model is closer to the rogue test case. Yeah, I was mistaken. Okay, that's why you selected the third model.
Yes.
Is there any other reason? I mean,
This plus
physical-
if you look into the compaction of, if you look into as the volume fraction for various test cases, when we looked into is closely into the particle bed region. Model 3 was predicting the physics actually, what we are expecting. No?
Yeah.
Yeah.
Thank you.
I have a couple of questions. So here you have written pressure versus time at 11 centimeter ahead.
Yes.
What does ahead mean? Is it upstream or downstream? Or?
Upstream here in this portion.
So it's in the gas that you are measuring the pressure.
Yes, since this is 6 equation, no? Equivalent pressure basically.
So where is the bed? Particle bed is okay. So the downstream of that is also gas only.
Gas
So
only.
you have a small bed. Okay.
Yes, only 2 centimeter thick.
Could we have a situation where the downstream is completely
Yes.
of particles?
Yes, we can.
And we can observe the wave passing through that.
Yes.
Okay, okay. So now I understand your, I was having a doubt with your, the compaction plots also. Now it's clear.
Okay.
Yeah. Okay, fine.
Yeah,
Thank
thank
you.
Yes.
Annie, can you go to slide 23 or 24?
23.
Here.
Ah.
The black curve I see, the red and green I don't see. Where is it?
Actually, the blue is overlapping the red and the green. I mean, if you actually, okay, if I zoom it, it could be seen blue is actually almost overlapping the red and the
Okay,
green.
in that case, why do you select model 3?
For higher MAC numbers, the prediction, if you see, the say model 1 and model 2, no? And if you look the pressures that we should attain, like P2 by P1 across it, it is comparatively lesser, I mean, under predicted.
But how do you know it's under prediction? I don't understand.
I mean, we had through equations generally, in case say MAC is passing, and then rough estimate of the P2 by P1 that we need. I mean, because now gas and particle phase, we don't have exact equation. So say we are taking only gas phase, and then in case if there is an incident shock and a reflected shock, what should be the P2 by P1? That's where rough estimate.
Okay, we will talk about it. I didn't
Okay.
understand.
I have one other basic question, I guess. So this approach, you are basically assuming same pressure for the particles and the gas.
Yes.
What is the interaction pressure in that case?
So basically, if you see there, that is there is something called nozzling effect. So since this particles are closely packed, it's a dense bed. What happens is, and the pressure is rising high. Problem is in between the particles. What happens is there is choking happening. So there's something called nozzling effect. To account for that, plus, I mean, it naturally occurs once this derivation is done, but it is to account into the nozzling effect when there is a choking between the particles.
That part is not resolved by your grid?
No, that is inherently, I mean, this already comes from, say, from single phase. When we derive these equations to two phase, this equations comes actually like one phase to two phase. So, and then that's significant.
Okay, maybe I'll talk
Yes.
to you separately on this. We can thank the speaker once more. If there are no other questions.
Thank you.
So with that, we come to the end of today's session. And we'll break for tea now, right?
Break for tea. I would like to request Professor T.M. Muruganandam to present a memento to our session chair, Professor Shantanu Ghosh. Next session will begin at 11 o'clock. So please come back a couple of minutes before that. Thank you.
Good morning, good afternoon, and good evening. I am Hidong Kim, the chairman of the 34th International Symposium on Shock Waves. It is a great honor to present a brief introduction to the 34th ISSW. Today, I will be talking about the symposium overview, committee, tentative program, key dates, the venue, special events, and accommodation. Finally, you can enjoy the video clip for the ISSW 2023. This is an overview of the 34th ISSW venue. We will be hosting the symposium at Daegu Expo, which is well equipped with advanced IT facilities, as well as modern convenience for international symposium. During the ISSW, 5G Wi-Fi network system is available for free use, and the participants can visit and enjoy a number of restaurants, cafeteria, and shops inside and around the venue. We are going to use Exco's third and fifth floors. The third floor has the grand ballroom for welcome session, exhibitions, and 16 oral presentation rooms. The fifth floor will be ready for opening ceremony, closing ceremony, and plenary lectures. And the Sky Garden will be also available for special events and other small group meetings. And we have a kite-wide exhibition space for poster presentations of more than 500 posters, books, and corporate communications as well. Key date for submission of abstract, full papers, and registration will be like this. We would like to start abstract submission as early as possible so that authors can have enough time to make the extract. This time we expect more than 500 abstracts. All the submitted paper will be reviewed by scientific review committee, which will be fixed in a couple of months. We'll make the book of abstract for symposium participants, and the full papers presented will be published in the proceedings shortly after the symposium. We have already fixed the International Advisory Committee and the local organizing committee, and now is contacting scientists and scholars over the world for the scientific review committee. This is the tentative program of the 34th ISSW. We'll have 3 plenary lectures, which will be delivered in the mornings of Monday, Wednesday, and Friday. The keynote lectures will be 2 parallel sessions in the afternoon every day, and the oral presentation in more than 12 parallel sessions, depending on the number of abstracts. As you can see here, we will make use of a smart registration system, which has been successfully applied to some previous international symposia. This is a real-time management system in which participants can check all the data regarding registration, abstract, hotels, and technical program on their own mobile and tablet PC. You see here an example of the smart registration system. The regular registration will include technical sessions, welcome session, coffee break, lunch, banquet, symposium tour, and the book of abstract. And the symposium proceeding will be available for additional registration. Daegu is quite convenient to access from your country. You can come to Daegu through Incheon International Airport and the Kinmye International Airport. Otherwise, you can directly come to Daegu International Airport, which has many flights from Asian countries. From the Incheon and Kinmye Airport, there are many traffic means to access Daegu, and the venue Exco is located in less than 15 minutes distance from Daegu Airport and train station. Prices in Daegu are much lower compared with other big cities, especially hotels and accommodations are relatively cheap. Transportation and social security in Daegu are quite good. Within 10 kilometers from the venue, more than 20 hotels and accommodation facilities are available. In addition, school dormitories and guest houses will be available for student participants at quite cheap rates. During the 34th ISSW, we will be learning more than 10 free shuttle buses for convenient transportations between hotels, the venue, and some major points in downtown. We will have a lot of lavish special events during the symposium. As in the previous symposia, we will have the welcome reception, banquet, opening ceremony, closing ceremony, student competition award, and some committee meetings. The symposium tour will be Gyeongju, which is one of Korea's most popular tourist attractions. In addition, we will have daily city tours and cultural tours for participants and spouse. During the symposium tours, you can enjoy ancient Korean relics as well as a variety of delicious food. In case of emergency situation like COVID-19, hospital ambulance and medical staff will be ready on site. We will have well-arranged quarantine system, and participants can take PCR test at the venue whenever they want. And also we will provide personal sanitation kit to all the participants. In addition, the LOC of the 34th ISSW will buy a medical insurance for participants. The homepage of the 34th ISSW will be opening just after this international colloquium of shockwave. We are going to design this website to provide various useful information for participants. Here you can see the cover page of ISSW 2023 homepage. We will do our very best to make the 34th ISSW a grand success. And we are looking forward to welcoming you all at Daegu Expo in 2023. Thank you very much. Good morning, good afternoon, and good evening. I am Hee-dong Kim, the chairman of the 34th International Symposium on Shock Waves. It is a great honor to present a brief introduction to the 34th ISSW. Today, I will be talking about the symposium overview, committee, tentative program, key date, the venue, special event, and accommodation. Finally, you can enjoy the video clip for the ISSW 2023. This is an overview of the 34th ISSW venue. We will be hosting the symposium at Daegu Expo, which is well equipped with advanced IT facilities, as well as modern convenience for international symposia. During the ISSW, 5G Wi-Fi network system is available for free use, and the participant can visit and enjoy a number of restaurants, cafeteria, and shops inside and around the venue. We are going to use Exco's third and fifth floors. The third floor has the grand volume for welcome session, exhibitions, and 16 oral presentation rooms. The fifth floor will be ready for opening ceremony, closing ceremony, and plenary lectures. And the Sky Garden will be also available for special events and other small group meetings. And we have a kite-wide exhibition space for poster presentations of more than 500 posters, books, and corporate communications as well. Key date for submission of abstract, full papers, and registration will be like this. We would like to start abstract submission as early as possible so that authors can have enough time to make the extract. This time we expect more than 500 abstracts. All the submitted paper will be reviewed by scientific review committee, which will be fixed in a couple of months. We'll make the book of abstract for symposium participants, and the full papers presented will be published in the proceedings shortly after the symposium. We have already fixed the International Advisory Committee and the local organizing committee, and now is contacting scientists and scholars over the world for the scientific review committee. This is the tentative program for the 34th ISSW. We will have 3 plenary lectures, which will be delivered in the mornings of Monday, Wednesday, and Friday. The keynote lectures will be 2 parallel sessions in the afternoon every day, and the oral presentation in more than 12 parallel sessions, depending on the number of abstracts. As you can see here, we will make use of a smart registration system, which has been successfully applied to some previous international. Check all the data regarding registration, abstract, hotels, and technical program on their own mobile and tablet PC. You see here an example.
Okay, if it is coming there, you can look at, yeah, fine. Okay. Next slide. That's okay. They changed already. They're changing it. I want to, there will be enough time on them. I will finish much earlier. My presentation is very short.
You can come to Daegu through Incheon International Airport and the Kinmye International Airport. Otherwise, you can directly come to Daegu International Airport, which has many flights from Asian countries. From the Incheon and Kinmye Airport, there are many traffic means to access Daegu, and the venue Exco is located in less than 15 minutes distance from Daegu Airport and train station. Prices in Daegu are much lower compared with other big cities, especially hotels and accommodations are relatively cheap. Transportation and social security in Daegu are quite good. Within 10 kilometers from the venue, more than 20 hotels and accommodation facilities are available. In addition, school dormitories and guest houses will be available for student participants at quite a cheap rates. During the 34th ISSW, we will be running more than 10 free shuttle buses for convenient transportations between hotels, the venue, and some major points in downtown. We will have a lot of lavish special events during the symposium. As in the previous symposia, we will have the welcome reception, banquet, opening ceremony, closing ceremony, student competition award, and some committee meetings. The symposium tour will be Gyeongju, which is one of Korea's most popular tourist attractions. In addition, we will have daily city tours and cultural tours for participants and spouses. During the symposium tours, you can enjoy ancient Korean relics as well as a variety of delicious food. In case of emergency situation like COVID-19, hospital ambulance and medical staff will be ready on site. We will have well-arranged quarantine system, and participants can take PCR test at the venue whenever they want. And also we will provide personal sanitation kit to all the participants. In addition, the LOC of the 34th ISSW will buy a medical insurance for participants. The homepage of the 34th ISSW will be opening just after this international colloquium of shockwaves. We are going to design this website to provide the various useful information for participants. Here you can see the cover page of ISSW 2023 homepage. We will do our very best to make the 34th ISSW a grand success And we are looking forward to welcoming you all at Daegu Expo in 2023. Thank you very much. Good morning, good afternoon, and good evening. I am Hidong Kim, the chairman of the 34th International Symposium on Shock Waves. It is a great honor to present a brief introduction to the 34th ISSW. Today, I will be talking about the symposium overview, committee, tentative program, key date, the venue, special event, and accommodation. Finally, you can enjoy the video clip for the ISSW 2023. This is an overview of the 34th ISSW venue. We will be hosting the symposium at Daegu Expo, which is well equipped with advanced IT facilities, as well as modern convenience for international symposia. During the ISSW, 5G Wi-Fi network system is available for free use, and the participant can visit and enjoy a number of restaurants, cafeteria, and shops inside and around the venue. We are going to use Exco's third and fifth floors. The third floor has the grand volume for welcome session, exhibitions, and 16 oral presentation rooms. The fifth floor will be ready for opening ceremony, closing ceremony, and plenary lectures. And the Sky Garden will be also available for special events and other small group meetings. And we have a kite-wide exhibition space for poster presentations of more than 500 posters, books, and corporate communications as well. Key date for submission of abstract, full papers, and registration will be like this. We would like to start abstract submission as early as possible so that authors can have enough time to make the extract. This time we expect more than 500 abstracts. All the submitted paper will be reviewed by scientific review committee, which will be fixed in a couple of months. We'll make the book of abstract for symposium participants, and the full papers presented will be published in the proceedings shortly April.
Good morning and welcome back, everyone. For this upcoming session, the session chair will be Dr. Arun Kumar Rajagopal from Mechanical Engineering Department of IIT Jodhpur. I request you to come on the dais. Thank you.
Morning and welcoming all to this session. So we have 5 papers in this session, and let us welcome the first presenter, which is Vaishak and Subramaniam Duhuri. The title is Shockwave Interactions in High-Speed Flows over a Spike Cylinder. Welcome.
Thank you. Hello, everyone. So this work is done at Indian Institute of Science in collaboration with Duri Subramaniam at Turbulent Shear Flow Physics and Engineering Laboratory. This work is done at Indian Institute of Science in collaboration with Duri Subramaniam at Turbulent Shear Flow Physics and Engineering Laboratory. So this work focus on the state transition over a spike cylinder. So this figure shows the sketch of a spike cylinder, and the flow state over this particular body is governed by L/D ratio. That's the single parameter or geometrical parameter that governs the flow state over this particular body. So what will happen? Say, if my L/D ratio is very small, like if the length of the spike is so small that it is lesser than the standoff distance of a shock wave, then the flow state will be steady. So there you can see a bow shock standing in front of that model. Now, if I increase the length of my spike or L/D ratio of my spike, what will happen is there will be another unsteady state called pulsation state. And if I increase my L/D ratio further, there is another state called oscillation state. And the pulsation state is a large amplitude oscillation state. Large amplitude means the oscillation amplitude is of the order of the spike length itself. Whereas in oscillation case, oscillation state is mostly governed by the breathing motion of a suppression bubble. So in this study, what we are focusing is the transition from one unsteady state to the another unsteady state, that is from pulsation to oscillation state. What is the trigger mechanism that transitions this state? So for that, we conducted a set of experiments, and the right side figure shows different, each data marker in that right side figure shows one experiment. So here we can see what we do is we will vary the L/D ratio, and when it passes the L/D ratio of 1.5, at that's the approximate location at which the transition happens. So we will look at the shock interaction trends when we approach from pulsation side to 1.5, and similarly we will look at the shock pattern trend when we approach the L/D ratio of 1.5 from the oscillation state also. So before going into that trend evaluation, I will introduce the pulsation state and oscillation state at say L/D equal to 1.25 and 1.75. This is a side note, and here in this you can see that at 1.5 you can see both oscillation state and pulsation state. So there is a hysteresis observation, which means when you approach the state transition from one side, it takes one path, and if you approach from oscillation state, it will take another path. So there is a hysteresis result in the literature. This you can keep it as a side note, and we will go to the actual result. So first we will look at the pulsation, how it is happening. So this is the pulsation state. So here we can see the separation region in front of the cylinder collapses completely, and then again refills it and again collapse it. That's the pulsation state of unsteadiness. So this shows one, this series of images shows one period of that pulsation. Here you can see that the separation shock in front of the, there is an interaction from the separation region, and there is a bow shock that is interacting. And from that interaction, you can expect a type 4 or type 3 shock interaction, and there will be a supersonic jet or shear layer that divert towards the spike axis, and that will feed the separation region. And once the separation region size increases, it will form a big bow shock standing in front of the spike cylinder, and the separation region collapses due to large opening at the sonic throat at the cylinder shoulder, and the cycle repeats. Similarly, oscillation means oscillation is a kind of a breathing motion where the separation region over the cylinder expands and contracts like this. And this unsteadiness is mostly governed by the unsteadiness of the shear layer that is developing over the separation region. Here you can see the oscillation state in one period. Here you can there will be a separate shear layer that is developing over the spike cylinder. And initially that shear layer is steady, and after a point, that particular point is marked as with a red cross here. After that, the shear layer becomes unsteady. And the entire oscillation state is governed by breathing motion of that separation region. So if you want to look at the transition triggering mechanism, here it is each image, we can see the trend towards oscillation. When we vary the LBD ratio and when we approach towards the oscillation state, that is close to L by D equal to 1.5. And this image represents the phase location where the bow shock is close to the cylinder phase. So here you can, it's marked there the interaction, that is from the spike cone, there is a shock wave that is interacting with the bow shock from the cylinder. So that interaction point actually moves away from the cylinder axis or the model axis. So that is one trend you can observe here, which means when you approach towards L by D equal to 1.5, the type 4 jet feeding the separation region decreases. Now, another phase is if you compare the situation where the separation point reaches the spike tip, when you compare the L by D ratio, you can see that again here also the interaction point moves away. The main notable parameter is the separation shock angle actually decreases with the increasing L by D ratio. So which means when you increase the L by D ratio, there is a chance that there is a possibility that the separation shock angle may not transfer into a detached bow shock. So that can be a possible mechanism that triggers the transition from pulsation to oscillation. Now, if you approach from the oscillation side, you can see that here again, the top row of images indicate the expanded case and the bottom row indicates the contracted case. So when you approach L by D equal to 1.5 from oscillation side, you can see that the separation shock angle also increases. And there is here also there is a possibility that the separation shock angle can go to a detached condition, and that can form a bow shock in front of the model, and then which will lead to escape of mass from the separation region due to the wide opening of the sonic throat over the cylinder shoulder. So the transition can be triggered or the mechanism that triggers the transition is the transformation of separation shock from a weak solution to a strong solution. I will take any question if there is any question.
Yeah, okay. Thanks, Vaishak. So any questions for the other? Okay, I have a couple of questions. This oscillation, the spike diameter is having some effect. The spike diameter is having some effect or not?
No, spike diameter can affect like say spike diameter. Now I have doubt. Sorry, I cannot answer that.
Okay, fine. Okay. So other thing is that this pulsation frequency. So this will depend upon what all parameters, the pulsation frequency.
Pulsation frequency again depends on parameter. Means you want some prediction.
Yeah. For example, let's say that may be having some dependence on the L/D ratio itself, right?
Yes, there
The
is a
frequency
dependence
rate.
on LBD.
Other than that, is there any geometrical parameters? For example, this diameter itself of the spike or something like that.
L by D is the single
Single parameter which
single
governs
parameter
all
that
this.
governs this particular.
Okay. Okay.
It
And-
will vary. The frequency will vary if you vary the L by D ratio.
Okay, so that is the only single parameter.
Then
which
Mach number
governs
may
this.
have a
Yeah, Mach number obviously. Okay.
In your experimental setup, was a spike being fixed, or is it like movable kind of mechanism?
The spike is fixed.
Okay, so if at all there is a mechanism where you can move the spike in the runtime,
correct.
Do you think there would be any difference in the transition that can happen? Or like whether the transition zone might widen or come down because of
See, in that scenario, ideally you have to do is the movement. You say you moved 1 mm, then you need to give some time to stabilize that flow. Then again 1 mm, give some time to stabilize the flow, like that. Otherwise, the problem is again it will be unsteady problem. If you move at a faster rate, then it is an unsteady problem. Then the situation may be slightly different.
In separation region, the bubble is not visible. You have to take a little bit closer focal length photographs.
I cannot hear. Repeat.
Yes, in separation region.
In separation region,
the bubble is not visible.
Bubble is not visible. Yes.
So to take finer pictures or
The bubble size is identified by the boundary. That is, there is a shear. So if you look here, there is a dark region, right? That is marked as shear layer. That's the boundary of that bubble, actually.
Yeah, so this over here on this side. Yeah, so this pulsation, it's an age-old problem. I mean, yeah. Yeah, pulsation is an age-old problem. I mean, starting from 1950s, people are working on this. And just some comments on it. It's not just the Mach number, Reynolds number, also your free stream velocity. Enthalpy also comes into picture. And he was asking a question, if you are going to change the spike length, will it change? In any case, the flow field is unsteady, right? You said you have to wait for some time. So that is a transition time for a cyclic process to set in. So I meant he asked if there will be any effect on changing this L by D, because in your conclusion, you have just mentioned at 1.5. So that is not a fixed number, right? It can be somewhere between 1.4 to 1.8 also in some cases. So you cannot fix on that number. Any comments on that? Or you're just working on only this 1.5?
The value of 1.5, right?
Yeah.
The value of 1.5 can slightly vary. Say if the spike tip, there is a angle, right? There is spike tip have an angle. So in this case, it is 10 degree. If somebody chooses 15 degree or 20 degree, that can slightly vary the transition value of 1.5. Or if the Mach number is slightly different or Reynolds number is different, it can slightly vary that value. So
Yeah,
1.5 is not a magical number. It's about the transition triggering mechanism. What is the possible mechanism?
No, even that 1.5, we cannot concretely say, right, this is the transition, this is the number at which things can change. Like you said, depends upon Mach number, Reynolds number, and the geometry as well.
1.5 is the approximate transition location.
You can say it's a range. That around that
It's
range.
always a range. It depends on slightly on a Mach number also. And if you consider the spike tip case also, it can be slightly vary.
Yeah.
Just not a question, actually, just a follow-up to Arun's earlier question on the spike diameter. So unless the spike diameter is very large, it will not have a order 1 effect on what you see here. So in literature, you'll see spikes are at least an order of magnitude lesser in diameter than the cylinder. So any small variation in that diameter will not affect the global flow. It might slightly move the numbers around, and of course the spike tip and so on. But the overall physics remains unchanged unless your spike becomes significant. Then it's like a forward-facing step problem. Okay.
So if there are no more questions, let us thank the presenter once again. So the next presentation is by Sushmita Janagiram and Dr. Subramaniam Duveri. The title is Experimental Investigation of RR-MR Transition in Curved Shock Wave Reflections.
Good morning, everyone. I'm Sushmita. I'm a PhD student at IISc, and Professor Subramaniam Duveri is my thesis advisor. And my talk is going to be about the experimental investigation of RR-MR transition in curved shock wave reflections. So why do we need to study the transition between regular reflection and Mach reflection configuration? And why use a curved shock wave generator? Here's a schematic of a hypersonic or a supersonic intake. This is the most commonly employed compression system in a ramjet or a scramjet engine. And although in the early days, the transition between regular reflection and Mach reflection configuration, these studies were motivated by academic interest. In recent years, the geometries explored in these studies have close resemblance to the geometries in hypersonic and supersonic intakes. And in comparison to a planar ramp, a curved compression ramp also employs isentropic compression waves for compression, and thereby resulting in better pressure recovery, better efficiency, and shorter length in comparison with an intake that would employ a purely planar ramp. Although this is the broader motivation, the current study is more of a fundamental study that focuses on reflection of curved shock on a flat plate. Here's a broad outline of my talk. I'll be discussing about the design of the curved ramp used in my experiments. I'll be going over the experimental setup, and then we move on to results and discussion. We all know that supersonic flow past a planar ramp would result in an oblique shock. Let's see what happens when we replace this planar ramp with a curved ramp. Curved compression ramp used in the current study comprises of three major sections. Closer to the leading edge, you have a very short planar section with a leading edge initial angle theta I equal to 4 degrees, which produces a very weak oblique shock. That's followed by a curved surface, and downstream to the curved surface, you have a planar surface tangential to the curved surface. The compression waves from the curved surface interact with the leading edge shock wave, gradually strengthening it and causing it to curve, resulting in the formation of a curved shock. Curved surface, the contour of the curved surface was designed such that the pressure gradient along the curved surface is constant in the x direction. Meaning if I choose an x location along the curved surface, and if I were to determine the local angle of inclination, so from my design constraints, I know the static pressure at that particular location, and I can estimate the Mach number at that particular location using isentropic relations. And then I use Prandtl-Meyer relations for estimating the local angle of inclination. The curved compression ramp used in the current study was designed such that a free stream Mach number of 6 would get compressed to Mach number of 4 downstream to the curved surface. The leading edge initial angle is equal to 4 degrees, and this particular curved compression ramp in a free stream Mach number of 6 would produce an overall deflection angle of 19.05 degrees at zero angle of attack. These experiments were conducted in the Rodam Narasimha hypersonic wind tunnel facility at ISC. So this is a blow down to vacuum type wind tunnel, and it's an enclosed pre-jet facility with nozzle exit diameter of 0.5 meters. And for every blowdown, you get a runtime of 5.8 seconds. And to the left of this figure, you have the pressure tanks, followed by the pebble bed heater. Downstream to the pebble bed heater, you have the settling chamber, followed by the CD nozzle, and then you have the test section. Downstream to the test section, you have the diffuser, followed by the vacuum tanks. Here are the flow conditions corresponding to the experimental study that was carried out. So all of these experiments were conducted at a free stream Mach number of 6. The unit Reynolds number was of the order of 10 million per meter. The stagnation pressure is equal to 11.4 bar, and the stagnation temperature is equal to 457 Kelvin. In this experiment, we place a flat plate adjacent to the curved compression ramp and vary the angle of attack of the curved ramp during the blowdown. All of the angles in this study are expressed in terms of the parameter theta d. Theta d is the overall flow deflection angle produced by the curved compression ramp, and theta d is equal to delta plus alpha. Delta is the flow deflection produced by the ramp at zero angle of attack, and alpha is equal to angle of attack of the ramp. Here's an image of the model mounted in the test section. The curved ramp was sting mounted to a sector whose rotating mechanism was controlled using hydraulics, and the flat plate was strut mounted. And in the span-wise direction, the width of the flat plate is equal to 16 centimeters. The width of the ramp is equal to 10 centimeters, and the length of the ramp is equal to 10 centimeters. Standard Z-type Schlerin setup was used for flow visualization and was captured using a high-speed camera. The high-powered pulsed diode laser was used as a light source. The angle of attack of the ramp was varied at a rate of 0.15 radians per second, which is of the order of 8 to 9 degrees per second. So we can assume the flow to be quasi-steady because the time scales associated with the shock interactions is much lower in comparison with the time scale associated with this angle of attack variation. Now let's see what happens when we increase the angle of attack of the ramp. So you can see the incident shock and the separation shock interacting to form a regular reflection. And as we increase the angle of attack of the ramp, max stem appears and the max stem height gradually increases with increase in angle of attack of the ramp. Let's take a closer look at the flow features associated with the Mach reflection configuration. So you have incident shock and separation shock interacting to form the Mach reflection. The dark region here corresponds to the shear layer. Downstream to the shear layer, you have the separation bubble followed by the reattachment shock. Now let's see what happens when you decrease the angle of attack of the ramp. We can see that the max stem height decreases with decrease in angle of attack of the ramp, and it gradually diminishes, and Mach reflection transitions to regular reflection. And it was observed that MR to RR transition occurred at pretty much the same angle as RR to MR transition, and which is equal to theta d equals 44.3 degrees. And I'd like to point out that the increasing angle of attack and decreasing angle of attack correspond to two different blowdowns. Now let's take a closer look at the regular reflection configuration. Once again, the incident shock and the separation shock interact to form the regular reflection configuration. And in this case, the separation shock angle is much lower in comparison with the separation shock angle that we observed for MAC reflection configuration. And the separation bubble height is also much lower in comparison with what we observed for MAC reflection configuration. Okay, now we increase the spacing between the ramp and the flat plate and repeat these experiments. Let's see what happens when we increase the angle of attack of the ramp. Once again, we see that regular reflection transitions to MAC reflection configuration, but this time it's happening at a much higher angle of attack in comparison with the previous case. And now when we decrease the angle of attack of the ramp, the maximum height again diminishes and MAC reflection transitions to regular reflection. And even for this case, the MR to RR transition and RR to MR transition happened at pretty much the same angle, which suggests the absence of hysteresis associated with RR-MR transition. So we saw that the RR to MR and MR to RR transition for reflection of a curved shock on a flat plate happened at pretty much the same angle for both the cases. And it happened at a much lower, the transition happened at a much lower angle for the case with a smaller distance between the ramp and the flat plate, and which is equal to 44.4 degrees. And it happened at a much higher flow deflection angle for the case with a larger separation between the ramp and the plate, which is equal to 52.0 degrees. The results corresponding to the second case that has been reported in the full paper. Similar study carried out in literature for a planar ramp at max 6. The transition angle was reported to be 37.8 degrees. And the current study, the transition angle that we obtained with the current with the design curved compression ramp design that was considered for the current study, the transition happened at a much higher angle, which suggests that if such a design were to be incorporated into a hypersonic intake or a supersonic intake, into a hypersonic intake, you would get a much broader window of operation in terms of angle of attack of the intake. And hysteresis that is typically observed in RR-MR transition in an inviscid scenario was absent in this case. This could be because of propagation of acoustic waves in the boundary layer. It was observed that the transition point is sensitive to the distance between the ramp and the plate, meaning as you increase the distance between the flat plate and the ramp, the transition from RR to MR was getting delayed. It's also sensitive to surface roughness of the plate. So higher the surface roughness of the plate, higher is your transition angle at which RR-MR transition happens.
Questions?
Susmita, nice work.
Thank you.
But couple of things. What do you mean by theta D?
Theta D is the overall flow deflection angle produced by the ramp.
So if it is a planar ramp, then the transition angle is 37.82.
Yeah.
Is what you told, right? And
Yeah.
here it is going up to 52.5, no?
Yeah. So theta D. So if I were to use this figure, theta D is basically the angle through which the flow gets deflected at this point. So downstream to the curved surface, you have planar surface, right? All of the streamlines are getting deflected through the same angle. And this is the last characteristic, last left characteristic line from the curved surface. And downstream to this, all of the streamlines would be aligned, would be parallel.
Okay.
Yeah.
Oh, okay.
Yeah.
Fine. That is typically the wedge angle that we follow for the plane ram case, right?
Yeah.
Actually, so if we investigate the curve shock reflection,
Huh.
there is another parameter which decides the transition, which is the shock angle at the interaction point. You have a curvature now.
Yeah.
The shock wave. So the shock is curved all the way up to the interaction point, no? The shock is curved all the way up to the interaction point. So the slope of that shock curve at the interaction point decides the transition typically. It is not the theta d. Of course, theta d will have a relation between the transition or influence of transition point, but mostly you have to measure the angle of the curve shock curve at the interaction point and correlate that with the planar shock case.
But sir, it's also not that straightforward, because if you look at all the streamlines in the cross stream direction, for a planar ramp, they have the same Mach number, but for a curved ramp in the cross stream direction, the Mach number varies. Because closer,
look at a particular point where the interaction happens between the two shock waves. The interaction point decides the streamline angle at that interaction point decides the transition.
Okay.
So that is what you have to measure and plot against the correlate with the planar ramp case. What I'm trying to say is your shock will be curved.
Right.
So it will have a varying curvature right from the top of the wedge to the interaction point.
Yes.
So the angle of that shock with the interaction point decides the transition.
Okay.
That you have to measure and correlate with the planar case. That is one thing. Second thing, what is your Mach number?
Free-stream Mach number is 6.
6, right?
Yeah.
Then I am little surprised why you have not observed a
detachment.
Hysteresis. Yeah, no, hysteresis here.
Hysteresis with RR-MR transition. We didn't observe hysteresis.
So is this a closed test section or open test section?
This is a free jet
facility. So
yeah.
then I was surprised not to see this particular hysteresis.
So related to your question, so how was this experiments carried out? I mean, you said you had test time of 5 seconds, right?
Yeah.
So it's like you did this RR to MR transition and MR to RR transition within this 5 seconds?
No. So RR to MR and MR to RR correspond to two different blowdowns, two separate blowdowns.
Then
no, even if it is two separate blowdowns, we were coming from RR to MR to RR case. So hysteresis, yeah, if we had to observe a hysteresis, we would have been able to capture using the within the experimental conditions that we carried out this work in. But then the point is, in literature, you mostly use symmetric wedges, right?
Doesn't make a difference. Symmetric or asymmetric, you should see a hysteresis at Mach number 6. This is a planar shock case, right? Means 2D flow field. Right?
2D, yeah. So even in literature, for a planar shock, hysteresis was not observed in the papers that I referred to for reflection of shock on a flat plate.
This is not a flat plate, right?
Yeah, flat plate.
So there will be a shock coming from the bottom, right? And there will be a shock coming from the top. So it's interaction of two shocks, right?
Yeah.
So then either it is symmetric or asymmetric, you will have a hysteresis forming there. Typically asymmetric problem, right?
So, but we repeated this experiment multiple times with multiple cases. In all of the cases, with the same geometric conditions and different geometric conditions, hysteresis was absent.
And that's something new. That then you should investigate that. Yes. I don't know.
That's
I don't know whether that
paper
separation
by
region has something to do with the
Zoe.
hysteresis, because anyway it is interaction of two
This
shock
is the
waves, right?
paper.
And you
Right.
expect to have a very large dual domain for the Mach 6 flow. That is what I was surprised why you are not able to see that. No, that separation bubble there, that is all the more reason that you should get hysteresis. To release the pressure. Yes, to relax it. No, it's one is coming up and one is going down. You have the bubble that is staying there. So the bubble has typically, I don't see why it is. Yeah, that they are all fixed, right? They are not.
You see the video, it's changed, right? The bubble, so it's a couple problem. See, as the ramp angle is being changed, the bubble size, angle, and the magnitude of unstrain is some metric, right? They're all function of that angle. So it's a couple problem.
In the viscous calculations, there has been hysteresis of the similar problems, not just the Euler computation. Even the Navier-Stokes computation have shown you have hysteresis. So I think this should have.
Okay, then my guess is, I'm not familiar with that particular piece of work, then my guess is there's probably a Reynolds number dependency on the problem. If you're seeing hysteresis with viscosity in the study that you're referring to and we don't observe it, one plausibility is that Reynolds number plays.
This is a blowdown tunnel.
This is a blowdown.
What is the turbulence level?
That's a good question. So that's a separate project that we are working on. So I can tell you it is comparable to the Ludwig tube that they have at DLR Braunschweig. I don't remember the numbers off the top of my head.
It's silent is what you're saying.
It's not silent. Neither of those two tunnels are silent. This is not a quiet facility.
Other than turbulence, I don't see why it shouldn't be.
No, that is different. So in a hypersonic wind tunnel, you have very strong free stream fluctuations, which are mostly acoustic pressure fluctuations. So it is, so the free stream fluctuations on a high speed wind tunnel in general are dominated by acoustic radiation from the turbulent boundary layers on the nozzle wall. So it's different. I think what you have in mind is turbulence getting quelled because of this is a different mechanism altogether, high speed wind tunnels.
Okay, anyways, Smith, the nice slides.
Is it possible that there is actually too much contraction, and because of that there is some other, it's like unstart of the intake taking place inside, and that's causing
within this, you mean within this setup? Yeah, for some angles we did observe that unstart happening, and that increased the blockage and the entire tunnel ended up unstarting for very high angle of attack. So depending on that, so we carefully chose the angle of attack range depending on that constraint. So there was.
So happened that you have chosen such that the unstart is not complete, it's just partial, sitting here and not going out fully.
Yeah,
Is that the case? In which case it won't match the other hysteresis effects and all will be overridden by this unstart effect. That effect will
the mechanism is the same.
Sorry to interrupt. We are running out of time, so maybe we can cut short and have the discussion outside.
Yeah, just one more point towards the larger angles. Your
Okay.
shock is actually having ripples, the bottom shock.
This one?
It is having a three-dimensional structure. Yeah, the bottom one. When your
Right.
angles of the wedge are larger, it's having, yeah, you can see it has, I have seen
Right.
three-dimensional structures develop.
Yes. You mean near the impingement point?
Yeah, not there, just before that, you actually get some, to take a closer look. In one of your slides, I was able to visualize it.
Okay.
You know, it sort of develops into, it's actually three-dimensional, but since it's line of sight integrated.
Right, right,
You
right.
get, some strands which come up and sort of.
Okay,
do this.
because the width of the plate is also not exactly equal to width of the ramp. That's 16 centimeters and 6 centimeters offset.
Okay. So let us thank Sushmita. Thanks. So the next presentation is by Vinod Eldo Baby and Vinod P. and Dr. G. Rajesh. The title is Analytical and Computational Study of Regular Reflection to Mac Reflection Transition in Short Wedges.
Good morning to you all. My name is Vinod Eldo Baby. I'm a research scholar at working with Professor G. Rajesh, Aerospace Department, IIT Madras. Today, I would like to present my studies on short wedges. The title is Analytical and Computational Study of Regular Reflection to Mac Reflection, Transition on Short Wedges. These are the contents: introduction, literature review, aim of the study, methodology, results and discussion, conclusion, and references. So we all know that when a supersonic flow passes over a double wedge, the flow turns to itself, which results in a shock reflection, which could be either a Mach reflection or a regular reflection, depending upon the flow parameter values. So there is a minimum and maximum HT associated with any Mach reflection. The HT value is the distance from the trailing edge point to the central line of symmetry. And the HT min is the minimum possible distance to form a MR, where the reflected shock just passes through the trailing edge point, whereas the maximum HT max is the maximum possible distance to form a MR without the expansion fan interacting with the incident shock. Now, all the possible shock reflections in between HT min and HT max are extensively studied. And basically, the HT value depends on the wedge length W and the centerline distance H as shown in this slide. So based on this WYH value, we can categorize wedges into long wedge and a short wedge. A long wedge is a wedge whose WH ratio is such that the expansion fan does not interact with the incident shock. Whereas in a short wedge, the WH ratio is such that the expansion fan interacts with the incident shock, it curves the incident shock, and the shock angle reduces as it reaches the central line of symmetry. Now, the extent of interaction is another thing, which depends on the curvature, the shock curvature. And always the extent of interaction always in turn depends on the WH value. Now, this is a very interesting phenomenon since what could be possibly a Mach reflection can be transformed into a regular reflection because of the lessening of the shock angle. Now, one of the initial works in the expansion fan shock wave interaction in wedge flows was done by Lee and Bendo in 1996. They developed an analytical model to approximate, to predict the shock curvature, and they approximated the shock curvature as a second order polynomial. But they did not consider the aspect of a prolonged interaction of the expansion wave of the same family. Lara Nell and Berix-Hughes in 2017 experimentally and numerically validated Lee-Bento model, but they found that the model is invalid for the analysis of a full interaction and to predict the extent of the shock curvature. R. Hillier, 2006, did a numerical study of the shock wave expansion wave interaction with the opposite family. His specific aim was to study the perturbed reflected shock wave from the solid surface. The interesting thing is, he noticed that the scale of Mach reflection can be altered by the deliberate generation of an expansion wave. Now, this might be used as a control mechanism for the maximum growth. So except for this paper, the analytical models developed till now mostly consider the modeling of maximum and did not consider the expansion fan interaction with the incident shock and the Mach triple point. So the aim of the study is to develop an analytical model to predict the shock curvature of the incident shock due to the prolonged interaction of the expansion wave of the same family. Second one is to validate the analytical model with an in-house developed envisaged 2D structured finite volume solver with a fifth order Vino scheme. The third one is to construct new transition lines for all possible shock reflections that may happen in short wedges. So the methodology involves developing the analytical model and validating it with CFD results. So model assumptions are the flow is steady, compressible, envisaged, 2D, and isentropic and rotational. Since the flow is rotational just after the curve shock, the entropy is constant only along the streamlines, the reflection is symmetrical. So what you see here is a schematic of the analytical model. The idea is to find out the discrete points along the shock curvature, and the method uses method of characteristics. So the solution algorithm is initiated by giving a small increment flow turn angle, say 0.03 degrees from point D. So you can find the flow property values using Prandtl mirror relations in plot at the point D. And once you have the flow property values at point D, the flow property values at interior point B1 can be solved by solving the characteristic curves from D and B. So the next solution point, as you see here, is a point on the shock. So there you have to find it iteratively. So we assume a pressure ratio across the shock first, then we'll solve for the flow property values after the shock. Now this flow property values must satisfy the compatibility equations. The compatibility equations, which is coming from the interior point B1. So once you have a match with the incoming Mach number and the pressure ratio across the shock angle can be calculated. So if I go back to the previous slide, this is for finding out the next shock point in the shock curvature. This is exactly what you do. You give another flow turn angle increment, and you calculate the interior points and eventually calculate the shock curvature point. So there are basically two algorithms: one to calculate the interior point in the flow field, and the other one to find out the shock point in the shock curvature. These are the results. This is one of the shock curvature captured by the analytical model. The flow parameter values are m equal to 3, wedge angle 30 degrees, W by H equals 0.33. Now we have the computational results for the same flow configuration, m equal to 3, wedge angle 30 degrees. In order to validate or compare both the analytic results and CFD results, we superimpose both the images, and we have a fairly good match of these results. The red line indicates actually the results from the analytical model, and the black line is beneath it from the CFD model. Now, to validate for the other flow parameter, the flow parameter values are changed for different W by H ratios, and the reflection point is calculated, and non-dimensionally using the centerline distance H, R by H is calculated, and for different WH ratios. This is the validation curve for one such WH ratio, 0.33, for different wedge angles. And the error percentage is less than 2%. So the analytical model matches with the CFD fairly accurately. So this, coming back to this slide, this is a very interesting result that you see here. Suppose we have, instead of using a short wedge like this, if we use a long wedge where the expansion fan doesn't interact with the incident shock, for this Mach number and the wedge angle 30 degrees, it would have been a Mach reflection. Now, instead of using a long wedge, when we use a short wedge, what happened? The expansion fan interacted with the incident shock and it turned into a regular reflection. So in a way, you can say that you have delayed the Mach reflection. Okay. So suppose if it would have happened at theta is 30 degrees. Now, by using a short wedge, you have delayed the Mach reflection. Now the Mach reflection happens at a larger theta, larger than theta equals 30 degrees. So to find out exactly where the transition happens, you have to draw transition lines. So this is the shift in the transition lines. I'll explain what is a theta d curve and the shock detachment curve, and then I'll go to the blue line. The theta d curve is a well-known curve. It's a curve based on the detachment criteria. The regions above the theta d curve shows the Mach reflection point, and regions below the theta d curve is a regular reflection point. For instance, if you take a point A where the Mach number is 3 and wedge angle is 20 degrees, it's below theta d, it results in a regular reflection. Whereas in a point C, where the Mach number is 3 and the wedge angle is 30 degrees, it is above the theta d curve and results in a Mach reflection. The shock detachment curve. The shock detachment curve is, it shows that whether the shock is attached to the wedge or detached to the wedge. For example, if you take a point here, Mach number 3 and theta is equal to 40 degrees, it will form a bow shock in front of the wedge. It will not be attached to this. So any region below the shock detachment curve will give you an attached shock, whether regular or Mach reflection. Now, moving on to this blue line here. So one point to be noted is that the theta d curve is constructed based on long wedges, or we can say that when we construct the theta d curve, we didn't consider that expansion fan is interacting with the incident shock. So what happens when you instead of using a long wedge, what happens when you use a short wedge? In this case, we have used a short wedge for WIH is equal to 0.5. So what happens is, as we saw earlier, theta wedge shifts upwards and the theta d curve shifts upwards. So for a WIH ratio 0.5, the curve actually follows the old theta d curve up to this point of shift, and then the shift happens. Now, this is very interesting. It seems like even if you use a short wedge, it doesn't mean that it starts interacting straight away. It follows the same old curve up to a point, and from that point where the interaction starts, that shift happens. Now, the new transition line follows the blue line, not the black line. It comes up to the point of shift and then follows the blue line. Now, what is the significance of this? If you observe closely the point B here, point B was actually above the theta d curve, and where the Mach number is 3 and theta is 25 degrees. For normal case, if you use a long wedge, it would give you a Mach reflection. Whereas if you use a short wedge instead of a long wedge, it is below the blue line and gives a regular reflection now. Now this is validated using CFD results. If you can see, I'll go to the point A first, which is below the theta d curve here, below the blue line also. It will give a regular reflection as shown here. It's a regular reflection. Point B is where we are using a short wedge here. If you can notice, the expansion fan is interacting with the incident shift. So when the point B is m equal to 3, theta is equal to 25 degrees, this one, that results in a regular reflection because it is under the blue line. Now, point C is actually where the point is above the blue line, or the Mach number is 3 and edge angle is 30 degrees, and results in a Mach reflection. Now, this is interesting. This is where the case where we use a long wedge. You can see that the expansion fan doesn't interact with the incident shock. And what happens if Mach is equal to 3 and theta is equal to 25 degrees, you get a Mach reflection. Now, instead of using this long wedge, if you use a short wedge, this is the case. If you use a short wedge, Mach equals 3, theta is equal to 25 degrees, you get a regular reflection. So now, if I could explain this slide a little more bigger, the question is, what happens if you use a different WH ratio? Let's say lesser than 0.5, greater than 0.5. So obviously, the extent of interaction is more. So the shift in Mach reflection always depend on the extent of the expansion fan interaction, and the extent of expansion fan interaction in turn depends on the WH ratio. So if you use a WH ratio less than 0.5, the shift happens at an earlier stage at a lesser Mach number. And if you use a WH ratio greater than 0.5, the shift happens at a later stage. So we have drawn the transition lines for different WH ratios. This is the same old figure. We have the theta d curve in the black line. Dashed line indicates the shock detachment curve. And we have drawn the transition lines ranging from a very small WH ratio 0.05 to 0.8. So what is the importance of this plot here? So the importance is we can actually choose the detachment point. Okay, for example, if you're operating, say, at a Mach number ranging from 2.5 to 3.5 in this region where the theta wedge is 25 degrees, I can easily make out that it is above the theta d curve, and it should give a Mach reflection for a long wedge. But if you choose this transition line, or that is WH is equal to 0.33, if you choose a short wedge of 0.33, you can make sure that throughout your Mach operating range, you will not get a Mach reflection. It will be always a regular reflection. So the significance of this plot is that we can choose a W by H ratio to achieve the required delay in Mach reflection. So that is the significance of this plot. So conclusion is the change in transition line for detachment criteria sorry, in steady flow with symmetrical short wedges has been investigated. The effect of expansion fan interaction on incident shock wave is found to curve the incident shock. The analytical model developed to predict the curved shock because fairly matches the computational results. The transition lines plotted for different WH ratios from 0.05 to 0.8 shows that the shift in the transition line depends on the extent of interaction. The plot is useful in finding the detachment criteria for any Mach number between 1 and 5 for a particular WH ratio. Moreover, we can delay or rather choose a detachment point for a particular Mach number by selecting the suitable WH ratio from the transition line plots. These are the references. Thank you.
Thanks, Vinod, for the presentation. Any questions? I have a question. In that, you go back. Yeah, this curve is okay. So no, the previous one. No, next one. This one. Next, in which you have plotted that parametric thing, that variation with the W by H.
Yeah. For one W by H.
No, different W by H. You plotted that parametric.
This one.
This one. So the detached shock wave angle is also influenced. Like the top hatched line, right? That is a detached shock wave, right?
That is a shock detachment.
So that is also changing with respect to this expansion fan interaction. For example, if you take Mach number 3, the blue line, which is having that short wedge, right? So the detachment is happening at, let's say, around 33 or something like that. Okay. But the other case, the detachment is happening at a much larger angle, right?
Other case in the sense?
In the sense that the longer wedge, the hatched line is a long wedge, right? That dashed line.
No, the hatched line is actually the shock detachment. The dashed lines, right?
There is a detached shock detached.
Shock is
condition.
detached. It forms a bow
Yeah,
shock.
yeah. So
it forms a bow shock.
bow shock, yeah. So the bow shock formation is also affected by the expansion fan interaction, right?
No, actually, the bow shock actually depends on the theta max angle, right?
But for this curve, if you see that blue curve, that okay, fine.
Are you just confused with the
Yeah,
theta?
okay, fine. I just got confused.
The black line is the theta
Fine,
D curve.
fine. Okay,
Detachment
okay,
curve
fine,
is this
fine,
one.
fine. I was confused.
Hi, Vinod.
Yes.
Good work. The curves I've never seen before.
Yeah.
When we are looking at a particular Mach number,
Okay.
and then we are saying that we are just going above this line, right? As of now. So I am saying that there is an expansion coming.
Okay.
And because of that, the normal shock should have different pressure downstream. Is that happening?
For Mach reflection area.
In the Mach reflection cases,
Okay.
are you having just simply when the Mach stem height is decreasing?
Yeah, I can.
It's supposed to become. It's supposed to be very high, and then it's going to go more downstream and diminish, right? That's what's supposed to happen in there. That's what is your curve, right?
Yeah, actually, the maximum I have in the analytical model is exclusively for regular capturing the regular reflection. The maximum prediction is going to be very tricky one because it's a complicated flow field. So the analytical model only predicts this cycle.
No, I'm asking from your simulations, CFD simulations also.
Yeah.
You can tell me,
Yeah.
like the pressure downstream of the normal shock.
Pressure downstream of the normal shock, does it change? That's what you're
Does
asking.
it change? Is the
What I experienced, what I observed in the simulations is this maximum height has a direct influence on the extent of interaction. Actually, that is obvious now. So I haven't measured the pressure as you asked, but I think definitely the pressure will change.
Yeah, basically my rationale is basically that expansion waves that are coming here go hit the subsonic portion.
Yeah.
And they run against the flow and go and influence the shock. So it's supposed to be a weaker shock.
Yeah.
That's the
True.
expectation. That is why I'm asking this question.
That is in the pipeline. We are going to work on that.
Okay. Okay, good one. No, expansion waves run very fast in
The pressure
subsonic conditions.
changes.
See,
That is.
waves run against supersonic flow and they cannot go any farther. So it just stays along the mark line, right? In subsonic, what's supposed to happen? There's nothing stopping them from running upstream. They run all the way upstream. They will go all the way up to the point where it goes and merges with the shock. That's the question I'm asking. Basically, will it change the shock itself? As in the pressure downstream of the shock will be lesser in that situation. No, the whole region, everywhere it's supposed to be. This is my way of understanding this flow, but that's why I'm asking for proof for my statement right now. So, but
We are
I've
working
asked
on
the
it, sir.
same question to two other people also. Nobody answered this exactly. So
Actually, the sonic throat has a role to play here. I guess I don't have a proof for saying that, but I think like that.
near the triple point, the shock is curved. Yes, that I agree. That I agree. That's not a problem. Yeah, possibly. I cannot understand.
Point, and that will reduce the
Not
pressure
just the triple point. I'm
downstream of.
saying it is just going to run upstream all the way.
Ah.
So the shock itself should get what do you call weakened.
Correct. So that is why it is having a lower angle at the triple point. Okay. So it will have a lower angle at the triple point.
Why is
Now,
it not affecting
the
the whole shock?
Normal shock.
normal shock means max term.
The stem, yes.
Max term, right? So when the expansion fan interacting with the shock wave upstream, there can be a reflected wave from that. This reflected wave again will be interacting with the other reflected wave from the triple point. So whether it will be coming down to the downstream of the max term, that means there's a subsonic domain there. This transmitted waves, if it comes down to the subsonic domain, then only the pressure will be decreased. But we have not investigated that. Why the maximum height is varying when the expansion fan is interacting with the incident shock? Because the incident shock has weakened already. It is more closer towards the RR then. Because if you have you're at the wedge point, you have, say, for example, 30 degree.
Stem part.
Ah.
Stem is going to start turning.
Maximum part, sorry?
The stem will
Ah.
not be straight anymore. It's going to start turning continuously.
I'm no.
But-
So it depends
but in
on
the-
the strength of the expansion. So the waves which are interacting with the max term, and strength of the waves are dependent mainly on the interaction between the expansion fan and the incident shock. So when the expansion fan and the incident shock interacts, there can be transmitted waves and reflected waves. These reflected waves are strong enough to influence the max term, then only it will be curved. But we don't know that. We have not looked at that part.
Okay, but you still have the CFT data.
Yeah, we'll be able
the
to look at
CFT data, we haven't seen a predominant curving or something like that. We saw a normal max term.
because we didn't have to include that effect in the analytical formulation to capture this. So we didn't look at that.
You cannot do that formulation with them.
Yes, correct.
This is one of those.
Okay, maybe last question. We are running out of time. Yeah, last.
A small question. Have you looked at hysteresis associated with this?
Now, how could I do that? Like in the simulation part, yeah.
Yeah, simulation.
No, I haven't looked at it.
So let us
Thank you.
thank Vinod for his nice presentation. Next presentation is by Tara Reshma, Abhyudaya Singh, and Dr. Rajesh. The title is Viscous Effects on Unsteady Shock Wave Reflection over a Convex Concave Ramp.
Good afternoon, everyone. My name is Abhyuday Singh, and I am a BTech student studying aeronautical engineering at MIT Manipal. And I'll be presenting my paper titled Viscous Effects on Unsteady Shockwave Reflections over a Convex Concave Ramp. So, shockwave reflections is a very hot topic in the field of high-speed flows and shockwave interactions. Because of their implementations in the various engineering aspects, including overexpanded nozzle flows and supersonic inlets. There are mainly three types of shockwave reflections, which are steady shockwave reflections, pseudo-steady shockwave reflection, and unsteady shockwave reflection. In steady shockwave reflection, there is a steady incoming supersonic flow, which impinges on a ramp, which creates a steady shock. In pseudo-steady reflection, there is a incident planar shock wave. Incident planar shock wave with a constant speed, which gets deflected from a straight ramp. In unsteady shock reflection, it can have a planar shock wave getting reflected from a curved ramp surface, or a curved shock wave getting reflected from a straight ramp surface, or it can be both a curved shock wave getting reflected from a curved ramp surface. Now, a lot of work has been done in the field of unsteady flows, including the works done by Jiva et al., in which they have done experimental studies on on a shock wave moving upwards in a coupled convex concave ramp. Tieb et al. Have numerically studied the effects of viscosity on shock focusing problems with reflectors of different shapes. Brahmi et al. Have studied shock wave reflection on a moving shock moving down a double concave ramp, and shock moving up a double concave ramp. Dricaris have studied viscous effects of shock moving over cylindrical convex surfaces. Reshma et al. Have studied the shockwave transition when incident shock travels down a coupled convex concave ramp. Now, when we talk about real world problems, we have to consider non-ideal effects such as the effects of viscosity and the boundary layer effects. Because of the fact that it has an upstream influence, because the pressure can travel through the subsonic part of the boundary layer and can change the local flow and the local shock structure at that point. So in our study, we have considered the effects of viscosity on unsteady flow on a coupled convex concave ramp, with the main focus on the interaction of the boundary layer with the stationary shock formed at the convex part of the ramp. And we have qualitatively and studied the qualitative aspects of the changes in shock structure and the local flow. This is the computational domain. The shock starts at the junction between the region 1 and region 2. The region 1 is initialized with post-shock conditions, and region 2 is initialized with driven condition. 63,842 quadrilateral cells are used in the mesh. The mesh also has a boundary layer with first cell height corresponding to y plus value of 1. The problem has been solved using a commercial CFD package, ANSYS Fluent. A density-based implicit solver has been used. For calculating the convective fluxes, AUSM plus scheme has been used. Third order MUSCL scheme has been used for spatial discretization, and second order implicit scheme used for temporal discretization. For modeling the turbulence, a K omega shear stress transport model has been used, and the simulations have been done on various incident shock Mach numbers, which are shown here. Now this is the animation of numerical Schlieren imaging at shock Mach number of 2.6. We can see as the shock moves down the ramp, the curvature of the shock changes and it adjusts itself to the curvature of the ramp. And as it moves over the flat surface, there is a Mach reflection getting generated. This is the animation for shock Mach number of 3.4. We can see the Mach reflection changing from a single Mach reflection to a transitional Mach reflection, and we can also see the changes in the shock structure near the ramp, which we'll be studying in detail later on. The numerical simulations have been validated against the experimental results, experimental studies conducted by Reshma et al. And we have got a good agreement between the experimental and the numerical simulations. This is the numerical Schlieren image at different Mach numbers, different non-dimensional times for shock Mach number of 1.4. We can see the stationary shock getting it's generated at time 4.76, which as time continues, it moves upstream. Now in this case, we see that the stationary shock weakly interacts with the boundary layer since there is no visible shock-induced separation. We can see a small bifurcation near the foot of the shock and a thickening of the boundary layer. And the separation is formed at some point downstream. These are the pressure contours and the surface pressure distributions. We can see due to the shock, the pressure rises sharply, and after that, there is some sudden decrease in pressure due to the separation region, which we saw earlier. This is the numerical Schlieren for shock Mach number of 2.6. In this case, the stationary shock is formed earlier than the previous case, and we can see the shock foot getting bifurcated into two, and the separation region forming. And as time continues, the separation region grows further. In the Mach number contours, we can see in much more detail the bifurcation of the shock foot and the shock-induced separation due to that. There is also, due to the convex curvature of the separation region, the flow after passing through the shock accelerates again, and we get pockets of supersonic region after that. In the surface pressure plot, we can see the pressure rising sharply due to the shock, and after that it stays somewhat constant for some time due to the separation region formed here, and then it rises again due to the adverse pressure gradient, which is encountered at the concave part of the ramp. For a later time step, we can see the growth in the shock foot and the growth in the recirculation bubble and pockets of supersonic region formed after the shock. For Mach number incident shock Mach number of 3.8, we see that the stationary shock is formed a bit earlier than the previous case. And in this case, we also see due to this sharp convex curvature of the separated region, the flow accelerates sharply, and we can see faint KH instabilities being formed for that time instant, and later as the curvature decreases, these instabilities also vanish away. And also due to the concave curvature of the separation region here, we see compression waves getting generated, which again coalesce into shock wave, and it joins with the main stationary shock. In the Mach number contours, we can see that in much more detail. We can see the regions of supersonic flow formed after the shock, and the recirculation bubble, and the KH instabilities being formed there. We have also compared the viscous case with the inviscid case, and we have seen drastic change in the flow separation pattern and the shock structure near it. In case of viscous case, in the viscous case, we see a separation bubble being formed, and due to that, the shock structure near that also changes. Whereas in case of inviscid case, we only see vortex shedding at the separated region, and also in viscous case, it has some influence more downstream compared to the inviscid case. Conclusion. So CFD simulations of planar shock moving down a convex concave ramp for various incident shock Mach number have been performed. Bifurcation of the foot of the stationary shock was observed due to the interaction between the boundary layer involving into a lambda shock. No significant shock-induced separation was observed for low shock Mach numbers below which were equal to or below 1.4. At higher shock Mach numbers, the lambda shock grows into a distinct shocks along with a significant flow separation. And strikingly different results were seen between viscous and inviscid solution while considering the shock structure and the flow separation. Scope of future work, a more detailed quantitative study involving different parameters like the boundary layer shape parameter, the incident shock Mach number, and the curvature of ramp will be, the effects of those will be studied on the flow separation and the stationary shock. Effect of viscosity on triple point trajectory and incident shock, and other wall temperature effects. These are the references which I used during my study. Thank you.
So we have time for just one quick question. Okay, so if there are no questions, let us thank the author. So the next presentation is by Shivaprasad ji, Dr. Rajesh, Dr. Jayachandran, and Arun. The title is Unstable Shock Solutions in Symmetric Wedge Flows.
Good morning, all. I am Shivaprasad. Today, I am going to present on unstable shock solution in symmetric wedge flows. I'm working under Rajesh. in the Department of Professor Rajesh and in the Department of Aerospace Engineering. Okay. This is the outline. Through these steps, I will take you all through my topic. Yeah, I'll introduce you about what is the current way of studies, and then how we achieved our objective using experimental and computational. Then present the results and conclude. When we take the shock formation studies, we in study flows under wedges, we are all the studies are focusing on the stable shock solution. But in the case of supersonic intakes and wind tunnels, they may pass through unsteady shock waves. For such studies, we need to focus on the transient evolution of that shock formation. To explain the current, the steady shock solution in a supersonic wedge. In a supersonic wedge, typically, we will say there are two solutions that happen generally. That is RR solution, regular reflection. When the wedge angle theta W, is lesser than the detachment criteria, there will be RR solution. And when it is greater than the detachment criteria, we'll say the solution that forms under that condition is MR. This is the shock polar, that incident shock and the reflected shock, which when it incidents on the pressure axis, what we get is the RR solution. And in the case of MR, there are two solutions possible that are standard MR solution and non-standard MR solution. That is when theta 1 is equal to theta 3 by theta 3 plus theta 2 in the case of standard MR solution, and in non-standard MR solution, theta 3 will be the sum of the theta 1 and theta 2. These are the stable solutions that forms in these scenarios. So what we are focusing is that during such wedge in a supersonic flow, during the formation of the RR or MR, what is the evolution that is happening of such shock? So for that, we have fabricated two internal models. That is, first one is RR model. We call it as RR model. That is, the wedge is actually 2 degree. And in the MR model, the wedge is only 12, wedges of 12 degree. These test sections are connected in an open jet facility, and which is the pressure is controlled using a PRV, and the valve is operated using an actuator. So internally is connected like that. And then there is a static pitot, not static pitot probe, there only a pitot probe is placed inside the settling chamber, which is shown as S. So we have fabricated that wind tunnel, that CD nozzle inside the wind tunnel using an MOC, which is invisible without the boundary layer correction. So to verify the Mach number in the test section, we have used a scanny valve to measure pressure from 10 ports in the test section. 6 of them in the center line, and other 4 are in transverse direction. And Mach number that we got is 1.46 for the first case, and with an uncertainty of 0.02. And second case, that is that MR case, 1.78 is the Mach number, and plus or minus 0.02. Since solving all the flow field within that wedge is difficult, we have used a second order Navier-Stokes with SST K omega and time stepping fourth order Runge-Kutta, and is used to evaluate the finer flow details And this is the domain where the subsonic inflow is even in the inlet and the subsonic outflow at outlet. And the viscous, walls are viscous and this is symmetry. It's a centerline Mach number profile from the computation. That red indicates the computation and the green indicates the experiments. For the case one alone is presented here. In the case of in the centerline Mach number, and you can see the transverse also matches pretty well. This is a transient evolution during the starting of the tunnel with the wedge here. So what happens is that the pressure, upstream pressure is what plotted here, Qt, and with time, the pressure is being ramped, and the starting shock moves all the way, and it hits the wedge, and it forms that RR. You can see that here when it moves from upstream to downstream through the wedge, what we've seen is actually it is multiple MR solutions are there before attaining that RR solution. Since it's not evident from here, that snapshots are put it here. So canny edge detection algorithm is being used to evaluate what is that angle, that shockwave angle with which that maximum reduces to a RR. You can see here even with the 0 maximum there is an RR, and it reaches our normal stable RR solution. And we have found that in using the canny edge detection algorithm, all these four have the same angle. So it's and that angle is at the shockwave angle is 47.12 with an uncertainty of 0.22, and it transition to RR. Further moving, since we know only the RR is the possible solution for such a 2-degree wedge, what is the nature of this Mach reflection? Are these Mach reflections different, and what is this? And from where these solutions came? Revisiting our shock polar that I have shown in the introduction section. This is the typical the shock polar. The red indicates I polar and the blue indicates the R polar. And we say that this is an RR solution when it hits the pressure axis. But there are two other solutions possible in this shock polar. That is one on the top. That is that R polar is again hitting the pressure axis, and then it hits with the I polar. So there is a strong MR that is solution that is possible, and also a strong RR solution also possible. Generally, we ignore these solutions are unphysical. So what we done is like applied two-shock theory and evaluated that strong shock and another 3-shock theory in this scenario for this strong MR. Since, as I said earlier, finer details capturing using sensor in that portion is difficult, we have used that numerical method, numerical computations to solve the flow field. And this is what during the transient evolution we have given the pressure, and these are at 4 different pressures. We have maintained the pressure P0, that is at the subsonic inlet constant, and run multiple simulations. And these are these 0, 1, 2, 3 indicates the particular the regions for that to compare with the 3-shock theory. And the case here also is compare this during the evolution we have used in the numerical solution and compared with the 3-shock theory, and that will be sway. The parameters that we are compared is Mach number and at those locations marked 1, 0, 2, 3. So you can see that the three-shock theory and 2-shock theory actually generally not applied in these scenarios. We have used that to check whether it is matching. So the 3-shock theory and the 2-shock theory, that is a strong one, actually matching with the CFD results when those appears in that CFD. So MR case, it is pretty well matching, and the strong RR case also matching. And finally, it matches with that weak RR solution, which we usually term the stable solution. In the case of in the second case, transient evolution of the wherever the MAC reflections are stable, that means theta is greater than detachment criteria. This is the case 2, where the wedge is 12 degree. The pressure is again the same. The pressure ramps over the time, and since it is too long, I captured only that wedge portion, and the shock comes and hits it. And what happens is that the snapshots clearly indicates that there, before reaching that particular max term, which is termed as stable, there are multiple MAC reflections with the different max term heights. And see, similarly, in the earlier case, we have seen that the transition was happening with a constant phi1. Here also, the canny edge detection algorithm shown that the shock angle here also remained the same during the transition. And to check, because here all are MR, here all solutions are MR, we have did the numerical method, the numerical computations to solve the flow field, and it is matching with the different max term. What is that max terms? The configuration with the different maximum height. So the B and C, different maximum height case is compared, and both are the same. Because in that case, shock polar also have only one intersection point. I didn't show you. Next step, what we done is, we try to maintain the pressure P0 that is there in the settling chamber the same. And what happens can be, we try to obtain those solutions. This is a case 1, the RR case, where the theta is 2 degree. We try to maintain the pressure constant so that we try to obtain those MAC reflections which are unstable. But as evident, it is actually oscillating. So our doubt is whether this oscillation is from the boundary layer or primarily from the upstream stagnation chamber itself. For that, what we have done is proper orthogonal decomposition of those Schlieren images. We have taken that captured flow field is captured at 10,000 FPS and a resolution of 325 cross 691. 14,000 Schlieren images are fed. I'll briefly explain what is the procedure. Each Schlieren images will be made into column vectors and put it as a large matrix A. That is, I call it as A matrix. So what happens is that in that column matrix, the size will be in that particular row, in the column, it made into a column. So the pixels. Okay, 625 into 691. This will be the size of the matrix, and that matrix we will calculate the eigenvalue of A transpose into A, and this is correlation matrix, and we get the eigen vectors as V and eigenvalue as epsilon. So we can do one more thing. The same procedure can be applied for the A into A transpose and obtain U and epsilon. But that is very tedious because the size is this much. So what we do is method of snapshots. What we have to do is, like, A is U epsilon V transpose. So to get the U, just multiply A, that is A into V, and this epsilon, which is the eigenvalues. So the V represents the temporal dynamics and U represents the spatial dynamics. And finally, the A will be this one. Even we can reduce the model taking the dominant modes, that is number of modes, I call it as R. And we can reconstruct it to get a modeled A. So this is the cumulative average, cumulative sum of that variance. I've shown only 50. By 50 of the 14,000 images itself, we have achieved 60% of the whole flow field. And that mode variance is, you can see the same trend here also. So these are the first 9 modes, where the first mode is kind of an RR mode, and with high dynamic, all the shocks are being present in the higher, because it all comes with the higher frequency dynamics. And in the case of our doubt that whether these oscillations are coming from the pressure, so what we have done is an amplitude spectrum of the stagnation pressure is taken. We have seen that frequency is actually 1.37, and for the first mode, the amplitude spectrum peaks it at nearly that value, 1.43. So from this, we can say that if we have some kind of hypothetical situation where we can maintain a particular P, it will be possible to achieve that particular unstable MRs. And this is to represent the higher modes. This is the 10th mode, and this is the 100th mode. And these will have the higher oscillations because of, and it happens at very low amplitude, not like the first modes. So this can be ignored. So I'm concluding my talk here. The RR formation in a wedge is a constant shock angle MR to RR transition. And during the transition, unstable solutions are observed and mapped to the strong solution that is there in the 3-shock theory. The intermediate show solutions are found to be unstable, and also it is predominantly unstable to the upstream pressure oscillations. Thank you.
Any quick one question?
Hi, one simple question. In the Schlieren videos, there is a normal shock, and behind that normal shock, again one more normal shock.
Yes, secondary starting shock. Is it which video you are referring to? This video? Or? Is this one you are referring to?
No, the other
just
one,
before?
One more was there. One more. Next video, the other video.
Okay.
Yeah, the next video.
Yeah. Here you can see that this shock, right? That is secondary starting shock, because after that first shock, you become subsonic. And that second throat again chokes and forms another starting shock.
Second throat, where is
second throat? There is a in the nose hill, there is a primary throat. So that I call it as a primary throat. Okay. And this throat that is formed by the wedge, since it is a strong shock that is generated here, all flow is subsonic here, and it accelerates again and creates a secondary starting shock. In that evolution, we can clearly see that secondary shock forming here, and it merges with that entire system.
No, we can have one more question.
Nice to see this. I hope you know Jintu James worked on something like this before.
Oh, I
Okay, don't know. Okay, you can find out. Yeah. Anyway, Jintu James worked on this kind of configuration, and he was looking at the transient that's happening across. Sorry?
Is it oscillations in the test section?
The oscillations across the diffuser throat.
Diffuser throat.
Yeah, which is like in this case, that becomes your diffuser throat.
Oh.
The second wedge
Yeah,
is
yeah,
your
yeah,
diffuser throat. So your Mach number is very low.
Yeah. It's
Okay,
one,
so
one,
that becomes your diffuser throat for that.
Okay.
condition. Whatever you just told, second starting shock, right? It's all related.
Okay.
So, but I wanted to point out that this particular thing you showed that there is a solution at the top, right?
Yeah.
That I also didn't think about before. That's an interesting thing. That's actually useful. This is what I believe Sushmita will have to look at in her flow for the same thing, because the backflow effect will come in. And then this basically when you're setting up your CFD I assume you would have done different P naught values, slowly increase P naught
Yeah.
values for each solution
For each
to
solution.
get to that particular point, right?
Yeah.
So you are basically looking at different P naught ratios, which is in some sense the back pressure is being changed for a single P naught to
Yes.
get to different starting conditions.
Correct.
Yeah.
Yeah.
So basically the effect of this normal shock coming in is related to, or coming in or going back is related to the back pressure being adjusted.
Okay.
And that back pressure being adjusted is now propagating inside on the subsonic portion to come and strengthen the shock or weaken the shock appropriately. Now we are saying that you are decreasing the pressure, so the shock is weakened and it's going more downstream. Okay, that effect will play a role in that Sushmita's, that thing which was a major discussion some time back, right? That will play a role and you have to take that into account. That's why I'm asking for pressure downstream always. But that will play a role there. Anyways.
In our case, we have hemmed up the pressure. It is a similar.
You increase the pressure.
Yeah,
upstream.
increase upstream.
That's okay.
Because it's
Same
easy
effect,
for us.
basically the same ratio.
Yeah, same ratio. The same.
Ratio is what matters.
Yeah.
Yeah. Okay. That's all.
So maybe we will wind up the session. We can have the discussions outside. Let's thank Shiva once again.
I would like to invite Professor Lijo from Government Engineering College, Thrissur, to present a memento to our session chair, Dr. Arun Kumar. For the next session, we have an invited talk at 2 p.m. IST. So please be back a couple minutes before the talk. Thank you.
Good morning, good afternoon, and good evening. I am Hidong Kim, the chairman of the 34th International Symposium on Shock Waves. It is a great honor to present brief introduction
check, check test, check. Check, check test, check. Hello, Professor Nicholas? Hello?
Hello, hello. Let me just start my video here.
Okay, okay.
Okay.
Hi, Professor Karas. How are you?
You hear me?
Yeah, I can hear you very clear.
Excellent.
You can hear me as well, no?
Yes, I
Okay.
hear you well.
We'll be starting the session in 10 minutes.
Right.
Okay.
So I will then just share my screen, right?
Yes,
For
sure.
the PPT presentation.
Yes.
Very good.
Hi, bro. Hi.
Hello.
We are just finishing lunch and in another 5 minutes we'll be able to start. You were able to hear me?
Yes, I hear you very well. Do you hear me?
Yeah.
Excellent.
Hello everyone, welcome back. So we have an invited talk now. For that, I would like to invite our session chair, Professor T. Jayachandran from Department of Aerospace Engineering, IIT Madras. Please come on the dais.
Good afternoon, everybody. Good afternoon, Professor Nicholas. Good afternoon, sir. Yeah. Today afternoon session, we have Professor Nicholas Apasidis. I think the pronunciation is right. To deliver the talk today. He is professor at KTH Royal Institute of Technology, Sweden, and got 3 decades of teaching and research experience in shockwave propagation, shockwave focusing phenomena, shock droplet and shock bubble interaction, and extreme states of matter produced by stable imploding shocks in various media. So I welcome Professor Nicholas Apasidis for the afternoon session. Welcome, sir, to IIT Madras and this symposium. Thank you.
Good afternoon. Thank you very much, Mr. Chairman, for these kind words. Let me start by sharing the screen with you for my presentation. Let's share the screen. Thank you, Mr. Chairman. First of all, I would like to express my thanks for organizers of this symposium. Excuse me. For giving me an opportunity to present the results of our research during the past decade. The title of this talk is therefore Highlights of Shock Focusing Research at KTH. And before I start, I would like to apologize for not citing any equations or formulas here. So please don't blame me for that. One of the most common examples of shocks which all of us have experienced is lightning and thunder. Extremely hot air produced by lightning functions as a piston as it rapidly expands into the cool surrounding air and creates an outgoing shock, as we can see in the image here. The shock strength decreases as the shock expands and is transformed into a sound wave producing low rumbling that we call thunder. In terms of energy, one can say that a very high initial energy density produced by a thin streak of lightning is spread over a larger volume of surrounding cool air with much lower energy concentration. But is it possible to reverse this process? Is it possible to transform thunder into lightning? This may sound as science fiction. However, it can be achieved experimentally by, so to say, collecting energy spread over a larger volume into a tiny streak of glowing gas through shock focusing. In this image, we can see a 5 millimeter high and 0.1 millimeter thin streak of argon plasma at the center of convergence chamber in one of our experiments. The convergence chamber with thin wing-shaped profiles placed radially is seen in this image. The wing profiles are used for shock stabilization, and we will get back to this experiment in a short while. So here is the outline of my talk. Why? What are the reasons for studying shock focusing? How? What methods, experimental as well as numerical, are employed? Results, experiments and simulations. So here we will show experimental as well as numerical results of our research. What are goals and benefits of shock focusing? One of the most spectacular potential applications is inertial confinement of fusion, and there are several companies exploring this, but there are, of course, many others. Often occurring when a moving shock is confined to a small volume. There is a broad field of applications in aerospace and protective technologies. In medicine, we can mention shockwave lithotripsy, in situ drug delivery by shock focusing, even tumor treatment. We can also mention multi-phase flow situations, for example, plane shock-induced non-symmetric bubble collapse, producing high-velocity liquid jets leading to erosion. Another example is production of gases with new chemical composition by extreme conditions in the focal regions, and many others. Another reason for studying shock focusing is that the extreme conditions in terms of pressure and temperature may result in human injuries and material damage when occurring uncontrolled, or may be used with advantage if controlled in a well-defined environment, producing extreme states of compressed matter, which are hard or even impossible to achieve by other methods. Highly nonlinear complex properties of strong shocks are revealed in the process of shock focusing as the initial shock strength increases. Last but not least point is that shock focusing is energetically very efficient. Very high energy density may be achieved by a low initial energy input. So, what are challenges and obstacles of shock focusing research? We should mention the first one is the converging shock stability. Converging shock stability, or rather instability, is one of the main issues here. Another challenge is a question of creation of converging shock. How can one create a converging shock? Cylindrical or spherical shock front experimentally. Another difficulty is the challenge is difficult access to the center of implosion for cylindrical or spherical shock fronts, which is another problem. It's actually a topological problem. How can you measure inside a cylindrical or even a more difficult task, spherical shock front? Non-ideal effects. As shock increases in strength, non-ideal effects such as ionization become important and even dominant mechanisms governing the convergence process. Short time and length scales. As shock converges on the focal region, it accelerates, and main effects occur on micro and even nanosecond timescale and sub-millimeter timescales. This presents, of course, a challenge in terms of experimental equipment, methodology, and diagnostics. So, how can one create a converging shock in a shock tube? This is a topological problem of transformation of a plane shock into a ring, and was first solved experimentally by Perry and Kontrovitz in 1951. Here we can see a sketch of their experimental setup with an axisymmetric teardrop-shaped body inserted along the axis of the shock tube. By this method, they were able to produce not just a segment, but a complete cylindrical converging shock front and study cylindrical shock convergence. This is a pivotal initial study formulating the roadmap for a large number of researchers following in their steps. Several key features of converging shocks were observed and investigated in this study. Stability or rather instability of converging cylindrical shocks, as we can see in the images here. It's maybe more clearly seen in these two images here, which are actually from a later study by Denon and Wilson from 1962, where we can see in this image, we can see a formation of a plane portion of initially cylindrical converging shock. Luminescence at the focal region is another important feature of converging shocks observed in this study. But let us get back to the first one feature, the first feature, namely tendency to planarity of a converging shock. The problem of stability of converging shocks has been investigated by a large number of researchers. Already in 1957, Whittam was one of the first to state that converging cylindrical shock becomes unstable with an increasing Mach number. In 1987, Takayama, Kleine, and Gröning, and later Watanabe and Takayama in 91, investigated stability of converging shocks in a series of experiments. Their findings confirmed that converging shocks exhibit tendency to planarity and transformation of initially cylindrical shock front to polygons with triangular or quadratic symmetries. In this image, we can see a nice symmetric quadratic form of a shock. Their explanation was that the initially cylindrical shock was perturbed by supporting struts inside the shock tube in their experimental studies. 3 struts produced triangular and 4 quadratic shock fronts. Here we can see a numerical simulation of instability from 2 small perturbations of an initially cylindrical converging shock front. As we can see, there is here the shock front is gradually transforming into a polygon with plane sides and corners. We can see a formation of, in this case, non-symmetric polygon. And this is not surprising since the perturbations occur non-symmetrically here. So again, look at this simulation. So, is it possible to stabilize the cylindrical shock as it converges on the focal region? Our main idea here is not to resist, but on the contrary, to go along with the nature and use the natural tendency of strong converging shocks to planarity in order to stabilize the shock convergence. The main point and condition here is to transform an initially cylindrical shock into a symmetric polygonal structure. And the key word here is symmetric. Important to note here is that the strength of converging a symmetric polygonal shock on average is the same as that of a perfectly cylindrical shock. The gain, however, is the stable convergence of a polygonal structure. In our experiments, we use an annular shock tube with a conical central body transforming a plane shock into a ring in a 2-dimensional convergence section, as shown in these upper 2 sketches here. To obtain polygonal shape, we are using symmetrically placed objects, such as cylinders, shown here, or thin or slim wing-shaped profiles placed radially in the chamber. So in the left image, we can see a front view of the test section with 8 small cylinders placed symmetrically close to the outer radius. And in the right image, the cylindrical objects are replaced by thin wing-shaped profiles, which are placed radially in the convergence section. Here we can see experimental results of a setup with 8 small cylindrical objects placed symmetrically close to the outer radius of the test chamber. Initially, cylindrical shock front is transformed by interacting with these small objects into an octagonal structure, converging on the center of the chamber, as we can see in these first 2 images here, creation of an octagonal structure. Once the octagonal shock is formed, it undergoes periodic transformations, doubling the number of sides in half cycle and then returning back to the original number by the end of the cycle, with the new polygon rotated compared to the original one. As we can see in these 2 images here, if we look at this image here, we see that we are getting back an octagon here. However, it is reoriented as compared to the initial one. We can see here that the corner is pointing between the cylindrical objects here, whereas in this first image, we can see corner pointing at the cylindrical object. In the last 2 images, we see shock front at the we can see a shock front at this is the focusing instant, and in this image we can see an outgoing shock after reflection. Here we can see a numerical simulation of the setup with 8 cylindrical objects in the test section. So we can see an interaction of the initially cylindrical shock with the objects. Let's have a look in greater detail. So we can see the interaction of initially cylindrical shock with the object. We can see Mach reflections here. And then formation of an octagonal structure. Here we can see formation of an octagonal structure. Then finally implosion, and then expansion of the reflected wave. So let us get back to our goal, which is improving convergence of shock stability. Is there any gain as compared to a purely cylindrical convergence? In this image, we see a comparison of light intensity at the focal region at the implosion instant for a series of runs in case of cylindrical versus octagonal convergence. As we can see, there is a much larger spread in intensity. You can see it here in case of a cylindrical convergence, and significantly more coherent distribution in an octagonal case, as can be seen in this figure here, which confirms greater stability or the preservation of symmetry in the latter case. Here is another configuration in which we transform an initially cylindrical shock into a polygonal structure, here by means of slim wing-shaped profiles placed radially in the test chamber. In this video, we can see a series of experimental images combined into a small movie. Let's have a look. So here we can see a formation of an octagonal structure, cyclic transformation. Here we see the doubling number of sides and corners in the process of convergence. We have the final convergence and then the expansion and then the outgoing reflected wave with a complex system of waves. This is a numerical simulation of the case with thin wing profiles, which we can follow the details in a little bit greater detail. So we can see, excuse me, let's have a look at this in a little bit greater detail. So we can see the interaction of the initial cylindrical shock with wing structure. You can see the formation of an octagonal structure here, implosion and reflected outgoing shock. Let's have a look again. And an outgoing reflected shock. So, what is the gain here? What are the results of an octagonal convergence in this case? The first image shows convergence chamber illuminated by the flash of glowing argon at the instant of shock implosion. So we get back to the image that we started with thin wing-shaped profiles. In the next image, we can see a final 5 millimeter high and 0.1 millimeter thin hot core of glowing argon gas. Please pay attention to surprisingly straight structure of the thin cylinder, confirming preservation of the converging shock wave symmetry, even in the final stages of the polygonal convergence. In the next images, we can see comparison of experimental, in this image, we can see comparison of experimental data, in this case with good delay solution. This curve plus stands for experimental values for air and circle for experimental values in argon. As we can see, there is a fairly good agreement here with some deviation in the final stages of convergence. In the next two images, we can see fits to black body fits to spectra at 100 and 3,200 nanoseconds into the flash. And the final figure shows experimental data of temperature measurements as function of time, with maximum temperature measured 100 nanoseconds into the flash, and maximum temperature is 5,800 Kelvin measured here. As we all know, spherical convergence is much more powerful than cylindrical two-dimensional case. Spherical converging shocks are mainly generated by reflecting a blast wave created at the center of the sphere by a spherical or semi-spherical reflector. This method has, though, several disadvantages. First of all, the strength of the initial blast is significantly decreased as it reaches the reflector boundary. There are also additional significant losses in the strength of the reflected shock due to the outgoing flow from the initial blast. The symmetry of the reflected shock is distorted by the outgoing flow. The symmetry is further distorted as it encounters the detonation products at the center. Temperature measurements are contaminated by temperature of the initial explosion, and it is difficult to access the center of the sphere for visualization and measurements. So, is it possible to improve this by creating a spherical converging shock by a different procedure? The answer is yes. One can create a spherical cap in a cylindrical shock tube. It can be achieved by a conically shaped transformation section, as we can see here. By this method, we eliminate all drawbacks mentioned above. The converging shock is not attenuated. On the contrary, it's growing in strength. It is not distorted, and we get direct access to the center of implosion at the tip of the convergence section. And measurements can be made we have direct access, and measurements can be made through a small opening sealed by a quartz window at the tip of the conical section. There is, however, still one challenge left. That is, the shock convergence in a simple conical geometry creates a series of Mach reflections, leading to shock fronts with plane portions, decreasing the focusing effect. To overcome this, we use a specially tailored shape of a test section, which gradually transforms an initially plane shock into a perfect cylindrical cap, as can be seen here, eliminating Mach reflections. Once the spherical cap is formed, it is guided to the tip of a small metal cone at the end of the test section, which is over here. And we can see it in this image. This is the image showing the general view of the setup. Here we can see a driver connected to a fast opening valve. This is the test section, and this is the cut of the test section showing the transformation section with a specially tailored form of the wall. We can also see optical fibers connected to a spectroscope for temperature measurements here. So what are the results of spherical convergence? This figure we can see fits to Planck's law for various Mach numbers. The maximum temperature measured in this series of experiments is 31,000 Kelvin in argon. The calculations based on geometrical shock dynamics, including non-ideal effects, indicate the dominant role of non-ideal effects, such as multiple level ionization, excitation, Coulomb interaction, and radiation. the main with ionization in the first place, the major sink. The main results of this study show that non-ideal effects become significant for Mach greater than 10 and dominant for Mach greater than 20. Evidently, ionization presents a major sink in the maximum attainable temperature. When we extended our calculations to convergence radius of 50 micrometers, the calculated temperature was 55,000 Kelvin, including the non-ideal effects, while in the perfect gas, it would reach 1.5 million degrees. On the basis of that, one can draw a conclusion that maximum attainable temperature in argon in similar experiments in practice is around 30,000 Kelvin. So here we are going to another technique of blast wave production. This is another setup in which the blast wave is generated by means of exploding wire technique. By means of this setup, we are able to study blast wave propagation and focusing not only in gases, but also in a variety of multi-phase flow and various geometrical situations. Here we can see a top view of the setup with exploding chamber and test chamber. Also a close-up view of the exploding chamber with 0.4 millimeter diameter copper wire connected to electrodes. In this image, we can see a side view of the setup with coaxial cables from 6 microfarad 30 kilovolt capacitor connected to the electrodes holding the wire, the copper wire. At a discharge of 17 kilovolts, which we were usually using in our experimental runs, the Mach number in the test section is around 3.8. Please note that the pulse energy at 17 kilovolts discharge from a 6 microfarad capacitor is just 860 joules. 860 joules. This is comparable to the energy content in 1 raisin. And this is brutto energy. The netto efficient energy is certainly less than that. Here we can see a general view of the experimental setup with the pulsed or continuous laser as a light source. Here we can see a test cell and the system of lenses guiding the light from the light source to the camera, a single image camera, or a high-speed Shimatsu video recorder with up to 10 million frames per second. So this setup was used for several experiments, and in this series of experiments, we're using the exploding wire setup to generate a supersonic jet in a miniature 150 millimeter long chamber. So we use the focusing effect to generate high-speed supersonic or even hypersonic jet here. This experiment, a supersonic jet of Mach number 4.5 in air, is produced experimentally at the apex of a miniature 150 times 50 millimeter convergence section. You can see the sketch of the section here and the upper view of the section here. Initial plane blast wave of Mach 2.4 in the convergence section is generated by exploding wire, and then the profile of the section is specially tailored to smoothly transform a plane blast wave into a perfectly cylindrical arc, imploding at the apex of the section. The cylindrical form of the imploding shock delivers maximum shock amplification in the two-dimensional test section, and therefore maximum subsequent jet flow velocity behind the shock front. Blast wave propagation and convergence chamber, as well as jet generation through a 2 millimeter opening at the apex of the convergence chamber is optically captured by a high-speed camera using shadowgraph method. So Here we can see an experimental video of shock propagation in the convergence chamber. You can follow here. You can see a transformation of a plane fast wave into a cylindrical form, focusing, and then generation of a supersonic jet. A supersonic jet of Mach 4.5 in the exhaust chamber. One of the main advantages of the described method, apart of being simple and robust, is the effective focusing of low initial energy input levels, just around 500 joules, resulting in production of supersonic jet in a small chamber. The lateral waves seen in this video are resulting from some inhomogeneities in the wire explosion in the exploding chamber. And here we can see the supersonic jet created in the exhaust chamber. This is a numerical simulation of the supersonic jet flow originating from the orifice at the apex of the convergence chamber, where we can see some main structures, some main jet structures, such as diffracted shock, contact surface, Mach disk, and vortex-induced shock pair, you can see here. So here we can see some details of this experiment. And in the upper left figure, it shows comparison of experimental and numerical jet structure at 50 microseconds after jet generation, where we can see some major components of the jet structure, such as the diffracted shock, contact surface, Mach disk. We have main vortex pair and vortex-induced shock pair, which we can see it's a little bit small here. The maximum jet velocity versus time can be seen in this next image. It is interesting to know that the maximum jet velocity of 1550 meters per second is reached not at the instant of jet generation, but some 6 microseconds after jet generation. This is due to the fact that maximum pressure difference is reached at this instant and not at the instant of jet generation, because of the pressure increase due to the reflected shock, as we can see in this figure here, in the convergence chamber. In the last two images, we can see jet structure at the instant of maximum jet velocity, which is 6 microseconds after jet generation. This is the jet structure here. And then a fully developed jet structure, some 60 microseconds after jet generation. I would like to round up my presentation by yet another example of shock focusing. However, in this case, shock focusing will result in a decrease of pressure at the focal region. We will here see negative pressures, and by negative, I really mean negative. This is the case of plane shock interaction with a cylindrical 22 millimeter diameter water droplet, which is placed between the upper and lower windows of the test section, as we can see in this image here. You can see the exploding chamber and the test section with the droplet placed here between the upper and lower surfaces of the test section. The cylindrical form of the water droplet with vertical wall is obtained by a combination of hydrophilic coating on the upper and lower contact surfaces. So the upper view shows the top view of the setup with droplet placed in the test section. And in the lower figure, we can see a close-up view of the droplet from the side and from above. And this is actually the actual shadowgraph image of the droplet here. So this is experimental video showing plane shock droplet interaction, where we can see a transmitted wave inside the droplet. You can see here. The transmitted wave reflects from the rear boundary of the droplet as an expansion wave. And it focuses at the location of approximately half droplet radius, creating negative pressures with a minimum of -23 bars. The negative pressures lead to cavitation with microscopic air bubbles, seen here as a dark cloud. This is a transient process, of course, and the cavitation bubbles disappear as the pressure increases over the cavitation threshold. And there we can also see the stripping of water particles from the upper and lower walls of the droplet, as well as creation of water mist. And two counter-rotating vortices creating a recirculation zone in the wake. The time span of the whole video is around 100 microseconds. Here we can also see the beginning of disintegration of the droplet. See the stripping of from the upper and lower boundaries of the droplet, creation of water mist, and two counter-rotating vortices. So in this image, we can see some details of this process. We can see a transmitted shock in the droplet. We can also see the reflected expansion wave here in this image here. And then we can see creation of cavitation seen as a dark cloud in this image here. This is a numerical simulation of this situation, showing some main features observed in the experiment. Let's have a look at it. Where we can also see the stripping of water particles from the upper and lower walls of the droplet and creation of two counter-rotating vortices, creating a recirculation zone in the wake. You can see. And this brings me to the end of my presentation. Thank you.
The last slide, where you have a shock that is interacting with the bubble or the droplet.
With the droplet, yes.
What kind of computation have you done?
It's a multi-phase computation with density of a mixture and volume fraction of both phases.
Can you be a little more detailed on that?
Well, it's a sixth order in time and using Wiener technique. The problem is in numerical computation, the problem is generation of the water mist. This is an obstacle, but it seemed to work out in this case. I can send you more detail if you send me an email. I can.
Yes, I will send you.
More detail. Yes.
Thank you.
Thank you.
Thank you, Professor, for that simulation. I just saw that droplet and shock interaction. From the rear side, when there's a recirculation bubble starting to form, will there be another shock that will run through the droplet inside in the liquid phase?
After the recirculation zone is formed?
Yeah, when the recirculation zone, just the bubble, the flow streamlines go and hit the bubble again, right? At that point, will there be another shock wave running through into the droplet?
No, I haven't seen it actually. Once the shock has already passed and is far away from the droplet when this process starts.
Yeah, I'm talking about a new flow coming and hitting the droplet, but maybe the pressure jump might be smaller and maybe you don't have enough resolution to pick it up probably.
No, actually, because of the very big impedance between air and water, the system of waves in the droplet is actually, it's an acoustic shock. In the beginning, the wave in the droplet has Mach number 1.01, and then it actually becomes acoustic. So you have a system of waves which is going back and forth in the droplet, but these are acoustic waves.
Okay, thank you. Then there might not be much in fact.
Thank you very much, Professor Nicholas. Thank you very much.
Thank you. Thank you.
So we'll end this session by presenting a memento. I request Professor T.M. Muruganandam to present a memento to our session chair. So for the remaining presentations, our next session chair will be Professor Ibrahim Mohammed Sugarno. I request him to come on the dais.
Am I audible? Am I audible? Right, so let's begin this session. We have a total of 3 talks in this session. Hope we'll wind up before coffee. The first one is by Lakan M. Manchpude and Swisha Rao. And the talk is on Reynolds number effect on shock mixing layer interaction. I'd like to request the presenter to go ahead with the presentation.
156. Okay. Okay. You can use this one is forward, backward, and this one is only. And this one only is. Is it? So there is not going any. That will not work then. Mostly this one.
Hello everyone, good afternoon. I have initial work on Reynolds number effect on shock mixing interaction. This is basically work we started recently, and it's basically a initial work. So myself Lakan, and I'm working with Dr. Shichara from IISc. So this is the outline of my paper, where I start with introduction, literature review, which basically will be very brief, and experimental details, numerical simulations, results, and bit of summary and brief references. So that's how we define the mixing layer, where region can be think of bounded by 2 boundaries, maybe have different velocities or different concentration or different densities. Entrainment is one of the important parameter when we think of mixing layers, because that's how it determines how the mixing layer grows. And mixing basically the process by which we remove the non-uniformity in that bounded region. This is typically the mixing layer flow profile looks like, where we have U1, M1, basically high speed stream, and ρ2, P2, M2 and a low speed stream. Convective speed and convective Mach number are the typical parameters which people use to define their mixing layers in terms of their performance, basically how it grows in different configurations. And this is typically the picture from Brown and Rashko, which is very famous. So if we see convective Mach number and convective velocity, that basically we define in terms of in a reference field, where we have to give relative velocity between your free stream and speed of your convective structure. So why we are studying mixing layers under a different condition, basically because these are the mixing, these are the features which we can typically observe in most of the experiments, applications where scramjets, or ejectors, where typically where we inject fuels in the combustors, there we used to have mixing layers, and their performance depends on various parameters such as density ratio, velocity ratio, concentration gradients, and Reynolds numbers. But there are few studies where people started working on mixing layers in 1980s, 70s. Brown and Rashko, Baba Masho, they're basically the famous studies where they pick up the work. And there's a parameter called convective Mach number, which I introduced earlier. Those parameters basically introduced by Bogdanov, where he started to see the effect of convective Mach number and how the mixing layer growth occurs when we start increasing the convective Mach number. After that, there are numerous studies where proposed by Gobel, Klemes Munjal, where they observed that whenever we increase convective Mach number by keeping other parameters constant, your basically mixing layer growth rate decreases. And there are a few studies which talks about how the mixing layer performance happens when you change the Reynolds number. So why we are interested too much in these parameters? The most important thing is most of the studies, whatever I have discussed till now, they are performed in constant pressure region. Basically, streamer pressures are constant. And in practical applications, we may not have always pressure constant across the mixing layer or in a streamer direction. So typical examples are ejectors where we can have unresponded jets where mixing layer at the lip of these nozzles can have curvature. Or and the study which is performed by Dr. Shisha, where you observe that whenever we have pressure difference at the exit of the nozzles, we'll have curved mixing layer and inclined at a particular angle. So this is one of the important factor which we need to consider when we start talking about mixing layers for practical applications. So keeping this in mind, I started my work, and along with this, typical inclination, mixing layer interaction, density ratio, velocity ratio, and Reynolds numbers is also important parameter when we talk about growth of mixing layer in this kind of scenarios. So this is my typical test section where M1 and M2 are high speed and low speed stream. And my test section dimensions are 600 mm in length, and plate splitter plate is around 120 mm. Test section height is 27 mm, and splitter plate thickness is 3 mm. This is a test section where I perform my experiments, and we supplied with 10 bar pressure from vessels, and right hand side you can see different combination of nozzles we can do, where we can have nozzle combination from Mach 2, basically Mach 1.5 to Mach 4, but we cannot go on higher range to 3.5 and 4 because mixing layers start deflecting too much towards the upper side of the wall, so it's difficult to analyze that section. So we restrict ourselves to from Mach 2 to Mach 3 range. These are the two cases where I have done experiments to talk about in this paper, where my M1 stream is Mach 3 and M2 is Mach 2. And we have convective Mach number is fixed constant to 0.23. And main difference here in two cases basically the Reynolds number. Reynolds number changing by changing the total pressure at the inlet. So first case it will be 28.5 and 47.1 combination. That will be my first case. And second case will be where I have Reynolds number 50.1 and 82.3 in primary and secondary streams. So Schlieren measurements I have done to visualize the flow structures and to calculate the visual thickness. So nanopulse lasers Hyler 640 is used with 10 nanoseconds of pulse width. Phantom Miro 110 camera at the resolution of 832 into 108 we used at 19,000 fps, keeping exposure time up to microseconds. With this resolution, I'm getting a spatial resolution of 0.3 mm per pixel. And pressure was static pressure measured using piezoresistive MPX 4250 absolute pressure sensors, which are accuracy of around 1.5%, and sampling rate is around 500 kilohertz. Along with the experiments, I have done some basic simulations, to larger simulations to extract more features and to understand what is happening after the interaction point. So these are basically governing equations. Left hand side, you can see they are resolved features, and right hand side, you will see basically subgrid terms. So to model subgrid terms, I'm using Whale model, which is given in equation 8, which is basically helpful in resolving near wall features where rotational and your strain parts are important. This is my LES mesh, basically the zoom in portion near to the splitter plate, because that is important to resolve near to the plate because we have curvature there. If we have rectangular plate, then it's a straightforward job. But if you don't resolve properly, it will go to blow off. So my computational dimension basically 140 mm in length, 27 mm in height, and 10 mm in spanwise direction. And grid points are showing there. And basically those guidelines were taken from Choi and Moin, where they said per mm of boundary thickness, how much element we should provide. So those numbers according to that. So total number of grid points comes around 44 million. So alias perform basically using raw energy form, which is open form based solver developed by Modesty. So I implemented the solver in a basic open form platform where they have used AUSM plus for displayation of convective terms and Whale subgrid model used to modeling subgrid scales. So inlet, I have given power law velocity, and this again taken from Pope, where they mentioned in the range of Reynolds number we are using, we can use power coefficient of around 0.192 so that it works better. And all the walls, including splitter plate, are given no sleep, and side walls are cyclic and exit wave transmission. And this is a different case for alias, basically a different Reynolds number, because we cannot go for high Reynolds number for alias simulation. It demands a lot of computational power. And numerous simulations are performed in Cray supercomputer in IISc. These are the typical flow features obtained from experiments where I have oblique shock, basically that created because of deflection of mixing layer. Shock mixing layer before shock interaction, shock mixing layer interaction, and mixing layer after the shock. And we have seen expansion fan also, that's again because of deflection of mixing layer in the high Mach number stream. In upper image, top side image, I'm showing these dot points just to show where measure the pressure. These pictures are from Elias. Here again, we can see the typical features are captured clearly. I'll come back to this image again because we require to describe that. So left-hand side image, basically my pressure measurements from my experiments. Here, typically, we can see there is a pressure gradient exists along the mixing layer itself. Black line basically in my top stream, high Mach number stream, and red lines showing in low Mach number stream. Right-hand side image is alias and experimental data validation. I again show my alias works better. So red line basically for low Reynolds number case, and case 2 is for high Reynolds number case. So from experiments using the Canny edge detection algorithm, we obtained this mixing layer growth rate before and after the interaction for 2 cases where we can see with increasing the Reynolds number, we basically have increase in our mixing layer growth rate even after the interaction for both before and after the interaction, if we increase the Reynolds number. So that's because one effect may be because of pressure gradient in initial part before interaction, and second part we can have curvature as well as the enhancement of vorticity because of shock interaction. So those details again I need to do in more detail. So here if you see this plot basically compared with the slicer, just given some modified convective Mach number, convective parameter, compressibility parameter basically. So red dot and red square basically shows mixing layer growth rate before interaction. So they fall well with the literature. But after the shock, mixing layer interaction, both cases, low Reynolds number and high Reynolds number case, we have this point basically lying above this curve. So this is one thing we have to investigate in much detail. So one reason for this because of, as you have seen shown in Elias. So initial structures are more or less looks two-dimensional, but as they process the shock, they are more of stretch and break. So we can see as this space between the two rollers are increasing, it distributing the vorticity to the higher region. So that's why the growth is more on the after interaction point, and the growth rate is higher for higher Reynolds number case. That is one of the reason, and details basically we have to investigate again. And right-hand side basically shows vorticity growth, non-dimensional growth, which is obtained from Elias. And as per literature, they show that whenever interaction happens, they will be increasing vorticity, but it might not sustain But we have, in our case, we have a curvature as well as different Reynolds number. So that increase in sustained growth rate of OTCD might be because of curvature effect and shock mixing interaction. So two effects are playing the role. That is what our initial thought is. And I did this pressure spectral density calculations on pressure data. X-axis basically wrong numbers, so we have one order less. So here Reynolds number case, we observed two peaks at around 400 hertz, but at higher frequency we don't see any definite peak. So basically it's a broadband. But we go to higher Reynolds number case, we have peak at around 350 hertz and around two peaks around 550 hertz. So they basically show Reynolds number playing a role in frequency of missing layer structures. So there again, I could say the breaking of structures after the interaction point playing a role in deciding the behavior of the missing layer. And these are some conclusions if we go. So higher Reynolds number case basically shows higher growth in mixing layer growth rates even before and after interaction points. And there are the higher peaks observed at higher Reynolds number case, basically 2 points, whereas there is no definite peak in high frequency at low Reynolds number case. From the aliens data, we can see that OTCT thickness increases after interaction points and it is sustained as compared to other cases where they say OTCT increase just drops just after some distance after the interaction point. That's all from my side. Thank you.
Yeah, thank you, Lakan. Questions?
Your plate seems to be having a thickness
Yes.
which is quite comparable with the interaction lengths that you consider.
Yeah, because we have to keep the thickness because we have pressure difference at the exit. So if we keep very, very thin, it starts bending.
No, what I'm asking is why do you need to have a blunted trailing edge? Why can't you have
Recirculation zone will be very high if we don't give the bluntness.
what?
Recirculation zone, that base region basically. So that will reduce if we have curve section there.
No, I'm not asking that to be flat. Why couldn't that have been sharp? Because I mean, immediately have had two.
Yeah, so there will be expansion region coming right from the EPB to corner there. There will be a huge expansion region both the sides. We already have expansion coming in because of deflection. So to avoid that, we keep it flat and make the circular at the edge.
Any more questions?
Can you go to your Schlieren image where you have three shocks focusing on one point? This.
Yeah.
Even this or the numerical one seems to be more clear in there, but yeah, I like this one. There are three shocks coming to the corner, right?
Yes.
Was it by plan or it just so happened that it's...
No, it happens actually. So we have deflection, right? So we start with expansion. So flow turn again away from mixing layer. The first shock comes. Second shock because of the separation bubble on the top side. And third shock is because of reattachment. So all these shock basically comes and coalesce together.
What is reattachment here?
So there will be separation bubble, right, up the top side. So there is a separation shock, black one. And once start reattaching the separation bubble, you will have the other shock there, a third shock.
Telling that the mixing layer is turning back and that's what you call as reattachment. Okay. So now for all these three things together, they meet at that point and form one big recirculation bubble.
Yes,
You don't see a separation shock starting from the inside. No, why is it happening only after the shocks?
No, sir. Basically, if you zoom in that region and more clearly, it is there. In experience, you can see basically there's a shock. That shock you can.
In the experiment, it's happening.
Yeah.
So in LES, it is not happening.
It's very faint that region, lower portion. That's because expansion coming and hitting that part also probably weakening that part, so it's not clearly visible there. So probably if I adjust the gradient in that region, it will be visible.
Okay, but what about the upstream end of your splitter plate?
Yeah.
What is that surface? Is it like round again in the front?
This part?
The upstream end of your.
No, that is like a normal nozzle inlet. We have constant total pressure selection there.
So is it a sharp end or is it a rounded end is the question, the plate?
That is sharp.
Sharp end.
Yeah.
Okay. And then it's symmetrically increasing thickness.
No, sir, it's a flat plate actually.
As in it's a
Spittle plate, right?
rectangle kind of end.
Yes.
Splitter plate has a rectangle kind of end, only this it's round.
Yes, yes.
Actually, it's better if that end is smooth, because otherwise the boundary layer growth will be affected.
Okay.
It will start having some oscillations. This was found by actually in IIC only. Raghuji did this sometime back.
Oh, okay.
He found that there was some problem because of this.
Okay, sir, I'll look at it.
Talk to him once and you'll know.
Yeah.
Okay.
Right. Any further questions? If no, let's thank the speaker once again. Thank you, Lakan. Right, let's move on to the next talk. It will be delivered by Akhil Shivadas and Deepu M. The work is on investigation on oblique shock shear layer interactions.
Good afternoon, everyone. I'll be delivering a talk on my research area, investigation on oblique shock shear layer interaction. Myself, Akhil Shivadas. I have been a research scholar at Indian Institute of Space Science and Technology, Tirunelveli, for the past 10 months, under the guidance of Dr. Deepam, who is a professor at Department of Aerospace Engineering, IIST, Tirunelveli. Now, these are some preliminary work which has been done by us in our research area. Coming into the overall overview of our presentation, first there will be introduction, literature review, objective, methodology, then research and discussions, followed by conclusion. Introduction, shock shear interaction. If you're talking about shock shear interaction, it is mainly found in supersonic flows. In most of the supersonic flows, such as in overexpanded nozzles, supersonic fighter jet weapon airways, in inlets of scramjet engines, supersonic cavity flows, such as the one which is shown in the figure. The importance of the interaction of shock on shear layers comes into the picture because this shock can affect the characteristics of shear layer. This is another effect of shock on shear layer study which has been done in our facility itself. This was done by Vishnu and Aravind. Now coming into the literature view, first we have the convection of a pattern of vorticity through a shock wave done by Ribner et al. In that, what they have done is that they have studied the effect of convection of a weak turbulence through a shock wave. This weak turbulence was modeled as a superposition of sinusoidal shear waves. And what they found is that very intense noise field is produced in the downstream portion of the flow when a low intensity turbulence passes through a shock wave. Next, coming into the other literature, next is the experimental work done by Papamosho et al., where they experimentally investigated the structure of turbulent compressible shear layer. What I found is that on increasing the compressibility, the convective velocity, which is the velocity of the large coherent structure within that mixing layer, it will approach that of either of U1 or that of U2. Next is the DNS study performed by Lee et al. To study the shock strength effect on turbulence. What I have found is that for Mach numbers up to 3, the amplification produced by the amplification of turbulence kinetic energy as well as vorticity fluctuation produced across the shock wave is significant, but beyond Mach number of 3, that much amplification was not observed. Next is the two literature studies done by Mahesh K. They also performed a DNS study. And what they have found is that if the correlation between U and T is negative, the amplification of turbulence kinetic energy, vorticity, and the thermodynamic fluctuations are enhanced. And if it is positive, the amplification was suppressed. And there is study by James et al., where they performed a DNS of shock turbulence interaction using second order McCormack. What I found is that if there are entropy fluctuations upstream of the shock wave, the amplification of turbulence kinetic energy and transverse vorticity fluctuations across the shock will be significant. Now, coming into the objective of our study, shear layers are basically formed when there are two parallel streams of fluid which are interacting at a surface having different velocities. So shear layers can be regarded as regions of velocity, intense velocity gradients. So shear layers in expanding flow have wide range of intense gradients. What we have found by going through the literature is that effective shock, oblique shock in such expanding flows was not found in that much abundance. And as such, our main objective was to study the effect of shock waves on shear layer characteristics in an expanding flow. This was the basic structure of our flow structure of our domain which we have obtained. Our shear layer was obtained by shear layer in supersonic flow was obtained by placing a splitter plate inside a planar feeding nozzle. And due to the geometry of the structure, oblique shock waves were generated which interacted with the shear layer. Now coming into methodology, mostly numerical studies was performed. For our numerical case, a planar feeding nozzle of area ratio 2 was considered. The feeding nozzle having a height of 40 mm and a splitter plate having a slanting edge at the top portion with a slanting angle of about 10 degree was given. This splitter plate was placed in the geometrical domain in such a way that the bottom portion of the splitter plate coincides with the center line of the nozzle. This nozzle was then attached to an extended duct of 135 mm in length. The convergence angle of the duct was 10 degree, 15 degree, while the divergence angle was 10 degree. We used 2D Navier-Stokes equations were solved, in which Q were the conservative quantities which are solved, F and G were the inviscid fluxes, F and G were the viscous fluxes. Turbulence modeling was done using SST K omega model was used for turbulence. The numerical scheme which was employed was pressure-based coupled solver available in Fluent, and for calculation of convective fluxes, reach or distance-based method was used. Steady-state analysis was performed for a pressure of 8 bar, and the parameters were discretized using were spatially discretized up to second order. And for convergence or order of convergence of residuals was fixed as 1 × 10⁻⁻6. This is basically, as I mentioned, 2D steady-state analysis was done. And in order to negate the effect of walls, the domain was extended 10 times along the flow directions and 5 times perpendicular to it. The splitter plate, the main aim of placing the splitter plate inside the feeding nozzle was to obtain shear layer. So by means of this splitter plate, a velocity difference was obtained between the top portion and the bottom portion. And as a result of that, a shear layer was formed. The inlet was given as at a stagnation pressure of about 8 bar, and the outlet conditions were given as pressure outlet with atmospheric conditions. And all the wall conditions, including the splitter plate and the nozzle extended sections, were maintained as adiabatic. Early cold flow analysis was done for our case with air as the working fluid. Now grid independence was done for 3 grids. Medium grid size was about 3,73,000 and coarse was 1,56,000 and fine was 6,23,000. Almost all the grid gave same pressure values at a plane which was selected at 170 mm from the inlet. So medium grid was chosen for computational easiness as well as to capture necessary flow phenomena. Now coming into the results and the discussions. An experimental Schlieren was also done to validate our flow structure which was obtained numerically with that of experiments. In the bottom figure, numerical Schlieren is shown, while in the top figure, experimental results, experimental Schlieren is shown. The flow structure, which essentially involves oblique shock wave emanating from the splitter plate tail edge, which on interaction with the walls undergo further reflection. That same structure was also obtained in the experimental Schlieren, which was performed in our lab itself. This is a video of experimental Schlieren, which was performed in our lab itself. For this work, the stagnation pressure given was about 8 bar, and the same was done numerically. So almost a similar flow structure was obtained. So our numerical work was qualitatively compared with that of the experimental results which we have obtained. Now coming into the flow structure which is happening inside our test domain. As I mentioned earlier, the test domain consists of a planar feed nozzle of area ratio 2, which is provided with a splitter plate having a slanting edge at the top portion. Due to this slanting edge given, the velocity which was produced in the top portion and bottom portion are different. And due to this velocity difference, a shear layer was formed. One oblique shock emanated from the trailing edge of the splitter plate, which undergo further reflection and it interacted with the shear layer. And oblique shock undergo further reflection in the extended duct section as well. And the shear layer was found to interact with this oblique shock. Numerically, we were able to observe this much more clearly. Now, my counter of this numerical simulations was also undertaken. In this numerical simulation, 4 planes were chosen. Planes 1 and 3 have presence of shear layer, but there is no appreciable interaction of oblique shocks on shear layer in planes 1 and 3. While in case of plane 2, there is shear layer as well as intersection of oblique shocks. This intersection of oblique shock waves is just downward direction, is in vertically downward, is just in vertically downward direction from that of shear layer. While in case of plane 4, which is considered here, oblique shock waves were found to interact with the shear layer. Shear layers was also found to undergo deflection when they interact with oblique shock waves. Initially, the shear layer was deflected upwards due to the pressure difference. At the lower portion, the pressure is comparatively higher to that of the top portion, and as a result, the flow will be deflected upwards, and along with that, the shear layer was also found to get deflected upwards. Further deflection of the shear layer as well as the flow happens due to the formation of the oblique shocks. Now, in order to account for the momentum loss across our test section, thrust was plotted. As you can see from the plot there, for the first and the third plane, only shear layers are coming into the picture. And because shear layers are regions of intense velocity gradients, thrust was found to decrease in the shear layer regions. In case of the fourth plane, shock was found to interact with the shear layer. And as a result of this interaction of the shock with shear layer, thrust increased in a steep manner in the fourth plane. While in case of the second plane, which is considered here, due to the presence of shear layer in the beginning, the thrust was decreased, but due to the interaction of the shock, thrust increased, and further due to expansion, the thrust was again found to be decreasing. Now, static temperature plot across 3 planes was also considered. In the first and the third plane, as mentioned earlier, there was no interaction of the shock with the shear layer. But so, due to the presence of shear layer, temperature was found to be increasing as a result of the presence of shear layer. But in the case of the third plane, just downstream of the shear layer, shock interaction was found. And as a result of that, the temperature was found to be temperature was found to have a steep gradient. And just below that, due to the expansion happening below the interaction of the shocks, the static temperature was found to be decreasing. So due to the high turbulence in the shear layers, this temperature was found to be increasing. And just below the shock wave, expansion happened. And because of that, the temperature decreased in case of the second plane. Now, velocity variation for those 3 planes was also plotted. Velocity variation, when comparing the velocity variation plot with that of the static temperature plot, what we have found is that it is contrary to the static temperature plot, in the sense that if velocity was, if static temperature was found to increase due to the presence of shear layer, velocity was found to decrease due to the presence of shear layer. And this again attributed to that velocity gradients which are found in the shear layer. And again, if we are considering the second plane, due to the presence of shock, a sharp gradient was noted, but below that shock expansion was happening, and due to that, the velocity was found to be increasing. It was found to be increasing mainly at the expense of static temperature. Now, in order to quantify the turbulence associated with the shear layer, Reynolds stress was also plotted. The effect of shock across the first and in this case also across the three planes, Reynolds stress was plotted. Across the first and the third plane, the Reynolds stress value due to the presence of shear layer, Reynolds stress was found to have some deflection. But across the fourth plane, where the shock was found to be interacting with the shear layer, Reynolds stress was found to have a significant value. This is due to the velocity gradients which has been produced by the shock. And as such, we can say that due to the presence of the shock on shear layer, Reynolds stress has been found to have a significant value across the shock. Now, coming into the conclusion, a 2D planar CD nozzle with a splitter plate was studied numerically, and the results were qualitatively compared with that of the experimental Schlieren, which was done. It was found that the major effect of the shock was to cause a deflection of the shear layer along with the flow direction. The shocks also was found to result in a slight increase of static temperature in the shear layer, which is approximately 1.295%. And the X component of velocity was also reduced slightly, which is 2% due to the present results of shock. So this was our major study, which was done using steady state simulations. Now, as a further advancement of our study, we are planning to do unsteady simulations and to obtain the effect of shock on shear layers. Now, these are the references which I have mentioned. Thank you.
Yeah, thank you, Akhil. Questions?
I just want to ask you that was there any particular reason why you chose a certain, it is a very sharp throat and then a straight section. So was this, you thought about the design of this or you just placed it? Because usually when people look at these kind of problems, they want to have, uniform flows. When you have this sharp throat, you don't get uniform flows and mostly the flow is non-uniform.
Sir, in order to create that shear layer, our main aim was to have a velocity difference in the top portion and the bottom portion. So to produce that velocity difference, if I am looking at the geometrical domain, that slanting edge was given at the throat section. So it's kind of giving a divergence so that the top portion, the velocity will be more compared to that of the bottom portion.
Yeah, that is, but your throat is very sharp and then it takes, it's more like a conical nozzle, like this section that you have. So they actually produce non-uniform flows.
Okay.
They don't produce, if you take a cross section, you will see that the flow is non-uniform. It's not, while your earlier pictures, if you see when they are looking at mixing layers, they'll have uniform U1, U2, and then at the mixing layer, you will have a non-uniform. But here, you are actually having two non-uniform flows. Did you give any consideration to this, or is this something that you had, so you started working with?
Actually, our main consideration while giving that slanting edge was to, as I mentioned earlier, to generate that velocity difference. Top and bottom should have velocity difference. The other non-uniformity which you have mentioned, we haven't considered that one.
And could you just check that, in your bottom section, your CFD result seems to show that that's actually a shock wave, not an expansion wave.
Do you mean
in the bottom part?
In the bottom,
you have a wave, right? That was starting right from the throat.
Yes, sir.
This is also a problem with these sharp throat nozzle, as they say.
Yes, sir.
Because if the throat is not smooth, you can at the sharp throat you can have larger expansion than what is ideal.
Yes, sir.
And then after that it can generate a shock, which is usually a feature with sharp throat nozzles.
Yes, sir. So
You will get intersecting shocks within the nozzle section itself.
Yes, sir.
So if you have labeled it as expansion wave,
Yes, sir.
probably you may need to go and check back whether, because your contours seems to show an increase and decrease at that region,
1 minute, sir.
the bottom half.
Yes.
It is increasing, you have a wave there, and then again it starts decreasing, and then again it starts increasing.
You mean from the diverging portion, starting of the diverging portion? Sir, at that diverging
Is
portion,
it an expansion or is it having a weak shock structure?
sir, when I am taking that from this Mach contour plot, I have checked before and after that expansion wave, what is the Mach number value numerically. itself. So what I found is that after this flow structure, the Mach number value is increasing. That's why I have mentioned it as expansion wave itself.
Okay, okay. Yeah, fine. All right.
Questions? So I have a question. I mean, like this numerical geometry was generated based on the test facility available, is it?
Yes, sir. Actually, this is a modification. 1 minute. Actually, that nozzle was already available in our test facility. So we have placed a splitter plate in order to have a shear layer effect.
That explains the constraints. All right. Okay. If no further questions, all right, let's thank the speaker once again. Yeah, thank you, Akhil. Well, the last talk for this session, we have Vishnu Prasad, Vinod Anbusarin Raj, and C.G. Rajesh. And they'll be presenting a study of expansion wave diffraction over bodies.
Good evening all. Myself is Vishnu Prasad, under the guidance of Professor G. Rajesh, Aerospace Engineering Department, IIT Madras. And I am here to talk about my paper on the topic, a study of expansion wave diffraction over bodies. My co-authors are P. Vinod and Anbusarin Raj. This is the outline of the presentation: introduction, methodology, computational details, results and discussions, and conclusion. So before going, expansion waves are Mach waves, which makes Mach angle with respect to the flow. So these are as important as shock waves. So expansion waves can be steady as well as unsteady. So as you can see in the first case, when a supersonic flow moves over a convex corner, centered expansion wave fan, also known as Prandtl-Meyer expansion waves, are generated. And also in shock 2, we can see moving expansion waves. My area of interest is the moving expansion wave, which can be generated using a shock 2. So as you can see the schematic of a shock 2, we have a diaphragm location. Region 4 is the driver section, and the right of that is the driven section. Driver section will be high pressure region and driven section will be low pressure region. As you can see, when the diaphragm bursts, expansion waves will travel towards the driver section. And the shock wave will move towards the driven section. So my area of interest is the study in driver section. So before going into expansion wave diffraction, shock tube studies can be conducted for shock wave diffraction as well as expansion wave diffraction. As I said, we are more focusing on the shock wave side towards the driven section. If you place the body over there and studies are conducted, it's called shock wave diffraction. And studying in the driver section of the shock tube, we study more about expansion wave diffraction. And expansion wave diffraction, focusing interaction like diffraction of shock waves, interaction, and focusing have been intensely studied for the last years, but only few works have been conducted on expansion wave diffraction. Some practical applications of expansion wave diffraction includes rupture of a pressure vessel. And an interesting application is in solid propellant rockets. As you can see, a problem, the main disadvantage of a solid propellant rocket is its compact, like after its manufacturing, its flexibility, we can't control that or extinguish the burning solid propellant rocket. So rapid depressurization to extinguish the burning solid propellant rocket is also an application of our expansion wave diffraction. As you can see, it can be simulated using a quench bomb. So you can see the propellant is placed in the primary chamber, which will be the high pressure region, and the secondary chamber, which mimics the driven section of a shock tube. So when the diaphragm bursts, expansion waves will travel towards the propellant region, and the studies are conducted for the rapid depressurization to extinguish the burning solid propellant rocket, which makes a very interesting application. So moving on to the expansion wave diffraction. Expansion wave diffraction happens based on depends upon two factors. One is the diffracting body over which the expansion wave diffracts, and second is the strength of the expansion wave. The strength of the expansion wave is decided by two criteria, which is the diaphragm pressure ratio and the location of the diaphragm from the diffracting body. And as I said, there have been intense study over the shock wave diffraction, but there are only few studies, namely 3 studies by Professor Berkskius and co-authors on expansion wave diffraction. The first and foremost study of expansion wave diffraction was conducted by Berkskius and Mohammed in 2014, where he studied the expansion wave propagating over a 90-degree corner. The main conditions he conducted numerical as well as experimental experiments, and the flow features were identified through high resolution shadowgraph imaging and numerical simulation. So the main criteria he considered for his study was the distance from the diffracting body as well as for different diaphragm pressure rupture ratio. The numerical simulations reveal complicated flow within the bubble, including local separation and secondary vortex. As I said, he conducted his experiments and computational for basically two different pressure ratios, and he observed, as you can see, when the expansion fan moves from right to left, the flow will be generated, the flow will be induced to the opposite direction from left to right. So he observed shear layer, and he concluded that whatever he has seen in experiment is not in agreement with computation also. So the second paper was actually a continuation of his first paper. This was also done by Professor Berkskius and Randall Patton in 2016, where he, in the last paper, he observed the shock wave development within the expansion flows, and he proposed it may be generated either by the development of the compression waves that consolidated into a shock wave, and or due to a local area of transonic or supersonic flow being generated. But also he concluded that he's not sure about what will be. That's why he proposed either because of these two, the shock wave will be developed within the expansion flow. And the last literature which I could find in the expansion wave diffraction is again by Berkskius and Valley in 2018, where he studied the expansion wave propagating into or reflecting from a cavity. As you can see, when the diaphragm bursts, expansion wave will be moving towards the cavity and the flow will be generated from left to right from the figure. So the shock waves were formed in the cavity as the flow met a concave surface for a compression corner at the cavity exit in the shock tube. The different parameters he considered for the study was the curved diaphragm effects and the diaphragm locations from the cavity and the diaphragm pressure ratio. So based on this literature review, as you can see, expansion wave diffractions over bodies have been studied to an extent to some limits. So there were many areas or aspects we need to further study. So that's why I took this as my objective. So for the numerical methodology, I have used an in-house 2D inviscid shock capturing finite volume code. So validated by my co-author in the lab, and I have used the reconstruction is carried out using 5th order Tino code and HLNC for flux calculation. Classical RK4 solver is used for the time marching. And about the domain details, a shock tube with the body placed in the driver section were considered. As an initial study, I have taken bluff body and a concave wedge for my study. As if now for the preliminary study, I have taken diaphragm pressure ratio of 11.5 and I kept the diaphragm 60 mm away from the body. So this is the numerical domain. All the parts of the domain are given as inviscid walls. And the driver section and the driver section are initialized with high pressure and low pressure based on that pressure ratio. These are the dimensions of the bluff body and wedge, which I consider for my study. So I have done grid dimension study for, I have used 3 grids of 0.5 mm, 1 mm, 2 mm in the X and Y directions. The variation of the pressure in X direction for 3 different grids at a location of Y equal to 0.085 meter and at a particular time of T equal to 0.7 milliseconds for a diaphragm pressure ratio of 11.5 for the bluff body case is shown in here. As and you can see, for the 1 mm and 0.5 mm mesh, the difference was not much. So I considered my as 1 mm as the optimized mesh for my study. So moving on to the results and discussions, I considered first the bluff body and for a diaphragm pressure ratio of 11.5. So you can see when the diaphragm bursts, a shock wave will be moving towards left, which will be towards the driven section, and my areas of interest is the driver section. So the expansion waves will move towards the body kept in driver section. When the expansion wave moves, the still air or the pressurized stagnant air will flow in the opposite direction. As you can see, when the expansion wave moves over the bluff body, the flow, when it flow over the bluff body at the edge, it will be like separating, and you can see some separation bubbles there. So the main interesting fact we observed was that moving shock generated in that during that expansion flow. So this makes a like interesting work. So as you can see, when that flow, like as the flow moves over the bluff body, you can see a moving shock is forming and it is traveling towards the downstream of the bluff body. So another interesting thing we observed is that movement of this moving shock. As you can see, the moving shock on the top and bottom travel upstream at different velocities, and it's evident. Like I have taken two exact location with respect to the midplane, and asymmetry is evident from the pressure plots at 2 different Y locations equidistant from the midplane of the midplane on either sides. So diffraction over the wedge, the same thing for the same diaphragm pressure ratio. As you can see, as the flow moves over the wedge, moving shock is also observed here. And for this diaphragm pressure ratio of 11.5, the Mach number or the flow will be supersonic. As you can see, when the supersonic flow moves over the wedge, an expansion fan is formed there. And again, the moving shock observed in the bluff body is also seen in this case also. So as you can see, it will be traveling downstream as the flow moves. And in this study of that wedge, you can see that moving shock on the top and bottom travels upstream at the same velocities. As you can, it is evident from the pressure plots at 2 different Y locations, equidistant from the midplane. And we're thinking it will be mainly because of the absence of recirculation vortex in the flow field. So this is the conclusion. We have numerically simulated the effect of diaphragm diffraction of expansion waves over a bluff body and a wedge for a diaphragm pressure ratio of 11.5. The flow induced by the expansion wave diffraction over the body was found to be supersonic, producing interesting flow features and shock structures. The main of the bodies we have considered was backward facing step over the bluff body. So you can see a pair of recirculation vortex over which a moving shock was identified. And the subsequent breakup of this vortex led to a flow asymmetry on either side of the midplane. But in case of wedge, it looks like that a supersonic patch with a centered expansion fan and terminating shock at the shoulder of the wedge. In addition to that, moving shock was observed. But in contrast to the bluff body, the moving shock in the wedge case were found to be symmetric and of the same strength. So these are my future work. I will be experimentally conducting experiments will be conducted for the same body shapes. And I will be varying the different diaphragm pressure ratios as well as different locations. We will be studying both experimentally and numerically. These are the references. Thank you.
Okay, thank you, Vishnu. Questions?
So Vishnu,
Yes.
good work. Wow, where is the sonic line?
Sir, actually, sonic line will be exactly at that. Like we have taken that Mach contour and we have seen that M equal to 1 will be here exactly at
No. You are having a moving shock upstream of it.
moving.
This shock, where is the shock coming from? An expansion wave running in and inducing the flow, right?
Yes, sir.
So where is the shock coming from?
Sir, where is the shock coming from?
Those vertical lines, what are those? They are
These are the shocks, sir.
yeah. So where the shocks running to the right?
Sir, as you can see, the expansion wave will be moving towards this driver section end, which making the pressure decreasing. So the shock formed will be moving towards that low pressure region.
So this is after the condition where the expansion is.
Yeah, expansion, yeah, goes back.
After the expansion has gone back, only you are studying. Okay, then only after that there is asymmetry in this.
Yes, sir.
Till that time there is no asymmetry.
Sir, that it's like we have observed it during my preliminary study. Like we have to make more conclusions based on this thing. Just a part of a preliminary study.
Is there any grid-based non-uniform
No.
asymmetry in this whole thing?
No, as of now, we have been observed that. It's not based on that big grid. It's happening. We have done some trials of experiments also, and we have observed this similar things. Like for the bluff case, the shock wave, that top and bottom shocks were moving at different velocities, and then the wedge case it was. But we have to validate. It's quantitative validate also. That.
This is actually a 2D simulation. In the experiment also.
Also 2D, yeah.
Planar kind of
Yeah,
simulation.
2D simulation.
Okay, that's interesting actually. I'll explain this shock moving backwards.
Thanks. Right. Any further questions?
Exactly like Professor Murganandan pointed out, it's quite interesting. One way to look at it, which a suggestion is to plot the XT diagram of the waves.
Yes, sir.
Right from the start of your simulations to understand where this shock waves actually start cropping up. And so your expansion waves are going to have a distribution, right?
Yes, sir.
They are like U minus A or U plus A kind of. If you look
Yes,
at it
sir.
in a 1D kind of system, we can then at least identify from which point
This
this
moving
kind
shocks
of
are,
effect is starting.
Sure.
So that's just a suggestion.
Okay, thank you.
Any questions? Well, if no questions, following up with Srisha's thing, you did an unsteady simulation, right? You did an unsteady simulation. So, but you would be having an idea right from, let's say, if T is equal to 0 is a diaphragm rupture.
Yes, sir.
At what time did you find these shock waves to occur or form?
Sir, when the expansion waves moves over the body and reflected.
You have a number for the any number for the time?
Yeah,
Let's say 10 microseconds, 20 microseconds, something like
It's
that.
after like it's between 0.5 and 0.8 milliseconds here.
Okay. 0.5 and so between somewhere around 500 to 800
It's almost,
microseconds. Okay. And right. Okay. Any more questions? Well, if no further questions, let's thank the speaker once again. And this ends the session. So let's break for coffee. Thank you.
Let us thank the session chair. I request Professor
You're
Srisha Rao to present a memento to our session chair, Professor Muhammad Ibrahim Sugarno. We shall now have a tea break. Thank you, everyone.
Hello? Hello, Deepak sir, can you hear me? Hello? Hello?
Hello.
Deepak Kumar sir?
Yes, I can hear you.
Yeah. The presentation will start shortly.
Okay.
Uh,
My voice is clear, right?
Yeah, your voice is clear.
Okay.
Audible. Do you want to test your
Presentation? Yes. So I'm going to share my screen.
Yeah, Mr. Deepak, can you
Yes.
hear me?
Yes,
Yeah,
yes.
I'm calling from the control room.
Okay.
There's some flicker in the video of yours. See, is your fan on?
No, sir.
Or are you using Logitech camera?
No, I'm using my laptop camera.
There's some disturbance in the frequency of electric. Or maybe there's some frame rating difference.
Okay, maybe I don't know.
I see a wavy image.
Yeah, I can also see.
That's because of your frame rate. Or you might be in 50 hertz of, probably your computer is setting in 50 hertz. It should be 60 hertz. All right. It doesn't matter. It's all right as long as, because your face anyway is going to be minimized now.
Yeah.
All right. Put it on the full screen and we can start.
So can you see my presentation?
Yeah.
Yeah, you can interact with the auditorium, please.
Okay.
So you want to check any videos or anything like that? Want to play?
I
video?
don't have any videos, so I will just keep forwarding it.
Yeah,
and
then
then
it's
you
okay. The presentation is very clear. Your
Okay.
voice is also audible.
Okay, good.
We'll start shortly. Please be online.
Just check if my pointer is visible.
Yeah, that is also visible.
Okay, good.
You can see it in your Zoom.
Okay.
We have zoomed it, the screen. You can see it in the side tile.
Just. Oh, okay, good.
Right? Right.
Okay, the slides are moving fine.
We'll inform you when to start.
Check.
Good evening, everyone. Welcome back. So for the upcoming presentations, I will invite Professor Rajkumar from Chemistry Department, IIT Madras, as a session chair. You can come.
Good evening. Thanks, Rajesh, for Rajesh and the team to give me this opportunity to chair this session. I understand the session is on chemical kinetics behind the reflected shocks or primary shocks. So now the first speaker is Mr. Deepak Kumar Singh. I guess he is working with my former PhD supervisor, Professor Arunan. He's going to talk on chemical thermometry in shock tube. I don't have specs, so sorry, I am struggling. Unimolecular decomposition of ethyl chloride and 1,1,1 trifluoroethane. So I request the speaker to please come. Thanks.
Thank you, Professor, for the introduction. So I will start my talk. Okay. Today I will be talking about chemical shock tube, and chemical shock tube, some pyrolysis experiments, specifically chemical thermometry, which is thermal decomposition of ethyl fluoride and 1,1,1 trifluoroethane behind reflected shock waves. Okay. So talking about shock tube, just a brief introduction. So shock tube studies are not new. It was started around 1900 by Weil in France, where he constructed the first shock tubes, and shock tubes after that were used by US, Canada, Great Britain to mostly study mine safety, shock-induced explosion, and aerodynamics. And the first application of shock tube in chemical kinetic experiments was started in Caltech. And then in 1960s, as the space exploration started, re-entry studies were done. In the 70s and 80s, laser experiments were done in Stanford, especially by Professor Hansen. And now in the current 2000 and after 2020, the shock tube has many uses, especially in astrophysics, astrochemistry, in blast wave, chemical kinetics, gas dynamics or aerodynamics, especially heat transfer, and spectroscopy for chemists. So basically, what is a shock tube? So it's already been discussed many times. So a shock tube for a chemist is basically a device which has ability to generate a high temperature or pressure ranging from a few microsecond to a few millisecond, depending on the dimension of the shock tube. So in the shock tube, we have a high pressure region and a low pressure region and a diaphragm separating the two regions. So when the diaphragm bursts, a primary shock wave will propagate in the x direction, and when the reflected shock wave meets with the expansion fan, you will have a proper test time for chemical reactions. So now I will talk about the chemical shock tube facility in our lab. So the chemical shock tube facility in our lab consists of two regions. One is so this is my driver section, which will be my high pressure section, and a driven section, which is a low pressure comparatively, and we have a ball valve which serves as a test section of the chemical shock tube experiment. We have a diaphragm slot separating the driven and driver section, and also my different equipments, turbomolecular pump, PID temperatures controllers, and data acquisition system where you have oscilloscope, PCB signal, and a LabVIEW, etc. And everything is controlled using an automated system using LabVIEW inside the control room, where we have a control panel along with different controls. And for identification of the components, we use gas chromatography, mass spectrometer, and gas chromatography, flame ionized detector. So these two serve as my detectors for different species of the chemical reactions. So when you talk about chemical kinetics in shock tube, there are two different ways to study the molecule or fuel. One is the experimental study, one is the theoretical study. We do both in our lab. So in experimental study, we use chemical shock tube as a thermal batch reactor. And then we do temperature calibration of shock tubes using chemical thermometry. And this shock tube can be used for pyrolysis and combustion at high pressure, at high temperature, and high and low pressures. For quantification or calculation of concentration of each and every species, we use gas chromatography, FID, and GCMS. So accordingly, we calculate the species distribution with respect to temperature. Another way of doing it, just to corroborate our data from experiment, we use theoretical study, electronic structure calculations, CBS QB3, CASSICF, MRCI for multi-reference calculation in Gaussian, and we try to calculate decomposition mechanism of each elementary reaction, energy and frequency calculations using transition state theory and variational transition state theory, and using different softwares, multival for rate parameter calculation. And using some existing chemical kinetic models, we make a Chemkin file, which is going to help us in simulation and comparison with experimental data. Finally, you can do a rate of production analysis and sensitivity analysis using Chemkin. And this, both the steps are very important in understanding the individual contribution of reaction for aromatic formation. And aromatic formation is very important to understand soot formation in combustion. So I will not talk about all these things. I will talk about a very small part of my work, that is temperature calibration of shock tube using chemical thermometry and some pyrolysis experiment. So how the experiment is performed. So this part I've already discussed, and this is my pressure trace signal. This is my initial pressure. P2 is my primary shock wave, and this is my P5, which is my reflected shock wave, and this is my dwell time or reaction time. And when the reflected shock wave interacts with the expansion fan, the cooling down of happens. So sometimes this is why it is also called a single pulse shock tube. And in shock tube, the calculation of temperature theoretically can be done by Rankine-Higuerit relations. But then in chemical shock tube experiments, there is a lot of uncertainty due to the chemical reactions. So that is why we have a different study related to chemical thermometry in shock tubes. So shock tubes are generally, for chemical reactions, are non-ideal. Why? First, there is a diaphragm opening time will depend on different diaphragms, and each shot can have different opening times for different materials. There is boundary layer growth at the walls, and also for chemistry purposes, endothermic and exothermic reactions are going to cause changes in the temperatures. And so what is chemical thermometry? We have two different methods. In internal thermometry, you will have the compound and the chemical thermometer along with the same sample. But in external thermometry, what we do the calibration of shock tube differently. So the fuel will be studied differently, and the chemical thermometer will be studied differently. So what is pyrolysis? So pyrolysis is basically thermal decomposition of any compound or chemical at elevated temperature in an inert atmosphere. So basically for our experiments, we have to take chemical concentration which is very low, around 1%, and rest is my argon species. In chemical thermometry experiments, we choose the experiment such that we are able to cover two different temperature regimes. So 950 to 1100 to 1150 Kelvin and 1185 to 1558 Kelvin. So for one range, we use ethyl fluoride decomposition, and for the second range, we have 1,1-trifluoroethane. So how do we do this calculation? So the initial rate expression, so this expression is already known. And if we want to back calculate our temperature, we just separate this T from this equation, and we get an equation. And this K experimental, the rate K and the theoretical T5 is calculated from the experiments, and then we plot a graph on the basis of this. So T5 kinetics is my experimental data, this one, and my T5 theoretical will be a theoretical calculation based on the Rankine-Higginbotham equations, and accordingly we get a state profile which is used for calculation in different experiments. So exactly similar thing is done for trifluoroethane, but for a different temperature range around 1184 and 1558 Kelvin. So my initial rate expression is already present. I know my K experimental and theoretical T5, and we can calculate this for the given temperature range, and accordingly, when we do our real experiments with the fuel, we can calculate the exact temperatures. So having discussed this, I will discuss only a few applications of shock tubes. So generally, there are two applications. One is pyrolysis, another is combustion. So for pyrolysis, cycloalkanes are very important compounds. Why? Because cycloalkanes are around 35% of conventional diesel fuels and 20% of jet fuel and 10% of gasoline. And cycloalkanes, it has been proved that precursors for soot formation in any engine. And as we see, there are cycloalkanes, decalene and hydrindane. So for hydrindane, which is a 6-ring fused with a 5-ring structure, the data, the available data for experiment as well as kinetic model is not available. So by experimental analysis, after this is the data which we get in post shock. So as you can see, we have two columns. So each column will be used to separate the product and the reactant. So for product, we have methane, ethane, propylene, alene, propyne, butene, and 1,3-butadiene. And for the high mass column, we have cyclopentadiene, methyl cyclopentadiene, benzene, cyclohexadiene, cyclohexene, toluene, methyl cyclohexadiene, styrene, and the reactant. So as you can see, whenever there is combustion or pyrolysis takes place, there are a lot of different components that are formed. And when you see a species profile, so you can see that we have chosen a temperature range, because in this temperature range, hydrindane is completely dissociated. And for my different products, we have ethene, methane, ethine, etc. And some other products, ethane, propene, alene. We calculate all this using the calculation from GCFIT, butene, butadiene. And there is one major thing which is there, that is the formation of aromatic compounds, that is benzene. So you can see that compared from toluene, styrene, benzene formation is much more. So this is an important observation of our experiment, which we will validate from our computational model. And then there are some very smaller components such as methyl cyclopentadiene, cyclohexadiene, and cyclohexene, which are formed in very small amounts. And so after this, experimentally, we calculate the overall rate of decomposition. So using this analysis and our computational model, we can validate the activation energy for the overall decomposition of hydrindane. And there is one more important application of shock tube, that is combustion. And in combustion, we study ignition delay studies. So what is ignition delay study? So ignition delay study is basically if you take a fuel mixture along with oxygen, you will behind the reflected shock wave, you will get pressure. So this is my pressure trace and this is my CH emission trace. So we use a monochromator along with the PCB sensor. So around 431 nanometer, we can see that CH emission occurs along with a rise in the pressure, abrupt rise in the pressure trace. So this signifies that from here to here, we can consider that this is my ignition delay time. And in our lab, we have different fuels, JP7, JP10, RP3, which Chaitanya will talk about. So I will not discuss much about ignition delay studies. And also we have high pressure ignition delay studies and low pressure ignition delay studies. So for formulating a complete kinetic model for any fuel, you need to have study based on pyrolysis also and a combustion also. Then you can formulate completely the study for any kinetic model for a fuel. So I will conclude my talk by saying that temperature calibration and chemical kinetics is important. As we saw, I discussed briefly the experiment about decomposition of hydrogen from 950 to 1600 Kelvin for 10 to 25 bar, and then just the a brief overview of ignition delay studies. So thank you, and I'm ready for some questions.
Thanks, Deepak. So you are in the US now, is it?
Hello?
Can you hear me?
Yes, sir.
Can you hear me?
Yes, now I can hear you.
Okay. You are in the US or?
No, I'm in India only, Bangalore.
Bangalore, okay, fine. So the floor is open for any questions? Yeah, Professor Hegde.
Hello, Deepak,
Yes,
can you
yes.
hear me?
Yes, sir, I can hear you.
I think this JP10.
Yes, yes.
I think this has been there for a long time. I think they have been studying. This is another variation of JP10 or the JP10 which they have been studying from 2010.
I'm actually not sure, sir, because it's still there in my chemical compartment, so I'm not sure.
Okay.
I cannot verify this.
Come on, Deepak, you cannot give this answer. You should know why you are doing. Instead of saying it is there in the compartment you are doing, I guess you should change that answer.
Because
Anyway.
that ignition delay measurement I said.
Right.
Okay, thank you. Thank you.
If there are no questions, I have several questions, but I'll refrain because I am the chairman here. I cannot trouble you.
Okay.
So, but one thing, the gap between that 1141 and 1185. So you are simply extrapolating. That gap can be filled with any other internal standard.
The gap between
1145. See, one is go to the other slide where you have described the slide number 9.
Okay.
See, 950 to 1141 and 1185 to 1558. Two different things you have taken. 1142, 1185, you simply extrapolate or?
I extrapolate from ethyl fluoride because the uncertainty for ethyl fluoride is less than the uncertainty of trifluoride.
But you have other compounds like cyclohexane or something like that. Did you work on that?
No, cyclohexane is there, but I think that is for low pressure, not high pressure.
And chlorocyclohexane, if you take it, what are the pressures you are working on? Yeah, that also will work out till 20 bar.
Okay, I will see.
That will cover from 1100 to 1100 to 1300.
Okay.
Roughly.
Okay.
That you should look into that.
Okay.
There are no other questions. Let us thank the speaker for a good talk. Yeah. Now our second speaker is Mr. Chaitanya Boyer. He's also working with Professor Arunan and Professor Jagdish. He's going to talk to us on temperature calibration of a single pulse shock tube at low pressures using unimolecular decomposition of cyclohexene.
Good evening, everyone. I am Chaitanya, and today I am going to present about temperature calibration of single pulse shock tube at low pressures using unimolecular decomposition of cyclohexene. So in previous talk, Deepak has already explained about the importance of shock tube calibration at high pressure conditions. But in this study, I will present about the importance of temperature calibration in low pressure conditions. So basically, we have calibrated the temperature behind reflected shock wave, and we have obtained a correlation between theoretical temperature and actual temperature in this study. So as all of us know that when we inject liquid hydrocarbon fuel inside scramjet combustor, it passes through various processes such as atomization, evaporation, and then the evaporated fuel basically mixes with incoming hot air. And after mixing and before the combustion begins, there is some time lag, and we call that as a ignition delay time. So since the air is flowing in the scramjet combustor at supersonic speed, the time available for completion of all these processes is about few milliseconds, and therefore ignition delay time is one of the important characteristics of any fuel. Also, many engine designers use numerical simulation for improving the design of the engine, and in their study for simulating combustion chemistry, they use various chemical kinetic models. So the developer of chemical kinetic model use the ignition delay data as a target data for validation. As you can see in the figure 2, this is a validation study of Narayan Swamy model with jet fuel in air study. So even though ignition delay time is one of the important characteristics, there is only high pressure ignition delay studies available in open literature, and people have not studied the ignition delay time of fuel in the low pressure condition. And it is expected that this scramjet combustor is expected to operate in pressure and temperature range of 0.25 to 3 bar and temperature range of 600 to 1500 Kelvin. Therefore, it is important to study the ignition delay time in the low pressure conditions and to study the effect of pressure on ignition delay time. So we can basically mainly use rapid compression machine and shock tube for measuring ignition delay time, but rapid compression machine is mainly used in high pressure and low to intermediate temperature. And we can use a shock tube for studying the ignition delay time in a wide range of operating conditions. So in our study, we are going to use CST3 present in our laboratory for study the ignition delay time of fuel at low pressure condition. So since I told that our tube is a single pulse shock tube, that means basically the reflected shock meets the reflected expansion fan before it meets the contact surface. And as you can see in the figure 5, there is this is basically pressure trace of a pressure sensor connected at 0.5 centimeter from the end flange. So there is arrival of incident shock, and there is again arrival of reflected shock at that pressure sensor. And then the pressure remains constant for some time, and then expansion fan comes and there is a pressure drop. Basically, there is also simultaneous temperature drop also. So we get the reaction time, that is basically time from arrival of incident shock to the time of arrival of expansion fan. So the equation A basically depicts, basically gives the ignition delay time in the form of Arrhenius correlation. And as you can see, the 1 by temperature is exponentially dependent. Basically, ignition delay time is exponentially dependent on 1 upon temperature, which you can also see in figure 6, which is the past, which is literature data about ignition delay time versus time. And there is exponential relationship between temperature and ignition delay time. So to generate reliable ignition delay time data, we need to know the actual temperature of measurements. So that's why the temperature calibration of the tube is necessary. In past, people have used 1D normal shock equations and chemical thermometry and tunable diode laser absorption spectroscopy for prediction of temperature behind reflected shock wave. But the the temperature predicted by 1D normal shock equation deviates a lot from the actual temperature, and therefore using chemical thermometry or TDLAS is a better option. So in this study, we have used chemical thermometry according to our convenience. So basically chemical thermometry means we use a molecule whose rate for whose decomposition reaction we know the rate parameter such as rate constant. So depending on whether we inject that molecule while doing the experiment or we study it separately, there is chemical thermometry with internal standard and chemical thermometry with external standard. I think in previous talk Deepak has already talked about the chemical thermometry, so I will move forward. So this is the our experimental setup. This is chemical shock tube 3 present in our lab, and in this shock tube we have attached 3 PCB sensors at 0.5, 45, and 155 centimeter from the end flange, and our shock tube inner diameter is 54 mm and outer diameter is 100 mm, and the length of driver section is 2.1 meter and driven section is 5.3 meter. We have used helium as a driver gas and argon as a helium as a driver gas and argon as a driven gas. So in this study, we have used 0.8 mm aluminum sheet with a orifice plate to achieve low pressure conditions in our shock tube. So this is the image of CST3 present in our laboratory along with GC and GCMS and GCFID to basically quantify and identify the product formed during the reaction. So for doing the experiment, what we do is initially we fix the diaphragm and then we evacuate both driver and driven section. Then we feel, since we get the required pressure, that is P5 and T5 by adjusting the P4 and P1, then we fill the driven section with argon to the pressure, the required pressure P1. And then again, we close the ball valve and then we fill our mixture. Basically, we have used 1.5% cyclohexene and 98.5% argon mixture that we fill into test section. And then just before doing the experiment, we open the diaphragm, open the ball valve, sorry. And then after we start filling that, then we set the data acquisition system. Basically, we are using oscilloscope, and then we fill the driver section to the required pressure. Basically, there is a groove on the diaphragm we are using. So the P4 we can adjust according to the depth of the groove. So once the diaphragm bursts, the shock travels and it reflects back and the reaction takes place. And after that, we collect the sample in the test cell, which is 2-liter test cell, and we inject into GC to analyze it further. So this is the chemical reaction. Basically, cyclohexene is decomposing into ethylene and 1,3 butadiene. And we have this, for this study, for this reaction, the rate constant was available from 0.8 to 3.7 atmosphere and 950 to 1300 Kelvin. A is basically rate constant. And the integrator first law is given as the final concentration of cyclohexene is equal to initial concentration into e to the power minus kT. So from the experiment, we obtain initial final concentration and test time, and from that we get the K rate constant, and by using the rate constant from equation 2, we get the temperature. So for calculating the initial concentration, basically we can get it from either from concentration of ethylene or concentration of butadiene, because 1 mole of cyclohexene is giving 1 mole of ethylene and 1 mole of 1,3 butadiene. So we have calculated the initial concentration from 3 methods. Third one is basically carbon balance method, and we use that method when we do not know the exact mole fraction we do not know stoichiometric coefficient of products formed during the reaction. And we have calculated the initial concentration from 3 method, and from that we got 3 different temperatures. The maximum, ideally they should give the equivalent temperature, but due to experimental uncertainty, there was around 20 maximum deviation of 20 Kelvin by using 3 different methods for calculating initial concentration. To get the theoretical temperature, since we have attached 3 pressure transducer, we got average velocity in between the pressure transducer. So we have extrapolated that average velocity to the end flange and considering the shock attenuation, and we got the shock velocity at the end flange. And from that shock velocity, we got incident shock Mach number at end flange, and from using the gamma CP, that is specific heat ratio of driven gas, we calculate the theoretical T5. So this is comparison of theoretical and actual temperature, and we found that at the highest temperature that we have calibrated our tube for, the temperature difference was around like percentage temperature difference was 8.86%, and basically the temperature difference increases at higher temperatures. And we have plotted the T5 actual and T5 theoretical, and we got linear correlation, and we will use this linear correlation in our future studies. So as the author has claimed that the cyclohexene decomposing into 1,3 butadiene and ethylene is the only path that the reaction is taking place, but we found that around 1140 at and above 1142 Kelvin, we found many other products such as 1,3 pentadiene, cyclopentadiene, methyl cyclopentadiene. So if we have to use the same rate constant equation for till 1300 Kelvin, then we have to consider the concentration of other products to calculate initial concentration. So we decided to keep our study limited to 735 Kelvin of actual temperature. So now we have started low pressure ignition delay time measurement in our shock tube. This is basically a signal we got for a pressure of 1.6 bar and temperature of 1128 Kelvin, and equivalence ratio of 1. We have used RP1 as a fuel. And as you can see, we have used CH emission as well as pressure to get the ignition delay time. Basically, that is time from the arrival of reflected shock to the sudden, the maximum slope of pressure rise, or basically maximum slope of CH emission. So in this study, we have calibrated our shock tube in the range of 970 to 1136 Kelvin, and pressure range of 0.85 to 3.75 bar. And the deviation in theoretical and actual temperature highlights the need for temperature calibration. We have also shown the disadvantage of using cyclohexene as external standard above 1142 Kelvin, because then the calculations will become tedious. And we have started the low pressure ignition delay time measurement study in our lab. Thank you.
Well before time, thank you. So floor is open for the questions, suggestions.
Sorry, I might have missed this one. This tunable laser diode, the spectroscopy. Where did you use?
No, we have not used, but people use that for getting temperature behind reflected shock wave.
Okay, that means the same measurement it can be done using that one.
Temperature measurement, yes.
Yeah, Srish.
So now you say this is low pressure measurement, right?
Yes, sir.
So, and you got a 0.4 milliseconds or so as your
ignition delay. Yes, sir.
So how does it compare to some standard, say, higher pressure
So actually, for
measurements?
comparing with higher pressure, we will have to get more signals, and then we can form the correlation that I have shown you before.
No, so this for RP1, it's not existing. The high pressure data is not there.
High pressure data is there, but that is the only one signal, and that
No,
I
no,
have,
just
still I
so
have not.
you
compared
have
with high
not
pressure. Yes.
looked at that.
Yes. We will first fit the data, and then we will compare it, because mainly data is available, and that is normalized for some constant pressure. Like even they got at different pressures, they have normalized it to certain pressure. So we will also form that correlation, and we will normalize it, and then we will compare.
Okay.
So, can you, if you don't mind, could you please go to that ignition delay measurement that,
Yes, sir.
yeah, this one. So, what is the line, which line you are following? CH emission, is it?
Yes, sir. Blue one is CH emission, and the black one is pressure rise.
Okay, how do you, what is the source of your CH? It's a reactant itself, is it? But did
Yes,
you
yes, sir.
calibrate that with the standard CH emission?
So actually, we are not quantifying the CH emission. We are just finding where this CH
Whether it
started
is a
from
CH emission or not, that's all.
yes. And for 431 nanometer of wavelength. Basically, we are using monochromator and we are just finding the signal of 431 nanometer emission.
Typically, what is the, what is the detector you have?
Monochromator, VM502 monochromator.
Okay.
Sir, I can answer that question. Deepak here, online.
Yeah, please.
Okay, so so the monochromator is with a photomultiplier tube, and that is already calibrated with a mercury lamp. So we know that it is a correct emission.
So 430 line at mercury line, is it? Mercury line at 430 nanometers, you use that and then calibrate with the monochromator, that PM tube.
Yes.
Measure the intensity and then, okay, that's all, fine. 430, that's right. That's okay, fine.
And okay, I will answer one more question. Professor Hegde asked.
Okay.
So earlier in our lab for combustion studies, we did not have TCD. So from TCD, we can calculate carbon monoxide and carbon dioxide. So then we can make a complete model. So that's why we will have that fuel study.
Deepak, we can measure.
Yes.
We don't calculate the carbon monoxide there. We'll
No,
measure,
measure.
we'll measure the concentration using thermal conductivity detector.
Yes, yes, yes.
Right, yeah, fine.
Earlier it was not there.
I know that, I know. Yeah. Very well, very much aware of that. All right. So if there are no further questions, please join me in thanking the speaker, Chaitanya. The last speaker of this particular session is Kushiram. Am I spelling it right? Pronouncing it right? Kushiram, right? Okay, fine. And you are IIT Delhi. Okay, fine. Okay, fine. He's going to talk on an experimental investigation of shock behavior of glass and basalt fiber composite. Let me try 1 minute. Laminates using shock tube. Yes. Sorry, I think I definitely need spectacles. Yeah, sorry.
Good evening, everyone. Myself Kushiram, and I'm from IIT Delhi. Today, I'm going to discuss about an experimental investigation of shock behavior of glass and basalt fiber composite laminates using shock tube. So in past few years, a lot of casualties happened due to the blast explosions. And in order to save human lives, there is requirement of the design and development of blast mitigation material systems. So these are few candidate materials for blast resistant system. Ultra high molecular weight polyethylene, UHMWP. It is a advanced ballistic fiber which has a density less than water. So it is used to make composites light in weight. And another is Kevlar, mostly used ballistic fiber. Earlier it is used. And rubber and polyurethane foams, which are used to change the shock or blast medium. Ceramics, which are used to deflect the blast waves because they are hardest after diamond and cubic boron nitride. And basalt, it is an organic fiber which has a higher thermal properties. And polytheramide, which is a polymer which is used as a matrix material. So it also has a better thermal properties. And honeycomb and corrugated plate structure, which is used to dissipate the blast energy. Functionally graded composite structures in which one or different materials combined together, so they can absorb or mitigate or deflect the blast waves in order to save the, attenuate the blast pressure. And the sandwich structures in which front and back face plate, in between these the corrugated or some foams are filled, so the blast, they absorb the blast energy. So this is the in-house design of developed shock tube facility, which is used for the carried out the experiments used in this study. The fabrication of composite laminates. So in composite, there are two parts. One is matrix and one is reinforcement. So for matrix, in this study, polypropylene is used, which is available in the form of granules. So using a single screw extruder, these granules are converted into the sheet form. and then fibers, and then these matrix are cut into a suitable size and stacking up to a desired thickness level. And using compression molding, at optimum pressure and temperature, these composites are fabricated. So this one is showing one laminates in which strain gauges are mounted to measure the deformation which is observed during the test. So these are the results. As the pressure increases, the center point deflection also increases, and at a threshold value of pressure, these specimens observe deformation, the fibers get ruptured, or shear deformation is observed. So as seen, the first image shows how the specimen is mounted. The in second image is shown the fibers are undergo tension and compression, so they get stretched and from the boundary layers. Again, the failed specimen, as seen, the fibers are completely undergone the shear failure, and the delamination of matrix happen due to when the shock waves impacts on the specimen, and also strain gauges also removed due to the impact of the shock loading. So these are the strain gauges when a shock wave impacts and the fibers get distorted and failure, the strain gauges wave off and the response is not correct. So my conclusions are there is a threshold value at which the material sustains the energy, and after that the failure occurs. The fibers undergo the delamination, shear failure, and for the measurement, the strain gauges are not suitable. So the digital image correlation, which is used for the further studies, and I conclusion that the basalt and polypropylene laminates absorb more energy as compared to glass fiber matrix. Francis, and thank you.
Okay. Sharp, crisp, and clear. So, questions? I'll get back. Yeah. System.
A shock tube.
Beautiful shock tube. And you are putting your laminate at the end of the,
yes,
which location that is? The next slide.
At this, laminates are mounted at that location.
What is the diameter of the shock tube?
Internal diameter is 100 mm.
How many layers?
Of which laminate? It is a density, it's a 1 mm thickness. So basalt and glass, both are of 1 mm thickness. So there are 6 layers of glass, and its density of basalt and glass is almost same. So almost
Okay. Strain gauges are on the surface of the outside. Strain gauges?
Strain gauges at other side. Once this side is a shock impacting, and an opposite side shock strain gauges are mounted.
That means when that ruptured,
yeah,
strain gauge signal. Okay, that I understand.
Yeah.
After that, the signal was going up.
Yes.
Up to that point only.
Yes.
That is completely ruptured.
Yeah.
Have you done some hardness test on your material, or do you have knowledge of how hard?
Yeah. For polymers, Shore D test is for polymer composites. There are normal test Rockwell, and these hardness tests not work. Shore D, there are for polymers there are another available. So I don't.
You said you have kept the strain gauges on the other side of the laminate, right? How is the life of those strain gauges if the laminate gets ruptured or something like that?
That's why I say digital image correlation is better, because when a specimen ruptured, the strain gauge also break, wire breaks or something happens, so data is not.
In your case till now, have you ever faced that?
Yeah.
Losing the strain gauges?
Yeah. That's why I suggest digital image correlation is better as compared to strain gauges in case of composites. If metal is, then strain gauges can work properly.
Okay, for how many tests, how many strain gauges you have lost?
So many, because single. No, sir. One strain gauge is used for one time. It's used. Yeah.
Were you able to, because it's a layer process in a composite, were you able to fix in the strain gauge sensor inside the composite and get the in between the laminates?
Yeah, but during fabrication, I insert the strain gauges inside. but the wire comes from the strain gauge. Then in a compression molding, there is a heating and pressure also. The laminate, these laminates are 200 degrees Celsius at temperature they are fabricated. So wire gets melt off. Yeah, pressure and also compression. These are fabricated 100 bar pressure of compression molding and temperature up to 200 degrees Celsius. And this polythermide, it melting time, it goes up to 400 degrees Celsius. So it's brittle in nature and PP is some ductile in nature. So I use PP here.
So any other questions? Yeah, Sirish, yeah, please.
So your specimen is at the end flange, right? Is it open or no? The end flange is completely closed.
Completely closed.
Okay, so the boundary condition behind the plate is it is having a rigid wall.
Yeah.
Right.
Yeah.
So there is no deformation of the, your composite laminate.
Composite deforms.
I mean, from the backside. Backside is rigid.
I show. This just like that. In first the specimen, so I only open the 100 mm diameter only specimen. Specimen
Okay.
size is 200 by 200 mm square plate. So the disc is used between, this is a specimen, then a disc is used. So I clamp this disc with the specimen.
Okay.
So
Okay.
only the
So if your suppose there is a failure of your specimen, failure of your specimen,
failure of,
then the shock tube flow is going to come out
yeah.
Into open.
Yeah.
Then
No, there is
that's what the thing is, or am I missing something?
No, this is a chamber. Yeah. This one is a chamber. So it's
Okay.
a closed chamber.
Everywhere, even what I am seeing as an opening, that is you close that.
This is a window. So I make this window for a digital image correlation. So
Okay.
there are two windows. This window used for a light source, to put a
Okay.
light source
Okay.
here, and another window in front of the specimen at the same level. So from there, I put the cameras.
All right. Okay. Thank
Yeah, the flange is either closed or open. You don't have to say completely closed. It cannot be partially
Yeah.
closed. Okay. Yeah, fine. If there are no further questions, please join me in thanking this speaker as well as previous two speakers. Thanks for joining.
Thank you.
The session is ended.
Okay. I request Professor
Thank you, sir. There is one more announcement to be made.
Good evening, all. I'll just wait a few seconds on this. Oh, no, that's fine. No problem. Take your time. Okay. Good evening, all. I'm here to make an announcement. Next year in February 2023, please note the dates 15th to 17th in the Physical Research Laboratory, Ahmedabad. We are hosting the National Shockwave Symposium, National Symposium on Shockwaves, the 7th symposium. Okay, so I'll be the chair. My colleague Dr. Vijayan will be the co-chair. So we would like to invite you all to the National Symposium on Shockwaves. So please do come, and the abstracts are open now. You are most welcome to submit abstracts. The deadline will be 30th November. Registration fees will be not so high. We try to make it, as less as possible, and also try to support some students for their travel and other arrangements. Okay. Not for all, but for a few of them. So please do. And we will be circulating the information soon over email. We'll share with you all. Initially, we had a set of emails which we had used, but after attending yesterday's session, I came to know that some of the emails are very, very old. So the information hasn't gone to many of the people in the community. Okay, so we'll welcome you once again. Thank you.
Thank you, everyone. That concludes day 2 of SIS 2022. We'll see you tomorrow at 9 a.m. Thank you.